Very good morning, everyone. So, welcome to this GATE 2026 marathon sessions. I hope I am audible to everybody. So, please let me know so that we can start the session. Please let me know in the chat box. Am I audible to everyone? Is my voice audible to everybody? Very good morning, everyone. So, welcome to this GATE 2026 marathon sessions. I hope I am audible to everybody. Yes. Okay. All right. Fine. Fine. So we'll start in 20-30 seconds. So please share this session to your friends who wanted to join this session. Yeah. Yes, we'll start very soon. Start very soon. Okay. Yeah, I'm planning to discuss all the four machines. It's a lengthy subject, as all of you know that. Yeah, so let's see how far we can cover. So I'll try my best to make sure that all the four machines are going to be covered. Okay. So as most of you know that this is just a revision session. Okay. So a marathon session. And one thing everybody has to understand, we cannot learn electrical machines in a single day, but this session will definitely help you for your quick revision. Okay. Probably to understand the main concepts. Okay. Which are highly expected in the final examination. Also, I'll try to discuss formulas, mainly focused on formulas, characteristics, okay, circuit diagrams, etc. And here and there we will solve some numerical questions also. Okay, so let's see how far we can cover. Okay, so four machines in a single day, it's going to be hectic, and I'll try so making sure that all the four machines are going to be covered uniformly. So we'll be starting with induction machines today. Okay, the first session is going to be induction machines. So what I'm trying to do in this particular discussion is that we'll try to discuss the summary points related to electrical machines, and related to the topics that we are going to discuss, we will solve some of the previous year gate questions also, so that whatever I discussed, it will be have a complete conclusion, so that you can answer new questions in the final examination. Okay, fine. So just a moment. Okay, all right. So coming to the point, so when I'm talking about induction machines, one of the important area, at least you can expect 2 to 3 marks from this particular topic, induction machines. Okay. So normally, if you look at the topics that are available in the syllabus of the GATE examination, so we need to understand the basics related to, just a moment. Yeah. So we need to understand the basics related to induction machines, and then the construction of induction machines. Okay, I don't focus much on construction part. This is more theoretical in nature. Okay, so we'll quickly go to the actual topics. Okay, and then we will talk about slip calculations. All right. So this is one area where you can expect at least one question. Every year in GATE examination, one question will definitely come from the slip calculations. Okay. So then we will talk about equivalent circuit of a three-phase induction motor. Okay. So once the equivalent circuit is completed, then we will talk about power flow diagram. This is another important area. So how power will flow from the input side to output side of an induction motor. So once we understand power flow diagrams, then we need to have a revision about torque equations. So there are number of torque equations available in induction motor subject. So what is starting torque, what is maximum torque, generalized torque, relation between starting torque, maximum torque, etc. Again, in these torque equations, two topics will be available. One is if stator branch impedance is considered. Another one is if stator branch impedance is neglected. Okay, all right. So torque equations, and then we will talk about torque speed characteristics. Okay, so speed torque characteristics of three-phase induction motor. All right. Okay, so once we are done with characteristics of the induction motor, then we will discuss about testing. I don't cover about state testing in this revision session. The time will not permit us. Okay, so we will skip this testing part, but I request you to study testing also, the no load test, blocked rotor test, etc. And then we will go to speed control topic, one of the important area where you can expect some questions. Okay, speed control. Later we will talk about starting methods. Okay, so there are different types of starting methods available for induction motor, like series reactance starting, auto transformer starting, star delta starting, etc. So once we are done with the starting methods, then we will go to single phase induction motors. Single phase induction motors. I'll be skipping some of the topics like braking methods, okay, harmonic analysis like cogging, crawling, etc., because they are much theoretical topics and the time doesn't permit us to discuss all those things. Okay, so because I'm trying to keep around 1.5 hour time for each machine's subject, so obviously it will go up to 2 hours. So even if I take 2 hours for each machine, it will take 4 machines 8 hours. In between we can have some breaks, so overall session will go beyond 10 hours. So it may not be possible to discuss each and every topic in detail, so I'll try to cover some important topics. Okay, all right. And I repeat again, this particular session is useful only for your quick revision. Okay, you cannot learn the subject completely. This will just help you for a quick revision. Okay, so in a normal classroom, we use it to discuss a single machines for about 40 hours, 42 hours, like that. So covering that in 2 hours means you must have an initial idea about machines concepts. Okay, and then only you can cope up with this particular session. If you are a first time learner, then this session is going to be a tough call for you. But if you have already learned induction machines and you are looking for a quick revision, definitely this session is going to be helpful. Okay, especially for those students, okay, who wanted to revise the subject quickly just before the examination, this is going to be helpful for you. All right. All right, so without wasting our time, so let us quickly move to our first topic. Okay, that is basics of electromagnetic torque. When I'm talking about three-phase induction motor, first of all, what is meant by a motor? If you wanted to call a particular machine as a motor, motor is a machine which converts electrical form of energy to mechanical form of energy, right? So we will give electrical power as the input and we will get mechanical power as output. That's a simple statement, right? And question is that on what principle basis this electrical motor is going to work. Okay, so electrical motor will work based on, okay, Lorentz force equation. Okay, so Lorentz force equation, simple equation. You will learn about these basics in your +2 level or diploma level, right? Okay, so what Lorentz force equation states that according to Lorentz force equation, whenever a current carrying conductor is placed inside a magnetic field, it will experience a force. Simple. And what is the magnitude of that force? Force is equal to BIL sine theta. Okay, you take a conductor, give conductor of length L and give some current to that conductor and keep that conductor in a magnetic field, definitely that conductor will experience a force. And because of that force only, the conductor started to move. That is how electrical motors will basically work. Be it a DC motor or induction motor or synchronous motor, it basically works based on the principle of Lorentz force equation. Okay, but the conditions are different for each motor. Okay, so what type of magnetic field we are using, what type of current we are using, are we using DC current or AC current? Are we using a time varying field or time invariant field? Are we using a rotating magnetic field or stationary magnetic field? So these are the different kind of things which will separate different types of motors. For example, if you are talking about DC motor, the current will be DC current and the magnetic field will be time invariant and stationary. If you are talking about induction motor, current is going to be AC current and magnetic field will be time varying and rotating in nature. If you are talking about a synchronous motor, current will be AC current, magnetic field will be time invariant but rotating in nature. So this is what is important to understand the difference among various types of motors that we have. Okay. Now, when I am talking about a force is being created, the question is how to identify the direction of that force. Yes, most of you know that the direction of a force can be identified using Fleming's left hand rule. Okay. So Fleming's left hand rule. Fleming's left hand rule. So what is the purpose of Fleming's left hand rule? Fleming's left hand rule does not give you magnitude of the force. Magnitude of the force is given by Lorentz force equation. But the direction of force can be identified by Fleming's left hand rule. So how to practice Fleming's left hand rule? Yes, according to Fleming's left hand rule, the first three fingers of your left hand must be placed in a mutual perpendicular direction. So this is a thumb, this is a point finger, and this is the middle finger of the left hand. So according to Fleming's left hand rule, thumb will always give you the direction of force. This is our requirement. We wanted to find out the force direction. Point finger will give you magnetic field, and remember magnetic field is always from north pole to south pole in the air medium. And then the central finger of the left hand will tell you what is the direction of current. Okay, so if you know any two parameters, the third parameter you can identify. If you wanted to identify the force direction, you need the current direction and also the magnetic field. Got it? So magnetic field and current, if you are able to identify, then automatically the force direction can be identified. Okay, so I'm not practicing that left hand rule, it will consume time. So just to try to understand, Fleming's left hand rule will give us the direction of force acting on a conductor. Okay, right. Now, let us understand what is the basic torque equation. See, I said this is a basic torque equation which will be applicable for any type of rotating electrical machine. Yes, let me write down quickly. The electromagnetic torque produced in rotating electrical machine, okay, is generally proportional to, electromagnetic torque is proportional to minus F1 F2 sine lambda. Okay, so here F1 is nothing but stator MMF. F1 is nothing but stator MMF. F is a symbol which indicates MMF, magneto-motive force. So F1 is stator MMF and F2 is rotor MMF. F2 is rotor MMF. That means to create electromagnetic torque, you need two magnetic fields. One will be created by stator, another one will be created by rotor. Okay. Next, imagine these two fields are separated by a phase angle lambda. We call that lambda as a torque angle. It is the angle between stator magnetic field and rotor magnetic field. And as the two fields are separated by some phase angle, the resultant field will be definitely vectorial sum of the two. Okay. So this is going to be the resultant magnetic field. We also call it as air gap field. Okay. That is sum of stator field and rotor field. Okay. Now the question here is that to create electromagnetic torque, there are three rules to be satisfied. To create electromagnetic torque, there are three rules. If these three rules are satisfied, then only electromagnetic torque can be created. The first rule is stator and rotor must have same number of poles. Very important. The poles in stator must be equal to the number of poles in rotor. For example, if a stator is a 4-pole design, rotor must also be designed for 4 poles only. If a stator is a 6-pole design, the rotor must also be designed with 6 poles only. So the number of poles in stator and the number of poles in rotor must be equal. This is the first rule. Second rule is relative speed between stator field and rotor field must be equal to 0. Okay. I must say relative speed. It's not speed, it is relative speed. Relative speed between F1 and F2 must be equal to 0. Must be equal to 0. So that means what? If a stator field is traveling with synchronous speed, rotor field should also travel with synchronous speed in the same direction. Both fields must travel at the same speed in the same direction, then only the relative speed will be equal to 0. And one more point, if these two fields rotate with synchronous speed, can I say the resultant air gap field will also rotate with synchronous speed? Yes, therefore in induction motor, if I ask you what is the speed of a stator field, that is ns rpm. What is the speed of rotor field, that is also ns rpm. Then what is the speed of air gap field, that is also ns rpm. All the magnetic fields are rotating in nature and they are rotating at a synchronous speed. Then what is the relative speed between stator field and rotor field? 0. This is another condition to be satisfied to create electromagnetic torque. And the third condition is the phase angle difference between stator field and rotor field must be finite. Lambda, that is nothing but lambda. Lambda must be finite. First of all, what is lambda here? Lambda is the angle difference between stator field and rotor field. That lambda must be finite value, then only electromagnetic torque can be created. For example, what if lambda is equal to 0? Yes, if you replace lambda equal to 0 here, what is sine 0 will be equal to 0. Therefore, electromagnetic torque will be equal to 0. So therefore, to produce electromagnetic torque, a finite phase angle difference is required between stator field and rotor field, then only torque can be produced. Now, if you clearly look at this equation, there is a negative sign also involved here. This negative sign states that the existence of Lenz's law. Please understand, I am only discussing the summary points here. I am not trying to prove any derivation or any concept in detail. Only the summary points we are discussing. Okay. So here the negative sign represents the existence of Lenz's law. What Lenz's law states that effect must try to reduce the cause of the production. So here the effect is nothing but electromagnetic torque and the cause is nothing but finite torque angle lambda. This is the cause. And this is the effect. For example, if lambda is equal to 0, torque cannot be created, right? So to create the torque, that torque angle lambda is important. Now what Lenz's law states that this effect will try to reduce that angle lambda. So another question, how can this lambda value can be reduced? Can I say this lambda value can be reduced if stator field and rotor field try to align with each other? Yes, if stator field and rotor field try to align with each other, then only that lambda value can be reduced. Therefore, according to Lenz's law, whatever electromagnetic torque is created, it will try to reduce the angle lambda. That means stator field and rotor field will always try to align with each other. Very important. Okay, stator field and rotor field will always try to align with each other. Clear? So that means what? There is an attractive force between stator and rotor or repulsive force? Yes, there is an attractive force between stator and rotor. Then only both can align with each other. Clear? Okay. Next, one more point I told you. Yes, stator field and rotor field, both are stationary or both are rotating? Yes, both fields are rotating in nature. Stator field is rotating, rotor field is also rotating. This is what we call it as rotating magnetic field. Rotating magnetic field. Stator field is rotating in nature, rotor field is also rotating in nature. Rotating magnetic field. Now, how can you create rotating magnetic field in electrical machines? Simple. To create rotating magnetic fields, there are two conditions again. First one is we need a polyphase distributed winding. A polyphase distributed winding is required. When I say polyphase, what exactly mean by polyphase? Polyphase means any number of phases except single phase. Any number of phases except single phase. It may be two phase or 3 phase or 6 phase, 9 phase, 12 phase, any number of phases except single phase. Such type of winding is known as polyphase winding. And also we need concentrated winding or distributed winding. Distributed winding. If it is a concentrated winding, rotating magnetic field cannot be created. We need distributed winding. Clear? Okay. Next, this winding must be excited with AC current. Must be excited with AC current. AC current. So if you take a 3-phase distributed winding, for example, then excite that winding with 3-phase AC current. If you take 2-phase distributed winding, excite that winding with 2-phase AC current. If you excite this winding with DC current, rotating magnetic field cannot be created. Now, for example, if I am talking about 3-phase induction motor, obviously the stator will have 3-phase distributed winding. Stator will have 3-phase distributed winding. Now what I am doing, let me excite this distributed winding, 3-phase distributed winding with AC current. Give 3-phase AC current to this winding. Okay, so when I give 3-phase AC current to a 3-phase distributed winding, what will happen? Rotating magnetic field will be created. So because of this, a rotating magnetic field is created. A rotating magnetic field is created. When I say rotating magnetic field, it will have direction of rotation, obviously. In which direction it is rotating? Yes, it depends upon supply sequence. Okay, I'm quickly going through the summary, guys. Okay, please understand. So when I say the field is rotating, the question is in which direction it will rotate? Yes, the direction of rotation will depend upon the sequence of the supply. Okay, so if I give ABC sequence, for example, then RMF will rotate in forward direction. Forward RMF is created, and the magnitude of that RMF will be equal to magnitude of the resultant. Yes, the resultant magnetic field is equal to 3/2 F max cos omega t minus theta. Okay, so this is ampere turns per pole. This is MMF equation. Resultant MMF means it is a combination of all the 3 phases, A phase, B phase and C phase together. And why we have a 3/2 F max here? This 3 represents the number of phases we are using. For example, if you use a 2-phase distributed winding, then this would have been 2/2 F max. If I use 6-phase distributed winding, this would have been 6/2 F max. I am using a 3-phase distributed winding, that's why this is 3/2 F max. What is F max here? Where F max is nothing but maximum MMF of each phase winding. Maximum MMF of each phase winding. For example, if every phase has a maximum MMF of 1000, then all 3 phases together, what is the resultant maximum value? 3/2 into 1000. That will become 1500, right? And also you're observing a term called omega t and theta. Here, omega t is nothing but a time angle and theta is nothing but a space angle. Okay, that means the resultant magnetic field was varying with respect to time, that is time varying, and also variable with respect to space. When I say space variation, that means it is movable in nature. See, right now I'm standing here. So spatially, I was to the left side of the board. If I move spatially, I am to the right side of the board. This is what we call it as spatial movement, the physical movement. Spatially, I am moving. So when I say some object was variable with respect to space, indirectly, it is movable in nature. Okay, movable in nature. This is a situation when I excite that 3-phase distributed winding with which sequence? ABC sequence means positive sequence supply. Now what if I excite this winding with ACB sequence? Can I say ACB sequence means negative sequence supply? If the supply was a negative sequence, the same rotating magnetic field will rotate in backward direction. So it will create backward rotating magnetic field. Backward rotating magnetic field. Backward means it will rotate in opposite direction. Then what is the magnitude? The resultant MMF magnitude will be equal to 3 by 2 F max cos omega t plus theta. See the change in the equation. Ampere turns per pole. Look at the change in the equation. If I use a positive sequence apply, it is a 3 by 2 F max cos omega t minus theta. If I use a negative sequence apply, that is a 3 by 2 F max cos omega t plus theta. This was the magnetic field rotating in backward direction. This is the magnetic field rotating in forward direction. Now, what is meant by ABC sequence? Is it not positive sequence? So positive sequence apply will create forward RMF. Negative sequence apply will create backward RMF. Got it? Okay. Now the question is, what if I use zero sequence apply? Zero sequence. If I use zero sequence apply, the resultant MMF will be equal to 0. That means RMF cannot be created if we use zero sequence apply. RMF can be created only when we use positive sequence or negative sequence apply. Clear? Next question is, at what speed the rotating magnetic field will move? Yes, rotating magnetic field will move at a synchronous speed. What is the formula for synchronous speed? 120 F by P, where F is nothing but supply frequency and P is nothing but number of poles. Okay, so when you excite any three-phase distributed winding, at what speed the magnetic field will move, that is nothing but synchronous speed, 120 F by P. Okay, yes, this is about the basic electromagnetic torque equation and also about rotating magnetic field concept. Okay. Okay. Next, we will try to understand, we will try to revise what is the operating principle of a three-phase. Just a moment. The session was running smoothly, right? Hope there are no issues. Yeah. Okay, yeah, going well. All right, now. So let's try to understand the operating principle of induction motor. Very simple principle, very simple principle. Induction motor will operate based on mutual induction plus Lorentz force equation. See, it is a combination of mutual induction and Lorentz force equation. I will quickly try to understand how this is going to be. See, induction motor will have two windings. One will be available on stator, another one will be available on rotor. Now, point is, stator will have a three-phase balanced distributed winding. Okay. Now, what we will do, we will excite this stator winding. It may be star or it may be delta. Any kind of winding you can select. Okay. Generally, high voltage motors will have star connection. Low voltage application motors will have delta connection. Okay. Yes. Now, what I am doing, I am exciting this stator winding with AC current like IA, IB and IC. Now what happens, this stator will create a rotating magnetic field. That's what I explained so far. For example, if I use a positive sequence apply, the magnetic field will rotate in forward direction. That stator field will cross air gap and link the rotor. Rotor will also have a distributed winding. And remember, there are two types of rotors. Squirrel cage rotor will be there, slip ring rotor will be there. Okay, so whatever may be the type of rotor, rotor will have distributed winding. Okay, and the point is, all these rotor terminals are short circuited like this. The rotor is a distributed winding, but the point it is short circuited. That means it is like a closed circuit or open circuit. It is just like a closed circuit. Okay, now what will happen? The stator will create a rotating magnetic field. That rotating magnetic field will cross air gap and link the rotor. This is the magnetic field. It will cross the air gap and link the rotor. Is it like primary winding flux in transformer links the secondary winding. Therefore, stator acts like primary winding of the transformer, rotor acts like secondary winding of the transformer. Therefore, what will happen? A self EMF will induce in primary and a mutual EMF will induce in secondary. Got it? Isn't it? And E1 by E2 is equal to number of turns in primary N1 by N2, the turns ratio. Now, once a mutual EMF induces in the secondary, that's what I told you, mutual induction phenomena. And rotor is a closed circuit or open circuit? Closed circuit. Because it is a closed circuit, the current will be generated immediately. If it is open circuit, current cannot be generated, but rotor is a closed circuit, so immediately current will generate. Now rotor will have normal conductors or current carrying conductors placed inside a magnetic field. Current carrying conductors placed inside a magnetic field. So whenever current carrying conductors placed inside a magnetic field, force will be created. Okay, force will be created. And because of this force or torque, you can use any word. Linearly we call it as force, but angularly we call it as a torque. So because the force is created, the rotor started to rotate. That's all. The rotor started to rotate. Therefore, three-phase induction motor is a self-starting motor. It is a self-starting motor. You don't need any external help. And one more important thing, it is a singly excited motor because I'm only using one supply source, which is nothing but three-phase AC supply. So I give AC supply to the stator. Stator will create a magnetic field that will cross the air gap and link the rotor. EMF will induce in rotor, mutual EMF, and that will create a current in rotor because rotor is a closed circuit. And those current carrying rotor conductors will start rotating. But the question is, in which direction they will rotate? Yes, rotor will rotate in the direction of a stator field. Rotor will rotate in the direction of stator field. In the direction of stator field. Okay, very important. Rotor will rotate in the direction of stator field. In the direction of stator field. First of all, stator field is rotating in which direction I told you. If the supply is ABC sequence, stator field will rotate in forward direction. Then rotor will also rotate in forward direction. If you give ACB sequence supply, stator field will rotate in backward direction, then the rotor will also rotate in backward direction. But one more question, at what speed the rotor is going to rotate? At what speed? Rotor will not reach exactly synchronous speed, guys. Rotor will rotate at a speed near to synchronous value. Why, if I wanted to explain, it will take a lot of time, so I'll try to make sure summary is discussed. Okay. So normally, you just imagine this is the stator part of the machine. Okay, stator. It's a stationary frame. Stator will have a three-phase distributed winding. And this three-phase distributed winding, we are exciting with positive sequence supply. Imagine stator is having P number of poles and excited with a frequency F. So whenever a distributed winding is excited with AC supply, what will happen? A rotating magnetic field will be created. So this is a rotating magnetic field at how much speed? Synchronous speed. Therefore, this is the position of stator field. That is the position of stator field. Okay. Now, what happens? Now, rotor, this stator field will cross air gap and link the rotor winding. So, once it links the rotor winding, somebody said, explain me slowly, and somebody said, discuss all four machines. Both will not happen at the same time. Okay. This is a revision session. I told you it will be useful only if you have idea about electrical machines already. Okay. It's a 40-hour subject. I need to discuss in 1.5 hours to 2 hours, that too with problems. So you can understand the scale at which I am going to discuss. Okay. If you wanted me to go slowly, detailed manner, then I can cover only one subject, one machine, not all the four machines. All right. Yeah. So this is a stator field. This stator field will cross air gap and link the rotor so that an EMF is induced in rotor. and immediately current will flow, torque is created. That torque will push the rotor near to the stator field. So the rotor will never reach synchronous speed, it will reach near to synchronous speed. Imagine this is the position of rotor. Rotor will also have distributed winding. Yes, this is the speed of the rotor. Okay. Now can I say there exists a relative speed between stator field and rotor conductors? Yes. And that relative speed is what we call it as slip speed. Okay, a term is coming important, slip speed. Okay, slip speed is nothing but relative speed between stator field and rotor conductors. Stator field is rotating at ns rpm, rotor conductors are rotating at nr rpm. What is the relative speed between these two? Is it not ns minus nr? So the slip speed is equal to ns minus nr rpm. Okay, all right. And this relative speed will be the reason to create electromagnetic torque. And electromagnetic torque, okay, see the relative speed is ns minus nr. Because of this relative speed only, an EMF is induced in rotor. Okay, and rotor is a closed circuit or open circuit? Closed circuit. Therefore, current will flow through rotor. And rotor is now normal conductor or current carrying conductors? Current carrying conductors. These current carrying rotor conductors will experience torque, right? And according to Lenz's law, this electromagnetic torque, that is indirectly the effect, will try to reduce this relative speed, which is the cause. That is the cause, right? What Lenz's law states that effect will always try to reduce the cause. Now, could you tell me, could you try to understand, okay, how electromagnetic torque can reduce this cause? Okay, that is by pushing the rotor in the direction of stator field. See, stator field was here, rotor conductors are here. You push the rotor in the direction of stator field. Okay, you push the rotor in the direction of stator field, then rotor will further accelerate, then only the relative speed can reduce. But after a certain point, you can't push the rotor further. Why? Because there is an opposition torque also, known as the load torque. A mechanical load will be connected, right? That load torque is opposing the movement. Got it? And the electromagnetic torque is supporting the rotation of rotor. So what happens at a particular moment? We call it as a steady state point. This opposition load torque and supporting electromagnetic torque both will balance each other. Once opposition torque and supporting torque balances each other, then the rotor doesn't accelerate further. The rotor speed remains constant, and this is near to synchronous speed, not exactly equal to synchronous speed. And this relative speed is what we call it as slip speed. Understand? That is what I wrote you here. And the moment you know slip speed, you can find out now what is per unit slip. What is the formula for per unit slip? Yes, it is the ratio between actual slip speed with respect to base speed. We all know per unit quantity definition. It is the ratio between actual value to base value. Okay, it is the ratio between actual value to base value. Hope the session was smooth. Right. Yeah. Yes. Actual speed with respect to base speed. What is the actual slip speed? It is ns minus nr. And remember, both for induction machine and synchronous machine, base speed is always synchronous speed. This is the formula for per unit slip. Simple formula, most of you know about this. In case if the speed is expressed in radian per second, the same slip can also be written as omega s minus omega r by omega s. This is another formula you can use for slip. Okay, this is when the speed is in rpm, this is when the speed is in radian per second. Okay, and also once you know this speed equation, slip equation, you just cross multiply and separate nr. Then you can write nr is equal to 1 minus s into ns rp. Okay, that means if you know synchronous speed and slip, you can easily find out rotor speed. Okay, next very important equation, nr is equal to 1 minus s into ns. That means whenever I ask you find the speed of the induction motor, then immediate question is to find the speed, we first need what is the slip value. Okay, yes. Next, once you know per unit slip, how can you calculate a percentage slip? Yes, we all know percentage value is always equal to per unit value multiplied with 100. So this is ns minus nr by ns into 100. This is percentage slip. Got it? Yes. This is a basic formula and a first kind of formula in induction motor subject. Okay, fine. Now, what I am trying to do is, let us try to solve one question related to the slip value. I have a previous gate questions with me. Okay. Okay, see here. All right, this is a 1 mark question. I hope it is visible, right, for you. All of you, please go through this 6th question. This is question number 6. This appeared in GATE 2022 paper, instrumentation paper. You can just go through this question. Right. So I can't write down here. Okay, anyway, at least question is visible to you, right? Read this question. A 440 volt 8 kilowatt 4 pole 50 hertz star connected induction motor has a full load slip of 0.04. What is the rotor speed in RPM? A very simple question, 1 mark question. We are asked to find out rotor speed, that is nr. Just now we found the formula, nr is equal to 1 minus s into ns. In that, slip was already given 0.04. What is the formula for ns? 120f by p. So here frequency was 50 hertz, number of poles are 4. So you can easily answer this question. Let me know the answer in the options quickly. Within 30 seconds you can answer this question and you can score 1 mark. Very easy question. So if I go, nr is equal to 1 minus s into ns. So in the given question, slip is 0.02. What is the formula for ns? 120f by p. Frequency was 50, number of poles are 4. You can use calculator, no problem. 0.98 into 1500. I think 2% or less than 1500. So it was 1470 RPM probably. Yes or not? Isn't it? 1470 RPM or 1440? 1440, all right. I don't have calculator with me. Okay, let me use calculator. Yeah, 1470 correct, right? Slip is 0.02. Slip was 0.02. Please understand. The slip, slip is 0.04. Correct. Not 0.02. Slip is 0.04. I substituted wrong value. Slip was 0.04. Okay. Then it will become 0.96. Then 1440 is correct. All right. Yes. Simple question. Yes, 1440 is correct. Now, let's move to the next observation. Once you understand what is the value of a slip, then we will try to understand what is EMF equation of induction motor. Then we will see frequency of induction motor, EMF equation. See, when I say EMF equation of induction motor, there are two things I need to discuss, because I told you induction motor will operate based on mutual induction principle, which is very similar to transformer. But there are two conditions here. One is starting condition, another one is running condition. Okay. So first of all, if I am talking about starting condition, what is mean by starting? That means the motor is at zero speed, right? We know at the time of starting any motor, the speed will be equal to zero. Okay, NR is equal to zero. If NR is equal to zero, can I say slip will be equal to 1? Yes, this is the starting condition. You know the formula for slip? Ns minus Nr by Ns. So if Nr is equal to 0, slip will be equal to 1. Now let us understand what is the stator induced EMF equation. Stator induced EMF per phase. Stator means, is it like primary side of the transformer? Yes. One more point, EMF equation is always defined per phase only. It is not per line. And the formula will be 4.44, directly let me write flux. 4.44 into flux into stator frequency, stator turns into stator winding factor. If it is a transformer equation, you don't find this winding factor term because transformer will have a concentrated winding, so winding factor is equal to 1. But induction motor will have distributed winding and winding factor will be always there. So this F1 is stator frequency, T1 is number of turns in stator, KW1 is stator winding factor. Okay. Next, rotor induced EMF. Rotor is like secondary side of the transformer right now. That is E2. Rotor is like secondary side. So the formula will be 4.44 flux into rotor frequency, rotor number of turns into rotor winding factor. Okay, rotor winding factor. Clear? So now, like I told you, at the time of starting, when I say starting, rotor was rotating or rotor is stationary? Yes, rotor is stationary, right? Stator is always stationary because it is a stationary part. Now rotor is also stationary. If both were stationary, is it not very much equivalent to transformer? There are no rotating parts in the machine, isn't it? Right now the machine is a stationary, static machine. Therefore, it is exactly similar to transformer. And if it is exactly similar to transformer, stator frequency and rotor frequency will be same, right? In a transformer, stator frequency and rotor frequency, primary frequency and secondary frequency both are equal. Transformer is a constant frequency device. Therefore, here also F1 and F2 both are equal. And this is nothing but a supply frequency. Why stator frequency and rotor frequency both are equal? Then the answer is the machine is at starting. At starting, induction motor is exactly equal to transformer. Therefore, stator frequency and rotor frequency both are equal. Okay, if both are equal, let's take the ratio from E1 and E2. So therefore, E1 by E2 is equal to T1 divided by T2. This is what we call it as turns ratio of induction motor. Turns ratio of induction motor. Clear? Now, this is at the time of starting. Now, let us understand running condition. Running condition means NR is not equal to 0. Rotor is rotating. But I told you, rotor can rotate only at a speed less than synchronous value. NR is always less than NS. Clear? Okay. Now see that. One point is very important. Whether starting or running condition, stator voltage doesn't change, right? Why? Why? Because stator winding is connected to supply source. And we all know supply voltage is always constant because it is power grid voltage. Stator will be excited from bus bar, right? Bus bar means its voltage and frequency are constant. So that's why stator voltage remains the same. E1 will be same as the previous case. Okay, but rotor voltage is subjected to change. Now the rotor voltage will be equal to S times of stator voltage. I am not going to the proof of this equation, guys. In regular class we will prove everything. Also we will discuss more in a detailed manner. We don't have that much luxury right now. I am directly right now. So under running condition, rotor voltage is equal to slip times of stator voltage. This is what we call it as slip voltage. We call it as slip voltage. Okay, or else I can write down in a more detailed way, another way like this. Let's say rotor voltage is equal to S times of E2. This is a better way of writing. This is what we call it as slip voltage. Slip voltage. Now what is E2 and what is S into E2? Remember, E2 is nothing but rotor induced EMF at the time of starting. But S into E2 is nothing but rotor induced EMF under running condition. So starting condition rotor voltage, running condition rotor voltage are not equal. At a starting condition, it is similar to transformer. But under running condition, rotor voltage will be equal to S times of starting voltage, S into E2. All right. So what is E2? Rotor voltage at the time of starting, S into E2 is rotor voltage under running condition. Important. That is known as slip voltage. Now, for example, what if I take the ratio between stator voltage to rotor voltage now? Earlier, stator voltage E1, rotor voltage E2. But now, stator voltage is the same E1, but rotor voltage is S into E2. This will not be equal to turns ratio. So under running condition, voltage ratio of induction motor is not equal to turns ratio. If I ask you why voltage ratio is not equal to turns ratio, the answer is voltage ratio modified or turns ratio modified. Yes, the answer is turns ratio is same, but voltage ratio modified. Why? Because earlier voltage ratio was E1 by E2, but now voltage ratio was E1 by S into E2. Because this term S, the voltage ratio changes, that is not equal to turns ratio. Now what is the issue here? What is the problem? If voltage ratio is not equal to turns ratio, the machine is no longer a generalized transformer. You can't treat this machine as a transformer anymore. If it is not like a transformer, you can't draw the circuit diagram like transformer. Without drawing a circuit diagram, we can't solve a mathematical analysis of this particular machine. Okay, so what to do, we will see later. Next. Similarly, let us understand frequency of induced EMF also. Next case. Frequency of induced EMF. Once again, two cases we will be discussing. First one is starting condition. Starting means what? NR is equal to 0. Slip will be equal to 1. And I told you at the time of starting, induction motor is very much equivalent to transformer. If it is equivalent to transformer, stator frequency F1, rotor frequency F2, both are absolutely same, and that is equal to what? Supply frequency. Why both frequencies are equal? Because machine is equivalent to transformer. In a transformer, primary frequency and a secondary frequency both are equal. That is nothing but supply frequency. But what about running condition? This is important. During a running condition, NR is not equal to 0, but NR is always less than synchronous speed. Now, question is whether it is a starting condition or running condition, which frequency doesn't change? Supply frequency doesn't change, right? Because the machine was excited from busbar. Busbar means the supply frequency remains constant. When I say supply frequency is constant, indirectly which frequency was constant? Stator frequency was constant. Now, stator frequency is same as supply frequency. But rotor frequency will change. The rotor frequency will be equal to slip times of supply frequency. Yes, this is what we call it as slip frequency of induction motor. Slip frequency. So very clear observation. At the time of starting, stator frequency and rotor frequency both are equal. Induction motor is similar to transformer. But under running condition, rotor frequency will change. The rotor frequency is now equal to slip times of supply frequency. For example, supply frequency was 50 Hz. Slip equal to, let us say, 10%. What is the rotor frequency? 10% of 50 Hz. Is it not 5 Hz only? So rotor frequency will change. Very, very important. We call it as slip frequency. Not only rotor frequency, the rotor voltage also changes. Rotor voltage is also equal to a slip voltage. Just for a few seconds, look at this equation. We will solve some questions related to this equation. Okay. Remember guys, my aim was to discuss all the 4 machines in a single day. So I'll be little quick, obviously. If you find the lecture was too quick, I better ask you, watch this lecture at 0.75x speed or 0.5x speed. Okay. If you find this lecture was very slow, then you watch it after the recording. Once the lecture is completed, recording session will be available. Then you can watch it 1.5x or 1.25x speed. Okay. Yeah. The lecture is particularly for those who wanted to have a quick revision. Yeah. Right. Okay. Now let us try to solve one question related to this concept from the previous GATE examination. Okay. Okay. Yeah. Let's solve this question number 3. Question number 3. This was in GATE 2014 set 1 of the question paper. Question number 3. Look at this question. An 8-pole 3-phase 50 Hz induction motor is operating at a speed of 700 rpm. The frequency of a rotor current of the motor. Just now I discussed frequency of rotor means, is it not a slip frequency? Yes or not? It will be equal to slip frequency. So first of all, find the synchronous speed of this machine, 8-pole 50 Hz. Okay, rotor is rotating at 700 rpm. So given first synchronous speed 120 f by p. So 120 into 50 Hz by 8 poles. I think it was equal to 750 rpm. Correct? You use calculator, no problem. Okay, 120 into 50 by 8, 750 rpm. And the rotor was rotating at 700 rpm. Now quickly find out what is the slip value. Slip is equal to ns minus nr by ns. What is ns here? 750. nr is 700 by 750. You will get slip value. Is it not 50 by 700? 50 by 700. I am using calculator. I request you to use only GATE calculator. Okay. Yes. It will be 0.0714. Remember, slip value is always very, very small. That's why use at least 3 to 4 digits after the fraction so that you will get accurate answers. Then, what is the rotor frequency they are asking? We just studied rotor frequency is equal to slip times of supply frequency. So 0.0714 into 50 Hz. Okay. So into 50. So that is 3.57 Hz. If I make any mathematical errors in the calculator, please try to correct them. No issues. So I am getting 3.57 Hz. I hope most of you got the same. 3.33 Hz. Okay. Okay, I think I made a error in slip calculation. It was 0.0666. Okay. So 0.0666 into 50. Okay, 3.33 is correct. 3.33 Hz. Okay, that is the value of slip frequency. Very simple question. Okay. Okay. Yeah, one more question. You go through this GATE 22 question, electrical engineering paper. You go through this question number 5, visible, right? Question number 5, this one. The frequencies of the stator and rotor currents are flowing in a 3-phase induction motor, 8 pole. Yes, stator frequency 40 Hz, rotor frequency 1 Hz. What is the motor speed they are asking? Motor speed means NR. They are asking about NR. Okay, stator frequency 40, rotor frequency 1. What is NR value? Can I say NR is equal to 1 minus S into NS? That direct formula I can use. So if you go through it, stator frequency 40 Hz, rotor frequency is equal to 1 Hz. But we know there is a relation, right? Rotor frequency is equal to S times of stator frequency. So slip is equal to F2 by F1, which is 1 by 40. That is the slip value. Now find out NS also. NS is 120 F by P. Remember, when you are calculating the synchronous speed, you have to use a supply frequency here. In place of F, we have to use a supply frequency. What is a supply frequency? 40 Hz, indirectly stator frequency, by 8 poles. The machine will have 8 poles. That was clearly given, 8 pole. Right. So what is 120 into 40 by 8? 120 into 40 by 8. 600 RPM. Okay. If NS is equal to 600 RPM, what is NR? NR is equal to 1 minus S into NS. So 1 minus 1 by 40 into NS 600. This is 39 by 40 into 600. I am getting 585 RPM. That is the answer, correct? 585. Correct answer. Good. That is the answer for rotor speed. Simple question. See, this is GATE 2022 paper question. So likewise, there are almost 5-6 questions in the previous GATE exam. Easily you can answer them. Okay, right. Now, once we understand what is a slip, what is slip frequency, what is slip voltage, we will quickly go through the next analysis, that is stator and rotor field speed. Stator and rotor fields. Okay, if you go back, I discussed already what are the conditions to be satisfied to create electromagnetic torque, right? One of the important condition is to create electromagnetic torque, the relative speed between stator field and rotor field must be always equal to 0. That means stator field and rotor field should travel with the same speed. How that is possible in induction motor, we will try to quickly discuss it. Okay, remember, in induction motor, stator is always stationary. Let us draw stator with a stationary line. These are the stator conductors. We will excite this stator with AC supply so that stator will create a rotating magnetic field at a synchronous speed. This is the position of stator field. Okay, and the rotor will rotate at a speed near to synchronous speed. This is the position of a rotor, NR, rotor. These are the rotor conductors. Now, important observation is, what is the frequency of stator? Stator frequency is equal to F with the number of poles P. But a rotor frequency is equal to S into F. We call it as slip frequency. Number of poles will be same. Stator and rotor will be designed with the same number of poles. Now, what happened? If you look at the stator field speed, okay, from stator, it is equal to NS. What is the formula for NS here? That is stator field speed. Stator field speed, let us say NS1. It is equal to 120 into stator frequency by poles. This is nothing but NS RPM. Similarly, what is rotor field speed? Rotor field speed, let us call it as NS2. As it was a rotor field speed, use rotor frequency here, F2. But what is rotor frequency? Is it not slip times of supply frequency? In place of F2, I can substitute slip frequency. You take slip outside, then it will become S into NS. And what is the formula for S? S is equal to NS minus NR by NS into NS. NS will cancel. Therefore, rotor field speed is equal to NS minus NR RPM. Very clear information. the speed of the rotor field is ns minus nr. That means what I need to do, from the rotor, draw a line with a distance equal to ns minus nr. This is the position of rotor field. Okay. Now the points are very simple. What is the speed of stator field from stator? It is ns rpm. What is the speed of rotor field from rotor? Ns minus nr rpm. But what if I ask you the speed of rotor field from stator? If you see the speed of rotor field from stator, this distance is already nr. This is ns minus nr. What is the whole distance is equal to? Is it not ns rpm again? Therefore, end of the day, what is your observation? Stator field and rotor field lying on the same line, right? If stator field and rotor field lies on the same line, what is the relative speed between the two fields? 0. So it is proved that the relative speed between stator field and rotor field is equal to 0. If that condition is satisfied, then only electromagnetic torque will be created. So if I quickly ask you, this diagram is very important. We are giving a supply to, stator. Stator field will rotate with a synchronous speed with respect to stator. Rotor field will rotate with a slip speed with respect to rotor. But when you see the rotor field speed with respect to stator, that is also equal to ns rpm. Got it? And based on this single concept, there is a question in the previous GATE examination. Okay, based on the field concepts. Okay, so let us see that question. Look at this, all of you. Question number 4. This is in GATE 2017, set 2. Read the question. A 3-phase 4-pole 400 volt 50 Hz squirrel cage induction motor is operating with a slip of 0.02. Now read the problem. The speed of the rotor flux, indirectly rotor field, in mechanical radian per second by a stationary observer. When I say stationary observer, it is indirectly stator. They are asking speed of the rotor flux, indirectly speed of the rotor field with respect to stator. We just discussed. What is the speed of the rotor field with respect to stator? Come on, let me know in the options, in the chat box. What is the speed of the rotor field with respect to stator? What is the speed of the rotor field with respect to stator? Come on. Look at the diagram and answer the question. Is it not ns rpm? Yes. Speed of the rotor field with respect to stator, it is equal to ns rpm. Right? It is equal to ns rpm. And what is ns in the question? In the given question, ns is equal to 120 f by p. So 120 into, yes, what is the frequency given? 50 Hz. Number of poles are 4. So it is 50 Hz. Number of poles are 4. It is equal to 1500 rpm. But the answer we need is in rpm or radian per second. The answer we need is in radian per second. That is, omega value is required. So what is the relation? Therefore, omega s, is it not 2 pi ns by 60? Yes. Omega is equal to 2 pi m by 60. So 2 pi into 1500 by 60, you will get the radian per second. Okay. So what will be the radian per second value? So 2 pi, where is pi here? Yes, I think 157 near to, right? Yes, 157 radian per second. 157 radian per second. Yes, this is the mechanical speed, guys. This is the mechanical speed. Revolution per minute, that is the mechanical speed in rpm. 157 is the radian per second. Okay, fine. It's a simple question. Now there is one more concept related to these fields. Right now in this particular diagram, we are giving a supply to which winding? Rotor winding, sorry, stator winding. Mutual EMF is induced in rotor. But what if you give supply to rotor winding? Especially in a slip ring induction motor, that is possible. In a slip ring induction motor, rotor terminals are accessible outside, right? To those rotor terminals also you can give supply. Okay, so what happens if induction motor is excited from rotor side? Excitation from rotor side. For example, if the induction motor is excited from rotor side, that is like excitation of transformer from the secondary side. Okay, so then what happens? See, this will be the stator part. Stator is always stationary. Stator winding is stationary. But this time, stator winding is not excited. Stator winding is short circuited on the end terminals. But who is excited? Rotor winding is excited. And this is a long discussion actually. In a classroom, we use it to discuss this concept for half an hour. But here, in 1 minute, I'll try to explain. So when you give excitation to rotor, the rotor will move in opposite direction to stator field. See here, we are giving excitation to stator. Stator field will move in forward direction. Then rotor will also move in forward direction. But when you give excitation to rotor, the rotor will not move in forward direction. Instead, the rotor will move in backward direction. Why it is rotating in backward direction, I am not discussing that right now. In regular class, we will study that. But rotor will now rotate in backward direction. At how much speed? Nr. But remember, I told you, rotor is a short circuit, or we are exciting the rotor? We are exciting the rotor, don't forget. With how much frequency? Supply frequency. Rotor is excited with supply frequency, having a number of poles P. With what sequence I am exciting? ABC. Therefore, rotor field will rotate in forward direction. With how much speed? NSRP. This is the position of rotor field. Rotor field. At what speed? NSRP. Okay. If I ask you the question now, what is the speed of rotor field with respect to rotor? That is NSRP. But at what speed rotor is rotating? Nr in the backward direction. Okay. What is the rotor frequency? F. If rotor frequency is equal to supply frequency, stator frequency will be equal to slip frequency. Remember, this time the machine is excited from stator side or rotor side? Rotor side. So rotor frequency is equal to supply frequency. Stator frequency will be equal to slip frequency. If you excite the machine from stator side, stator frequency will be supply frequency, rotor frequency will be slip frequency. Okay. Now, this is a rotor. Rotor will also have a field, right? Now, rotor field will rotate with the slip speed, ns minus nr. This is the position of stator field. Okay. So, earlier, rotor field speed is equal to slip speed. Stator field speed is equal to synchronous speed. But now, rotor field speed is a synchronous speed. Stator field speed is equal to slip speed, ns minus nr. This is the diagram when machine is excited from which side? Rotor side. Very rarely questions will come from excitation from the rotor side, but you better study this. Okay. You just remember this diagram, you can answer the questions. Okay. Yes. Clear? Alright, this is about slip calculations in induction motor. So we will now go to the next concept, that is equivalent circuit. Okay. There are many other questions also. It's not possible to solve each and every question. Okay. So let's move to the next concept, which is equivalent circuit of induction motor. Okay. Equivalent circuit. See, when it comes to equivalent circuit, again two types of equivalent circuits we are going to discuss. One will be equivalent circuit at the time of starting. Another one is equivalent circuit under running condition. Okay. So at the time of starting, the equivalent circuit will be very similar to transformer. But under running condition, the equivalent circuit will change. Okay. Yes. So first we will discuss about starting condition. Starting condition means NR is equal to 0, slip will be equal to 1, and rotor frequency is same as stator frequency, correct? And this equivalent circuit will be similar to transformer. I hope you remember transformer circuit diagram, and exactly similar to that we will be having equivalent circuit of induction motor also. See, this is the stator resistance per phase, stator leakage reactance per phase, and then there will be a no load branch. The no load branch will have core loss resistance and magnetizing reactance. Okay, no load branch is a shunt branch. And then we have ideal stator winding. Coming to the rotor, this is the ideal rotor winding. Rotor winding will have some resistance R2. Rotor winding will have leakage reactance X2. And I told you very clearly, rotor is a closed circuit. Okay. So here we will give supply voltage V1. This is induced EMF in the primary, let us say E1. Induced EMF in the secondary, that is E2. And what is E1 by E2 is equal to turns ratio T1 by T2. Right? This is the stator current I1. I1 will have two components in it. One is the no load current I0, another one is the load component current I1 dash. And then the rotor current will be I2. I2 is the rotor current. Okay. So this is equivalent circuit of induction motor at the time of starting. Therefore, all the parameters expressed in the rotor side, they are per phase values at the time of starting. What is E2? Rotor voltage per phase at starting. R2, rotor resistance per phase at starting. Starting or standstill condition, both are same. X2, rotor leakage reactance at starting. Okay. Clear? So all the parameters are expressed on the rotor side. They are per phase values and also at the time of starting. Now, under running condition, what will happen? The circuit diagram will change. I told you already, under running condition, rotor voltage will change from E2 to S into E2. Under rotor frequency will also change, right? Under running condition, frequency will be slip frequency. So, if I wanted to modify the same equivalent circuit under running condition, I'm doing it here only. So, what happens? Under running condition, NR is not equal to 0, but NR is always less than NS. Rotor frequency is equal to slip frequency. Now, what are the modifications you will get? No modifications on the stator side because stator voltage is fixed, stator frequency is fixed. But on the rotor side, instead of E2, we will get S into E2. That is known as slip voltage. What about frequency also? Frequency will also change, right? Instead of F, you will get S into F. And we all know whenever frequency changes, the reactance term is going to change because the reactance will depend upon frequency. So now the reactance is not X, it will become S times of X. Because reactance is proportional to frequency, right? So therefore, this X2, which is at the time of starting, changes to S into X2. Very simple. So what is X2? What is S into X2? X2 is rotor leakage reactance at the time of starting. S into X2, rotor leakage reactance under running condition. What is E2? Rotor voltage at the time of starting. S into E2, rotor voltage under running condition. Clear? Now what is the voltage ratio? Is it E1 by E2 or E1 by S into E2? Yes, the voltage ratio is E1 by S into E2. Will it be equal to turns ratio or not equal to turns ratio? If I ask you the question, why voltage ratio is not equal to turns ratio, the answer is because turns ratio modified or voltage ratio modified? Voltage ratio modified. Turns will never change. Once the construction is completed, number of turns will be fixed, right? So, but the voltage ratio changes, so voltage ratio and turns ratio were not equal. What is the problem? This machine is no longer similar to transformer. If it is no longer similar to transformer, you can't transfer primary parameters to secondary or secondary parameters to primary. Generally, in a transformer subject, we will study, right? Transferring parameters from one side to another side to make it like a single circuit. So, I can't transfer primary parameters to secondary or secondary parameters to primary. If I wanted to do that, I have to make sure this circuit is similar to transformer. It will be similar to transformer only when voltage ratio is equal to turns ratio. For that, we will modify the rotor equivalent circuit. See, what is the modification we are going to do? So, modified rotor equivalent circuit. You please first understand what is the original rotor circuit. In the original rotor circuit, voltage is S into E2, resistance R2, reactance S into X2. Now, rotor voltage is S into E2, rotor resistance is R2, rotor leakage reactance is S into X2, and rotor current is I2. Now, what is the magnitude of this I2? This I2 is equal to voltage S into E2 by impedance. What is the impedance? Square root of R2 square plus S into X2 whole square, right? Magnitude only I am talking about. Square root of real part square plus imaginary part square. Now what I can modify? I can rewrite this equation. You simply take S square out of the root in the denominator. S will come outside, S and S will cancel. Then this will become E2 by root over R2 by S whole square plus X2 square. Please understand the first equation and the second equation both are same, right? I just took S common and cancelled it. So the voltage is E2. Now resistance part is R2 by S whole square. Reactance part is X2 square. Therefore, the same equivalent circuit was modified such that voltage is now E2. Resistance is R2 by S. Leakage reactance is X2. Now tell me, in both circuits, the current value is the same or different? Same. But if you look at the second circuit diagram, what is the voltage? E2. If the voltage is E2, then can I say voltage ratio and turns ratio will be same like starting condition? You remember at the time of starting, what is the voltage ratio? E1 by E2, that is equal to turns ratio. Even if you look at this second circuit diagram, the voltage ratio will become E1 by E2, which is equal to turns ratio. Therefore, I can use this circuit number 2 to make induction motor similar to transformer, so that I can transfer parameters from one side to another side. Remember, this is the original circuit, but I won't use it because I can't transfer the parameters from stator to rotor or rotor to stator. I have to use this modified circuit so that I can transfer parameters from stator to rotor or rotor to stator. Also, one more modification you see, you have a resistance R2 by S, right? That resistance R2 by S can be written as sum of R2 and R2 into 1 by S minus 1. You see, both are same. LHS and RHS both are equal. That means a single resistance R2 by S is divided into series combination of two resistances. One is R2, another one is R2 into 1 by S minus 1. Therefore, the circuit diagram can change further. You see, now the rotor voltage is E2, one resistance is R2, another resistance is R2 into 1 by S minus 1. Just a moment. 1 by S minus 1. Now all these three equivalent circuits will have same magnitude of the current. Same magnitude of the current. But I can only use a second circuit and a third circuit to transfer parameters from one side to another side. Okay. All right. So for example, if I use a second circuit diagram and transfer rotor side parameters to stator side, you know how to transfer parameters, right? Just like a transformer. Then you will get complete equivalent circuit referred to stator. Okay. See. Complete circuit referred to stator. Okay, so stator parameters doesn't change, R1 and X1. Then we have a shunt branch, core loss resistance and magnetizing reactance. Now, and with this stator circuit is completed, then the rotor circuit will start. Now what is the resistance of the rotor? R2 by S. Don't use this circuit. If I use this circuit, I can't transfer the parameters. I have to use the modified circuit. What is the rotor resistance? R2 by S. When R2 by S transferred to primary, its value will become R2 dash by S. Reactance will become X2 dash. Now this is the complete equivalent circuit of transformer referred to which side? State. I0, I1 dash, and this current is I2 dash. I2 is a rotor current referred to rotor. I2 dash is rotor current referred to stator. This is the complete circuit diagram of induction motor. But you can take one approximation here. What is approximation? You look at this shunt branch. This shunt branch will have two current components here. One is loss component current IW, another one magnetizing current IB. But we know this magnetizing current is much higher compared to this loss component current. What is a magnetizing current induction motor? 20 to 30% of rated current. In a transformer, it is just 4 to 5% only, but in induction motor, it was 20 to 30% because of air gap. Air will offer low permeability, that's why magnetizing current demand increases. Therefore, this loss component current value we can neglect compared to magnetizing current. So see, the moment I neglected this RC, what is the only element available in shunt? Magnetizing reactance only. Therefore, I can modify this circuit that the shunt branch will have only magnetizing reactance. XM. In some of the problems, they use it to say neglect this magnetizing current also. If magnetizing current is neglected, the entire shunt branch will be neglected. Then you will have only series branch. Again, in this series branch, what if I say stator impedance is neglected? If stator impedance is neglected, then R1 and X1 will also be neglected. Only rotor branch will be available. Okay. Clear? Fine. This is about equivalent circuit of induction motor. All right. Okay. Now, once we understand the equivalent circuit, now we will try to answer a question related to equivalent circuit of induction motor. Okay, so yeah. Okay, look at this question. This is a 1 mark question, simple question. This was given in GATE 2010 paper. Please read this question. GATE 2010 paper. All of you please read this question. Let me zoom in. Okay. A balanced three-phase voltage is applied to a star-connected induction motor. The phase to neutral voltage, indirectly phase voltage, was V. The stator resistance, rotor resistance referred to stator leakage reactance, rotor leakage reactance. See, all the parameters are referred to stator. Magnetizing reactance is also given. Okay, so stator resistance RS, rotor resistance RR, stator reactance XS, rotor reactance XR, magnetizing reactance XM. What is the magnitude of starting current of the induction motor? They are asking about starting current. Okay, the options are available here. You see, here are the options. These are the 4 options available. We are asked to answer what is going to be the starting current of the motor. We just now we discussed about equivalent circuit of induction motor, right? They are just asking us starting current of the motor. Can I say at the time of starting, what is NR is equal to 0? If NR is equal to 0, then slip will be equal to 1. Yes or not? Therefore, in this equivalent circuit, you just replace S equal to 1. If I replace S equal to 1, automatically I will get the starting equivalent circuit. Then what is the starting current they are asking? Okay, look at the options. 4 options are available. V by Rs plus Rr whole square, Xs Xr whole square, like that 4 options are available. Okay, so what is the correct answer is the question. Okay, yes. See that at the time of starting, replace S equal to 1. Just modify here. S equal to 1. And we know at the time of starting, machine will draw very high current or very low current, very high current. That is why we are using starters to control that current. As the starting current is very high, this magnetizing current can be neglected compared to starting current. Okay, because flip equal to 1, the starting current, the current passing through series branch is very high compared to this shunt branch. Therefore, this shunt branch can be neglected. This current can be neglected. If that current is neglected, what is the approximate circuit diagram? R1 and X1. Then coming to rotor, this is R2 dash and X2 dash. This is the simplified circuit because the magnetizing current is neglected compared to the starting current. And in the given question, this R1 is nothing but RS, this is RR, this is XS, and this is XR. Therefore, the starting current, I starting, will be simply equal to voltage by the impedance, starting impedance. Is it impedance square root of real part square plus imaginary part square? So it is V by root over stator resistance plus rotor resistance whole square plus stator reactance plus rotor reactance whole square. That is a simple equation which will be useful to find out the starting current. Important thing is why the shunt branch current is neglected. This is a suitable option. Why shunt branch current is neglected? Because at the time of starting, the series branch current is way high compared to shunt branch current. That's why we neglected. That is the only option which will be suitable. Okay. Clear? Yes, this is the correct answer. Okay. Next, we will try to answer one more simple question. 2 marks question also we will answer. You go through this question number 1. It is in GATE 2019 paper. There are many questions. We can't answer all the questions. At least a few questions we will try to answer. Okay. Question number 1. 2019 paper. Just read this problem. Yes. A delta connected 3.7 kilowatt 400 volt line 3 phase 4 pole 50 Hz squirrel cage induction motor has the following equivalent circuit parameters per phase referred to the stator. All parameters are referred to stator. R1 given, R2 given, X1 given, X2 given. Neglect shunt branch, that is clearly mentioned. The starting line current in amperes when it is connected to a 100 volt line 10 Hz 3 phase AC circuit. See, one simple observation is all the resistance and reactance parameters are given for 50 Hz frequency. But the answer is required to find out with respect to 10 Hz frequency. So tell me which parameters will change when you change the frequency from 50 Hz to 10 Hz. Obviously, reactance will change. Am I right? Because reactance is directly proportional to what? Frequency. Okay. So hope you are understanding the problem. So here the reactance was X1 and X2 both are equal to 8.22. This 8.22 is at 50 Hz, but I need at 10 Hz. Okay. So what is the relation? We know reactance is equal to 2 pi f into L. So reactance is directly proportional to frequency. So X1 by X2 is equal to F1 by F2, where X1 is first case reactance, X2 is second case reactance. In first case, the reactance was 8.22. What is the new reactance? First case frequency 50, second case frequency 10. So can I say it was simply 10 by 50 times of that 8.22. Okay, how much? It is 1 by 5 times. 8.22 by 5. 1.64 ohm per phase. This is the new reactance what I need to do use in the equivalent circuit. Now draw the equivalent circuit. R1, X1, next R2 dash, X2 dash. Remember, in the actual circuit diagram, this was R2 dash by S. But they are asking us to find out starting current. We know at the time of starting, slip is equal to 1 simply. What is the voltage? The given circuit is a delta connection or star connection. Please go through the circuit diagram. It was delta connected. In a delta connection, in a delta connection, line voltage and phase voltage will be same, right? If line voltage was if line voltage was 100, because we are asked to find out starting current at 100 volt, then phase voltage will also be equal to 100. Phase voltage is also 100. So what is the starting current is the question. Can I say current is simply voltage by impedance? So the starting current is equal to voltage is 100 by impedance square root of what is the real part? R1 plus R2. In the question it was given. What is R1, R2? 5.39, 5.72. 5.39 plus 5.72 whole square plus x1 plus x2. Can I say x1 and x2 are having the same value? 1.644. 1.644 plus 1.644 whole square. This will directly tell you the starting current per phase. Then you convert to line value. So what is answer? So 5.39 plus 5.72 whole square plus under root, okay, by 100. Inverse of that. Okay, let me do it. So how much you are getting? 5.39 plus 5.72 whole square plus 1.644 whole square under root. Yes, I am getting 8.63 ampere per phase. If a per phase value was 8.63, then what is the answer? The answer is a line current. Remember guys, please be very, very careful. In machines and power system subject, this is where students must be extremely careful. Are they asking line values or phase values? Okay, please go through it again. The starting line current we need. The question is delta connected. In a delta connection, line current will be equal to root 3 times of phase current into root 3. So the correct answer will be 14.94 amperes. So the line current will be, I'll go to the next page. The line current will be root 3 times of phase current. It will be 14.94 ampere per line. That is the starting line current. See how simple the questions were. Okay, it's a 2 marks question, nothing is there. But you need to be attentive. The given parameters were measured at 50 Hz frequency, but the answer we need at 10 Hz frequency and 100 volt line value. Okay, right. Okay, that's all. This is an example question related to equivalent circuit, right? 14.94, correct answer. Okay. So we will move to the next topic, power flow diagram. So power flow diagram is a concept where we will study how active power flows from input to output of an induction motor and how power losses also takes place. So I hope most of you have idea about the different types of power losses in rotating electrical machine. We will be having copper loss, iron loss, and mechanical loss also, known as rotational loss. Okay. So coming to induction motor. In induction motor, 2 magnetic circuits are available, right? So one is stator part, another one is a rotor part. The medium between the two is air gap, obviously. Now, we will give electrical power as input or mechanical power as input. Electrical power as input, then mechanical power will be output, right? So here is the input power, which is electrical. And after losses in stator, remaining power will be transferred to rotor through air gap. So we call it as air gap power. What are the losses in stator? Stator will have a copper loss. Stator will also have iron loss. After these two power losses, remaining power will be transferred to rotor. We call it as air gap power because it is passing through air medium. Got it? Why there are no rotational losses in stator? Because it is a stationary part. Remember, rotational losses will be available only when there are rotating bodies. That will be available in rotor, not in stator. Now, air gap power will be received by rotor. Next, rotor will also have a copper loss. Copper loss in rotor. Remember, iron losses are neglected in rotor. Why iron losses are neglected? Because rotor frequency is very, very small. Yes, rotor frequency is equal to supply frequency or slip frequency. Slip frequency is very small, so iron losses are neglected because iron losses depends upon frequency. If iron losses are neglected, only copper losses will be considered in rotor. Now, the remaining power, whatever is the remaining power, that will be converted into mechanical power here. Whatever remaining power is there, we call it as mechanical power developed inside the rotor. Inside the motor, electrical power is converted to mechanical power. But whatever mechanical power is available inside the motor, that entire mechanical power cannot be received by the load. Obviously, mechanical losses will be there. We also call it as rotational losses. Because of friction and windage losses, mechanical losses will be produced. After mechanical losses, whatever power is available, that will be finally delivered to the load. Okay, this is finally delivered to the load. Which load? Mechanical load, obviously. And that power is known as output power or net power received by the load or shaft power. Okay, any word you can use. Okay, this is how the active power flows in induction motor. You will give electrical power as input, but you don't get entire power to the rotor. Obviously, losses are there in stator. Then air gap power will come. This air gap power converted to mechanical power. Entire mechanical power does not received by the load. Obviously, mechanical losses are there. Therefore, if you have this diagram with you, you can find out relation among all the power equations available here. For example, what if I ask you to find out air gap power if you have electrical power with you? Just a moment. Yeah. So for example, if you have electrical power with you, how do you find out air gap power? Yes, simple equations. I hope you have idea, right? So first equation, air gap power is equal to input power minus stator loss. Stator has two losses. Okay. If you remove the losses from stator, remaining power will go to the air gap. Next, if you have air gap power with you, how do you find out mechanical power developed? Can I say the difference between these two is the rotor copper loss? Therefore, mechanical power developed is equal to air gap power minus copper loss in rotor. Next, if you have mechanical developed power with you, how do you find out output power? Output power will be equal to mechanical power developed minus mechanical loss. That mechanical loss is also known as rotational loss in the machine. And if you have output power and input power with you, you can find out efficiency also. What is efficiency? Output power divided by input power multiplied with 100. Okay. Similarly, if you have output power, you should be able to calculate input power also. Any one power data will be given in the problem. You have to find out the remaining power. Clear? Now, out of these various power equations, most important term is air gap power. Air gap power is nothing but power transferred from stator to rotor through air medium. Therefore, it is the active power drawn by the rotor indirectly. Okay. So let us find out equation for air gap power. Air gap power. So air gap power is nothing but active power drawn by rotor. First of all, if I draw the rotor circuit diagram, yes, modified rotor you have to draw R2 by S and X2. This is the rotor voltage E2, rotor current I2. You remember, this is a modified equivalent circuit. You must use a modified circuit only, then only parameters can be transferred from stator to rotor, rotor to stator. Now, in this circuit diagram, what is the only element drawing the active power? Obviously, R2 by S. Therefore, whatever power is drawn by element R2 by S is nothing but air gap power. So, what is the formula now? Air gap power is equal to power drawn by resistor. Is it not I square into R? That I is nothing but I2. R is nothing but R2 by S. This formula will give you air gap power. But the point is, you have to multiply this equation with 3. Why? Because every parameter mentioned in the equivalent circuit, they are per phase values. Therefore, if you wanted to get 3-phase power, we have to multiply the equation with 3. Okay. Also, what is the magnitude of the current I2 here? I2 magnitude is equal to, is it not voltage by simply impedance, that is R2 by S whole square plus X2 square. You can replace this I2 here. Then air gap power, you will get one more equation. 3 into E2 square divided by R2 by S whole square plus X2 square into R2 by S. That is one more formula you can use for air gap power. Got it? Any formula you can use. First formula is more frequently we will use generally. Okay, that is air gap power. It is the active power drawn by rotor that is consumed by a resistance R2 by S. Next one, rotor copper loss. Rotor copper loss. As the name itself is indicating, it is a copper loss produced within the resistance of the rotor. You remember, rotor can be, actually rotor resistance is R2 by S, but that R2 by S can be written as series combination of two resistors, right? One is R2 and another one is R2 into 1 by S minus 1. This is rotor voltage E2, rotor current I2. Now, whatever power is lost in this resistance R2, this is what we call it as copper loss in rotor resistance. Okay. So, copper loss in rotor is simply the power loss in rotor resistance. I square R loss, that's all. What is the resistance in rotor? R2, current is I2, so the loss is I2 square into R2. The remaining power, whatever is drawn by this element, this is what we call it as mechanical power developed. Mechanical power developed. Mechanical power developed is nothing but power drawn by resistance R2 into 1 by S minus 1. So that is 3 into I2 square into R2 into 1 by S minus 1. Simple rules everyone has to understand. What is the power drawn by resistance R2 by S? Air gap power. Power drawn by resistance R2, copper loss. Power drawn by resistance R2 into 1 by S minus 1, that is mechanical power developed. Please understand, I am not going through the derivations of each and every formula. I am just writing down the final formulas. Understand? Final formulas, which will help you to revise quickly. Now I can find a relation among this air gap power, rotor copper loss and mechanical power developed. What is the relation? I hope most of you know this. Air gap power is to rotor copper loss is to mechanical power developed is equal to 1 is to S is to 1 minus S. Yes or not? That will be the relation among air gap power, rotor copper loss and mechanical power developed. For example, what if I take the ratio between first two terms? Let us say copper loss in rotor divided by air gap power. That is the ratio from second term to first term. second term to first term, is it not yes? Therefore, copper loss in rotor is equal to S times of air gap power. S times of air gap power. Similarly, what if I take the ratio from last term to first term? Mechanical power developed divided by air gap power. If I take the ratio from last term to first term, then last term to first term, is it not 1 minus S by 1? If you cross multiply, mechanical power developed is equal to 1 minus S into air gap power. Simple equation. So you remember this relation so that any formula we can develop. Okay. What if I take the ratio from last term to second term? Mechanical power developed by rotor copper loss 1 by S minus S, or copper loss by mechanical power S by 1 minus S, so that you can develop any relation using this equation. Okay. So this is a power flow diagram. Most important term in power flow diagram is air gap power. What is air gap power? It is a power drawn by rotor, electrical power or active power drawn by rotor. In a rotor, there is a resistance R2 by S. So active power drawn by rotor means it is the active power drawn by resistance R2 by S. This is simply the power flow diagram of a three-phase induction motor. All right. Now we will try to answer a simple question related to power flow diagram. Yeah. So this is a 1 mark question, a very simple question. Just go through it. Okay. For an induction motor operating at a slip S, the ratio of gross power output to air gap power. We need the ratio between gross power output, that is output power to air gap power. Output power to air gap power. Look at the power flow diagram. Output power means it was here. Am I right? Air gap power was here. What is the ratio between these two? Can I say between these two we have two losses? One is a copper loss in rotor, another one is a mechanical loss. But there is no information in the problem about mechanical loss. If you look at the problem carefully, there is no information about mechanical loss, because usually mechanical loss is very, very small. Unless it is given, you need not to consider it. For example, friction is neglected. That means mechanical loss will be 0. Because it was not given in the problem. Yes, you have to go according to the problem. Understand? Because the mechanical loss was not given, neglect this mechanical loss. If I neglect mechanical loss, can I say output power or mechanical power developed will be same? So therefore, indirectly they are asking us ratio between mechanical power developed to air gap power. We just found, right? Ratio between mechanical power developed to air gap power. Yes, what is the ratio? 1 minus S. Therefore, the answer for that question will be equal to 1 minus S. Simple question, 1 mark question given in GATE 2005 paper. Okay. We'll answer one more question, latest question, GATE 2021 paper. Go through this question, read the problem, everybody. Let me zoom in. Yeah. Look at this question. The power input to a 500 volt. Yeah. Power input to a 500 volt 50 hertz 6 pole 3 phase induction motor running at 975 rpm is 40 kilowatt. The total stator losses are 1 kilowatt. If total friction and windage losses are 2.025 kilowatt, then what is the efficiency they are asking? First of all, it was a 6 pole 50 hertz machine. Total input power was 40 kilowatt. Machine was rotating at 975 rpm. So let's try to find out what is the slip of the machine first. Okay, 6 pole 50 hertz, right? Then what is NS is equal to 120 F by P. So 120 into 50 by 6 pole, 1000 rpm. Okay, what is NR given? Machine was rotating at 975 rpm. That was given in the problem. So what is a slip? Slip is equal to ns minus nr by ns. Is it not 1000 minus 975 by 1000, that is equal to 0.025. Yes. Next, one more information given in the problem is total input power was 40 kilowatt. Input power was given 40 kilowatt. Stator losses are 1 kilowatt. Okay. So if I go through the power flow diagram, see, input power was 40 kilowatt. Total stator loss is 1 kilowatt. That means the air gap power will be 40 minus 1, 39 kilowatt. Yes. So therefore, first observation, air gap power will be equal to input power minus stator loss. Okay. So 40 minus 1, which is equal to 39 kilowatt. Input power is 39 kilowatt. Sorry, air gap power. The moment I know air gap power, I can easily find out the required answer. What is answer we need? What is the efficiency? Already, if rotational losses are given, you find out rotor copper loss. Okay. So once I know air gap power, what is the mechanical power developed? Mechanical power developed will be equal to 1 minus S into air gap power. So what is S value? We found 0.025. Air gap power is 39. You will get the mechanical power developed. Yes. So 1 minus 0.25 into 39. So 38.025 is the mechanical power developed. The moment I know mechanical power developed, I can find out output power, which is mechanical power developed minus mechanical loss. So 38.025 minus, what is the mechanical loss? Remember, mechanical loss or friction and windage loss both are same. So it is given clearly, the friction and windage loss is 2.025 kilowatt. 2.025. Okay. 2.025. So therefore it will be 36 kilowatt. Yes. Now you have output power with you and input power with you. Find out the efficiency. Correct? Yes. Output power was 36 kilowatt. Input power was 40 kilowatt. Therefore, you can find the efficiency, which is output power by input power. Correct? Yes. It will be 90%. Correct answer. 90%. Simple. Yes. 90% is correct. 90% is correct. Okay. Right. See how simple the questions are. Only point is that you should be able to apply simple basic concepts. Okay. Now we'll try to answer one 2 marks question also related to this. One latest question we'll answer. We'll try to answer. Yeah. Go through GATE 2008 paper question. Look at this. Simple question. Go through it, all of you. Yeah, read that problem. A 400 volt 50 Hz 30 HP 3-phase induction motor is drawing 50 ampere current at 0.8 power factor lagging. The stator and rotor copper losses are given to you. Friction and windage losses are given. Core losses are also given. What is the air gap power of the motor? Very simple question. Given for 2 marks. Just believe it. This question was given for 2 marks. And it is a very simple question. 400 volt 50 Hz 30 HP 3-phase induction motor drawing 50 ampere current at 0.8 power factor lagging. Remember, by default, all the quantities given in the problem are line values only. So the line voltage was 400 volt. The line current was 50 ampere. Power factor was 0.8. I gave you a circuit. I gave you the voltage of the circuit, current and power factor also. Then can you find out active power drawn by that circuit? Yes. What is the formula? √3 VL IL cos phi. Simple. So therefore, as the voltage, current and power factor are available, first to find out what is the input power. The input power will be equal to √3 VL IL cos phi. Yes, the line voltage was 400, line current was 50, overall power factor was 0.8. This will give you the input power value, right? Calculate that. root 3 into 400 into 50 into 0.8. So 27712.8. 27712.8. This is the power drawn by the motor. After that, copper loss in stator was given, right? What is the copper loss in stator? Yes. See, power factor like the stator and rotor copper loss. See, stator copper loss 1.5 kilowatt. Iron losses are 1200 watt. So stator copper loss is 1.5 kilowatt. Iron loss is 1200 watt. Now what I need? I just need air gap power only. If you go back to the power flow diagram, if you want air gap power, you don't need all the losses, right? Only stator copper loss and iron losses are required. So what is the air gap power formula now? Yes. Therefore, air gap power is equal to input power minus copper loss in stator plus iron loss in stator. No mechanical loss in stator, right? What is the input power? 27712.8 minus copper loss in stator 1500 watt, iron loss was 1200 watt. You will get the air gap power in watt. You can convert into kilowatt. 2725012. 012 watt, that means 25.012 kilowatt. That is the value of air gap power. You see how simple the question. Option C is the correct answer. This question was given for 2 marks. Okay. So scoring marks from electrical machines subject is very easy. But you should not panic in the examination hall. Okay. 25 kilowatt is the correct answer. Fine. That's all. This is about power flow diagrams. Now, let's move to the next topic, torque equations. Okay. So first of all, we would like to develop the electromagnetic torque equation of a 3-phase induction motor. Okay, I can't derive each and every equation. I will directly write down the equation. The first equation that should come to your mind when we are talking about electromagnetic torque in induction motor, that is what I'm writing right now. Yes, electromagnetic torque is equal to air gap power divided by synchronous speed in radian per second. Very important. This is the first equation that should come to your mind when we are talking about equation for electromagnetic torque in induction motor. Air gap power divided by omega s, where omega s is nothing but synchronous speed in radian per second. And we already derived what is air gap power equation, right? In the rotor, there is a resistance and reactance, right? Resistance R2 by S, reactance X2. Try to solve it from the circuit diagram. Now, you leave about this is a machine. This is simply electrical circuits discussion, a simple RL circuit. Now, in this circuit, which element was drawing air gap power? R2 by S was drawing air gap power. What is the formula? We have written already, right? Air gap power is a power drawn by this resistance. Is it not I2 square into R2 by S? And you just divide that power with omega S, you will get the torque equation. So what is the electromagnetic torque equation now? Yes, first air gap power equation, 3 into I2 square into R2 by S. This is air gap power equation. Divide this equation with omega S. So therefore, let me write in more detailed manner. It will be 3 by omega S into I2 square into R2 by S. This is the formula for electromagnetic torque. I just divided air gap power with its omega S value. Next, what is the magnitude of current I2 here? Can I say current is equal to simply voltage by the impedance value? Therefore, one more equation for electromagnetic torque is 3 by omega S into, I need current square. Current square means voltage square divided by impedance R2 by S whole square plus X2 square into R2 by S. This is another equation. Can I say this is the equation in terms of voltage? This is the electromagnetic torque equation at what slip? At a slip S equal S. At a slip S. According to this equation, what is the relation between torque and voltage? Can I say electromagnetic torque is directly proportional to voltage or square of the voltage? Yes, torque is always directly proportional to square of the voltage. Therefore, if you try to excite induction motor with less voltage, sufficient torque cannot be created. Rated voltage is required. Also, electromagnetic torque depends upon the slip at which the motor is operating. Slip is very, very important. And remember, this is the equation we developed only by using rotor equivalent circuit. What if I give you stator branch also? Torque equation using complete circuit. Using a complete circuit, that means the stator branch is available R1, stator leakage reactance X1, rotor resistance R2 by S, rotor leakage reactance X2. I just neglected the shunt branch. Shunt branch is neglected because no load current is usually less. And what is the supply voltage? V1. This current is nothing but I2 dash. Rotor current referred to stator. Now in this entire equivalent circuit, who is drawing air gap power? R2 by S was drawing air gap power. Now the torque equation is same formula, air gap power divided by omega S. Who is drawing air gap power? This resistance is I2 square into resistance only. Power is I2 square into R divided by omega S. So it will become 3 by omega S into I2 dash whole square into R2 dash by S. Now how can you write current equation? Current means simply voltage by impedance. But you have current square here. Then this will become 3 by omega S into, what is the square of the current? Voltage by impedance. It is V1 square by impedance means this whole branch impedance will come. What is the total real part? R1 plus R2 dash by S whole square plus X1 plus X2 dash whole square into R2 dash by S. This looks a little lengthy, but actually the equation was very, very easy. It is simply air gap power divided by omega S. And who is drawing air gap power here? R2 by S. R2 by S. Normally, at gate level exams, usually stator branch impedance will be neglected. But in case if it is considered, you must use the full equation. But otherwise, this equation will be most of the times we will use. We will call this equation as generalized electromagnetic torque equation. You can use this equation for any amount of slip. Okay. For example, if I ask you to find out torque at 5% slip, you will replace S equal to 0.05. If I ask you to find out the torque at 10% slip, you will replace this S with 0.1. So you can find out torque using any amount of slip if you have this equation with you. Now what I will try to do is that using this equation, let me try to develop starting torque formula. Starting torque. Okay, right. What is meant by starting? We know at the time of starting, NR is equal to 0, slip will be equal to 1. Therefore, in the generalized torque equation, you have the generalized torque equation with you. You just replace S equal to 1, then it will become starting torque. Okay. So, if S is replaced with 1, then generalized torque equation will become starting torque. Then what will be the formula for starting torque? 3 by omega S into E2 square divided by, in the denominator S equal to 1, right? R2 square plus X2 square into R2. But if you look at the denominator, it is clearly resistance square plus reactance square. But we know this resistance square is usually very, very small. Because we will design the winding to have low resistance or high resistance, very low resistance. So therefore R2 square is neglected. So if R2 square is neglected, then what is the starting torque equation will become 3 by omega s into E2 square divided by x2 square into R2. x2 square into R2. Okay. Yes, this is approximate equation, guys. And according to this equation, you can understand starting torque value is directly proportional to rotor resistance R2. Okay. So starting torque of an induction motor is directly proportional to rotor resistance. So if you wanted to create higher starting torque, you have to add extra resistance to rotor. But extra resistance can be added into rotor only when the machine is which type? A slip ring induction motor type. If it is a squirrel cage type, we can't add extra resistance, right? Therefore, higher starting torque can be created by adding extra resistance into rotor. That is in slip ring induction motor. This is about starting torque. If you carefully look at that, starting torque is proportional to voltage or square of the voltage? Square of the voltage. Starting torque will also depend upon leakage reactance. Starting torque is also dependent upon rotor resistance. Okay, fine. Similarly, let us find out maximum torque equation also. Remember, maximum torque can also be called as breakdown torque, stalling torque, pull out torque, any word you can use. Maximum torque. Okay, first of all, I told you already, torque is equal to air gap power by synchronous speed. Can I say synchronous speed will depend upon supply frequency 120 F by P? For example, if the motor is excited from infinite bus bar, frequency will be always constant. That means synchronous speed is a constant value. If a synchronous speed is constant, torque is directly proportional to air gap power only. According to this equation, maximum torque can be created when air gap power is maximum. When air gap power is maximum. This is where maximum power transfer theorem concept will come into picture. If you draw the rotor circuit diagram, only the rotor circuit diagram, rotor has a reactance X2, a resistance R2 by S, voltage E2, current I2. Clear? This is the rotor, only rotor branch. I am not considering the stator branch at all. In this circuit, who is drawing air gap power? Yes. R2 by S was drawing air gap. Now our aim is air gap power must be maximum. If air gap power is maximum, then only torque will be maximum. So to make air gap power maximum, I can use maximum power transfer theorem. What is the condition? According to maximum power transfer theorem, the load power will be maximum if load impedance is equal to the source impedance. Okay, according to maximum power transfer theorem. According to maximum power transfer theorem, if load impedance is equal to source impedance, then only the load power will be maximum. Here load is nothing but R2 by S. Okay, so this impedance should be equal to source impedance. What is the load impedance? R2 by S must be equal to the source impedance X2. For example, if this condition was satisfied, then air gap power will be maximum. Automatically the torque is also maximum. Therefore, at this condition, whatever slip is available, we call it as SMT. That is nothing but the slip at which maximum torque is created. And you can separate SMT from here. What is SMT is equal to R2 by X2. Important. What is SMT? First of all, SMT is nothing but the slip at which maximum torque is created. For example, resistance is 1 ohm, reactance is 10 ohm. 1 by 10. SMT is equal to 0.1. That means the given induction motor will develop maximum torque at a slip equal to 0.1. Okay. Now, if that is SMT, then what about NMT? NMT is equal to 1 minus SMT into NS. First of all, what is mean by NMT? NMT is nothing but the speed at which maximum torque is created. I told you, SMT is the slip at which maximum torque is created. Similarly, NMT is the speed at which maximum torque is created. Okay, and very clearly that slip at maximum torque is created is dependent on rotor resistance R2. Remember, this is a maximum torque equation, not just a condition for maximum torque. This is just a condition. If you substitute this condition in the generalized torque equation, then you will get maximum torque equation. So if S is equal to SMT, then generalized torque will be equal to maximum torque. Okay, I will directly write down what is the formula for maximum torque. So maximum torque will be equal to 3 by omega S into E2 square divided by 2x2. This is the formula for maximum torque. 3 by omega S into E2 square by 2x2. Okay, according to this equation, you can conclude that maximum torque is independent of rotor resistance. Are you observing any R2 term here? No. Maximum torque is independent of rotor resistance. Whatever may be the rotor resistance, maximum torque will be same. But the speed at which maximum torque is created, that will definitely depend upon rotor resistance R2. Okay, if R2 changes, SMT will change. If SMT changes, NMT will change. So the speed at which maximum torque is created, that is definitely dependent on rotor resistance, but magnitude of the maximum torque is independent of rotor resistance. So we found three formulas so far. First one, generalized torque equation, 3 by omega S into E2 square divided by R2 by S whole square plus X2 square into R2 by S. This is a generalized torque equation. Next one, we also found starting torque, 3 by omega S into E2 square divided by R2 square plus X2 square into R2. Then we found maximum torque equation, 3 by omega S into E2 square divided by 2x2. Okay, three equations we found. This is a generalized equation. That means you can use this equation to find out torque at any slip. And remember, all these three equations are valid if stator branch is neglected or with respect to rotor branch only. Okay, with respect to rotor. I'm not considering stator branch at all. If stator branch is considered, what to do, I already explained in one way. In one case I explained, generalized case. If you replace S equal to 1, you will get starting torque. If you replace S equal to SMT, you will get maximum torque. But most of the time stator branch will be neglected. We will solve questions also, right? Now, there is a relation available among these three torques. The next duty is to find out the relation among these three torques: generalized torque, starting torque, and maximum torque. I will directly write down the equation. I'm not going through the derivation. Yes, first relation, generalized torque divided by maximum torque. This will be equal to 2 SMT into S divided by SMT square plus S square, where SMT is the slip at which maximum torque is created. Next relation, starting torque to maximum torque. You just replace S with 1. If I replace S with 1, generalized torque will become starting torque. Then it will become 2 SMT by SMT square plus 1 square. S equal to 1, that's all. Then it is SMT square plus 1 square, 1 square is 1. These two equations are very, very important. This is a relation among generalized torque and maximum torque, starting torque and maximum torque. Okay, these are the various torque equations. Okay, so first I told you, when we are talking about torque, the first thing that should come to our mind is torque is simply air gap power divided by omega s. It is simply air gap power divided by omega s. Okay, then we have starting torque, we have a maximum torque. Condition for maximum torque is important. SMT is equal to R2 by X2, but remember, this condition was developed by neglecting stator. Stator was not considered here. Only by using rotor, we developed this condition. And then we have maximum torque and relation among generalized torque, starting torque, and maximum torque. Okay, that's it. Now we will try to answer a question related to this concept. We are crossing our time actually. It's not possible to complete electrical machines in a speed of time. Okay, all right. So let's go through some questions related to the torque equations quickly. Look at this first question. So long back in GATE 96 paper. Yes, very simple question. When the supply voltage to an induction motor is reduced by 10%, maximum torque will decrease by how much percentage? We already found maximum torque is proportional to what? Look at the maximum torque equation. Is it not maximum torque proportional to square of the voltage? So if voltage was reduced by 10%, that means it becomes 0.9 times of the rated voltage. Then torque is proportional to square. What is 0.9 square? 0.81. That means 19% torque will be reduced. Maximum torque will be reduced by 19, approximately 20. Straightforward answer. Okay. Let's answer some difficult questions, 2 marks questions. Questions are always very easy. In electrical machines, you don't find difficult questions much. Okay. Yeah. So now let us try to answer question number 1. That is easy question actually. Go through this question. Yeah. A 3-phase wound rotor induction motor is to be operated with slip energy in the constant torque mode. When it delivers an output of P naught at a slip S, then theoretically the maximum power that is available for recovery at the rotor terminals. Okay, they are asking us power available at the rotor terminals. At the rotor terminals, is it not a slip power? The power that you can draw from the rotor is nothing but a slip power. Slip power is equal to S into air gap power. Okay, that is a slip power recovery concept. I did not discuss that. Okay, but you know that, right? In a regular classroom, we will discuss what is slip power and how to recover slip power, etc. So the power that can be recovered from rotor is known as slip power. That is nothing but S into air gap power. Okay, so S into air gap power means, can I write output power divided by 1 minus S, or actually air gap power formula, is it not mechanical power developed by 1 minus S? Therefore it is S by 1 minus S into mechanical power is nothing but output power only, because mechanical losses are neglected. So the answer will be S by 1 minus S times of output power. S by 1 minus S, that is last option. S by 1 minus S times of output power. This is the power you can recover from the rotor. Okay, slip power. All right, and that slip power can be given to the next motor. In speed control, there is a topic known as cascaded speed control. In that cascaded speed control, we will recover some power from the rotor of the machine and we will give that power to the next motor. Okay, we call it a slip power recovery concept. So it was simply S by 1 minus S into output power. Okay. Okay, next question number 2. Go through this question. A 400 volt 15 kilowatt 4 pole 50 hertz Y connected induction motor has full load slip of 4%. Output torque of the machine at full load is how much? Output torque of the machine at full load. Already it is given, it is a 15 kilowatt induction motor. Is it not output power? Because we know the nameplate power is always nothing but output power of the machine. And a full load slip is also given 4%. What is the torque we are asked to find out? Okay. Yes. See, the output power was equal to 15 kilowatt, that is 15,000 watt. Slip is equal to 0.04. We are asked to find out what is the torque. So the torque is equal to air gap power divided by synchronous speed. Okay, but air gap power was not given directly. Instead of that, output power was given. So air gap power is equal to output power divided by 1 minus S, correct? Yes, air gap power is equal to output power divided by 1 minus S, and there is omega S in the denominator. What is output power? 15,000. Remember, I am neglecting mechanical loss, guys. When mechanical loss was not given, you can neglect it. If mechanical loss is neglected, then only output power will be same as mechanical power developed. Okay. So, yes. So 15,000 divided by 1 minus, what is the slip? 0.04. What is omega S, guys? Is it not omega S is equal to 2 pi ns by 60? Separately, you calculate it. Omega S is equal to 2 pi ns by 60. It's a 2 marks question. Okay. So what is ns according to the question? It was a 4 pole 50 hertz. Is it not ns 1500 rpm? So it is 2 pi into 1500 divided by 60. You calculate this separately. Radian per second. I think you'll get 157 there. Substitute that 157 here. You will get the torque. Okay. You'll get the torque. Right? Tell me quickly, how much is that? So 15,000 is the output power divided by 1 minus 0.04 divided by 157. I am getting a 99.5 Newton meter. Come on, quickly answer. 99.5 Newton meter. Okay. So near to 100 is the answer. 99.5 Newton. Okay. So that was this one. 99.47. Simple question. Okay. This is a 2 marks question. Likewise, there are many questions. We don't have time to solve each and every one. One GATE 2008 question we will answer. This is important model. Yes. Anyway, all of you go through this question number 4. Okay, we will take a break after this. Go through this question number 4. GATE 2008 paper. Important 2 marks question. Question number 4. Yes, read that problem. A 400 volt 50 hertz 4 pole 1400 rpm star connected squirrel cage induction motor has the following parameters referred to stator. See, resistance is given, stator resistance. Reactances are also, don't mind about those question marks. Okay, that is stator and rotor reactances both are equal 1.5 ohm. Neglect stator resistance and core losses. Rotational losses are also neglected. Motor is controlled from a 3-phase voltage source inverter with constant V by F control. The stator line to line voltage and frequency to obtain maximum torque at starting will be. We want maximum torque at the time of starting. According to this question, we want maximum torque at the time of starting. Okay. First of all, this is a circuit where stator branch is considered or neglected. Yes, stator branch is considered. Therefore, we should not use our regular formulas. We have to draw the circuit diagram. But point is, stator resistance is neglected, but stator reactance is considered. 1.5 ohm. At which frequency? 50 hertz. Let's draw the circuit diagram first. Okay. So if I draw the circuit diagram, stator resistance is neglected, only reactance is available in stator. Next we have a rotor reactance X2, then we have rotor resistance R2 by S. Of course, they are referred to stator. Here we have the stator voltage, and this is the current, rotor current referred to stator. This is a circuit diagram with stator branch, but stator resistance is neglected. And who is drawing air gap power here? Air gap power is drawn by resistance R2 by S. Therefore, torque is equal to always air gap power by omega S. So, torque is directly proportional to air gap power divided by, can I say omega S is dependent on frequency? Correct. Omega S is definitely dependent on frequency. Okay, but they are asking us maximum torque at the time of starting. Okay, we all know at starting S is equal to 1. Correct or not? S is equal to 1. Remember, in this case, frequency is not constant. In the given question, frequency is a finite value. Because of frequency, they are modifying. If you read the question carefully, rated frequency was 50, but you look at options, frequency changes. At what frequency maximum torque is created? That's the question. V by F ratio must be constant. Okay, therefore frequency is variable. All right. Now at starting S equal to 1, if S equal to 1, can I say this resistance will become simply R2 dash only? Then electromagnetic torque is directly proportional to, what is the formula for air gap power? 3 I2 square into R2 only. Actually it is R2 by S, but at starting S equal to 1. Clear? Now what is the formula for I2? I2 is nothing but voltage by impedance only. Yes. So therefore torque is directly proportional to 3 by F I2 square. Is it not voltage square divided by impedance, that is square root of x1 plus x2 whole square plus R2 square into R2. Now what are the only variable parameters here? Voltage and frequency are variables such that torque must be maximum. Okay, maximum torque is possible when load impedance is equal to source impedance. Correct or not? What is the load impedance? Air gap power will be maximum if load impedance is equal to source impedance. What is the load impedance? R2 dash. What is the source impedance? X1 plus X2 dash. Then air gap power will be maximum. Okay. If air gap power is maximum, then automatically the torque is also going to be maximum. You can find out easily. Okay. What is the rotor resistance given? Resistance is 1 ohm, but the two reactances combination is 1.5. Yes. R2 is 1 ohm, but at 50 Hertz, X1 plus X2 is equal to 1.5 plus 1.5. This is 3 ohm. But now at maximum torque, X1 plus X2 new value must be equal to R2. The new reactance must be equal to R2. Why? If reactance is equal to resistance, then only maximum power will transfer to this resistance. Then only air gap power will be maximum. Correct? So therefore, the new reactance X1 plus X2 is equal to 1 ohm. Earlier, what is the total reactance? 3, but now what is the total reactance? 1. That means, can I say reactance is divided by 3? Overall reactance divided by 3. Overall reactance will be divided by 3 only if frequency divided by 3. Therefore, what is a new frequency? 1 by 3 times of rated frequency. 1 by 3 times of rated frequency was 50. Is it not how much? 50 by 3. $16.66. You see, 16.66 Hertz. That is the new frequency. But they said V by F ratio must be constant. That means rated voltage by rated frequency must be equal to new voltage by new frequency. What is the rated voltage? 400, rated frequency 50. Then what about new voltage and new frequency? So rated voltage 400 by rated frequency 50 is equal to new voltage by, what is the new frequency? 16.66. Find out what is the new voltage. 133.33 volt. So the new voltage was 133.33. New frequency was 16.66. So 133.33 is the new voltage. New frequency was 16.6. Correct? So the point is frequency is a variable value, and we are asked to find out maximum torque at the time of starting. At the time of starting, S equal to 1. Okay, this much derivation is also not required actually. All this derivation is not required. Simple thing is, if S equal to 1, this resistance becomes simply R2. And this power will be maximum. Okay, just a moment. Yeah, this power will be maximum only when the load impedance is equal to source impedance. The source impedance is this reactance only. Load impedance is this resistance. So actually this reactance is a 3 ohm. Together it is 3. But the new reactance should be equal to 1 ohm. Correct? 3 ohm will become 1 ohm only when reactance is divided by 3. Reactance will be divided by 3 only if frequency divided by 3. That is how I found the new frequency. 1 by 3 times. Okay? Right. There are many questions. Okay? Important questions. Okay. We can't solve every question because I recorded one separate video, gate PYQs, 1 year back. You go through that video, you will find the solutions to all the gate questions. Here we have to discuss all the topics. Anyway, so take a short break, then we will discuss the remaining topics related to induction motors. Okay. Take your lunch, then we will continue our discussion. All right, welcome back, guys. So hope you had your lunch. All right, let's continue our discussion. So we are discussing about induction machines, and in which we completed up to the torque equations. So let's move to the next topic. All right. All right, we have seen different types of torque equations like starting torque, okay, maximum torque, generalized torque equation, etc. So let's move to the next topic, that is uh, torque speed characteristics. Okay. Okay. So I'll be directly drawing the characteristics. Okay. So we will not be discussing about how the characteristics came and what is the proof, etc. So I'll be taking the speed on x-axis, and we will be taking electromagnetic torque on y-axis. First we will draw only for the motoring mode, then we will see for all the three types of modes, that is motoring, braking, generating, etc. So let's start here. This is the point. I hope my audio was clear. Everything is all right, right? Check once. Yeah. So everything is all right. Fine. Yeah. So so let us start here. This is the point where nr is equal to 0. Starting means nr is equal to 0. nr equal to 0 means slip will be equal to 1. Let us say this is a final point where nr is equal to ns. That means slip will be equal to 0. And we know at the time of starting, the torque is a finite value. Three-phase induction motor is a self-starting motor because its starting torque is a finite value. And later, it will increase non-linearly till it reaches to maximum value, and then the torque will become 0. So this is what we call it as maximum torque of an induction motor. Yes or not? And this maximum torque is observed at a speed equal to nmt and a slip equal to SMT. We discussed what is SMT, what is NMT, etc. Right? Now you can understand there are two modes of operation here. This is a non-linear zone where torque is inversely proportional to slip. This is a linear zone where torque is directly proportional to slip. And which zone is usually stable? We know that the linear operating zone is usually stable and a non-linear operating zone will be usually unstable. When I say usual, indirectly, for majority of industrial drive applications, this linear zone will be stable and a non-linear zone will be unstable. Okay. Yes. So this linear zone will be usually stable and this non-linear zone will be usually unstable. And a very important observation is this linear zone. This linear zone is the zone where slip is near to 0, correct or not? Slip near to 0 or speed near to synchronous value. And in this operating zone, R2 by S value will be much higher compared to X2. This is very, very important. If you draw the equivalent circuit of induction motor, there are two parameters in the rotor. One is R2 by S, another one is X2. Correct or not? Now, machine will always operate in the linear operating zone. And in this linear operating zone, slip is very near to 0. Usual range of slip will be 1% to 5%. That is 0.01 to 0.05. As slip was very near to 0, this S value is very low. That's why R2 by S is very high. So when I say R2 by S is very high, don't say R2 is very high. It is not because R2 is very high, because it is S is very low. Usually resistance is very small, but R2 by S is high because slip is very low. So in the stable operating zone, R2 by S value is much higher than X2. Very, very important. Okay. Now, how to find out the stability of a given induction motor? There are certain example questions also. Okay. So if you just let us go through this question, all of you. Okay. Yeah. I don't know whether it is visible to you or not. Let's go through this question number 3. It is given in GATE 2007 paper. According to this question, there are electromagnetic torque TE curve and load torque TL curve, both were given. And there are 4 options, which is going to be stable and which is going to be unstable. That is what we need to find out. A, B, C, D, there are 3 curves given, 4 curves. What are the stable operating curves and what are the unstable operating curves? Okay, this is the question. Now let me try to answer this. Okay, to find out the stability of the given curve, the first thing you need to do is create a disturbance. Create a disturbance, and if the machine was able to regain the steady state, it is called as a stable system. Unable to regain the steady state, it is called as unstable system. And we have 4 operating zones like that. Okay, I think the space is not sufficient. Let me do one thing. Okay, so I'll take the first curve, only 1-2 curves. If I solve, then the remaining thing you can do. So you see electromagnetic torque is like this, load torque is like this. Okay, so this is the speed curve and this is the torque, and they said according to the graph, electromagnetic torque, load torque. I'll just redraw. This is electromagnetic torque curve and this is the load torque. This is operating point A. Is that A point is stable or not? First of all, right now this point is known as steady state operating point. Steady state means the point where electromagnetic torque and load torque both are equal. And we know in induction motor which torque is supporting torque and which torque is opposing torque. I told you electromagnetic torque is a supporting torque. It will push the rotor towards the synchronous speed. But a load torque is an opposition torque. It will push the rotor in the opposite direction. Electromagnetic torque is supporting, load torque is opposition. So this electromagnetic torque is a supporting torque. This load torque is an opposition torque. To find out the stability, what is the first thing we need to do? Create a disturbance. When I say disturbance, it may be either sudden decrease in speed or sudden increase in speed. Anything it can be. Even though a disturbance is created, if the motor was able to regain the steady state, we call it a stable operating point. Otherwise, it is going to be unstable. So at this point, assume the speed is equal to NR. Create a disturbance. Let us say what happens if speed is suddenly reduced from NR to, let us say, NR dash. Okay. Now at this NR dash, yes, this point represents which torque? This is a load torque, guys. At the same NR dash speed, this is the electromagnetic torque. So if I ask you the question, electromagnetic torque is more or load torque is more right now? Yes, you can easily understand electromagnetic torque is more. That means the supporting torque is more or opposition torque is more? Supporting torque is more. If supporting torque is more, machine will accelerate or decelerate? Accelerate. Therefore, speed will increase and will come back to the previous speed. That means even though the disturbance is created, the machine was able to regain the steady state, previous steady state. That's why operating point A is going to be a stable operating point. Okay, let us take one more curve. If you look at the last curve, you can do the remaining 2 also. I am taking the last curve. Okay, yes, not last curve. Let us solve one unstable operating point. Yeah. So let us take curve number B. You can see this is electromagnetic torque, this is load torque. Okay. Let us take one more curve. This is the speed of the motor. This is the torque. Okay. So if you look at the graph carefully, second graph. Okay. Electromagnetic, this is the load torque. And this is the electromagnetic torque. This is known as operating point B. Is this operating point B stable or unstable is the question. As I mentioned, to understand stability, you have to create a disturbance. The disturbance may be either decrease in speed or increase in speed. Let's say at this operating point B, let us say speed is steady state. Let's call it as NR. Disturbance means either decrease in speed or increase in speed. For example, what if speed increases suddenly from NR to NR dash? You can take decrease in speed also, no problem. You can take any speed. What if speed suddenly increases? Now can I say at this NR dash, this is the load torque value. At the same NR dash, this is the electromagnetic torque value. Which torque looks higher? This is load torque magnitude. This is electromagnetic torque magnitude. Can I say electromagnetic torque is higher? Electromagnetic torque is higher means supporting torque is higher or opposition torque is higher? Supporting torque is higher. If supporting torque is higher, machine will accelerate, therefore speed will further increase. Speed will further increase. That means, is it able to come back to the previous steady state? No. That is why operating point B is unstable. Operating point B is unstable. So, to identify the stability of induction motor, we have to create a disturbance. The disturbance may be either decrease in speed or increase in speed. Right now, the machine is in motoring mode. That's why electromagnetic torque is supporting torque, load torque is opposition torque. For example, if the machine is in generating mode, then exactly opposite thing will happen. Electromagnetic torque will become opposition torque, load torque will become supporting torque. Okay, there was one question related to that mode also. I think, yeah. In question number 5, same model but a different way of answering. Question number 5, this was given in GATE 2014 paper and it was a 2 marks question, I think. Yeah, question number 5, read this question and there are 2 graphs. Once again, the question is about stability only. Okay, see the torque speed characteristics of motor Tm and load TL for the 2 cases are shown in the below figures A and B. The load torque is equal to the motor torque at PQ, R and S. There are 2 graphs, right? This is graph 1, first characteristics A, and this is the second characteristics B. We are asked to find out the stable operating points. We will take any one curve right now. Okay, yeah, let us take operating curve 1. If I take first graph, you can easily understand right now according to this graph, x-axis is right side. That means this is a positive value. But the curve is on the negative side of y-axis. Am I correct? That means the speed is negative. Torque is positive, speed is negative. Torque positive, speed negative. That means both are in the same direction or opposite direction? Opposite direction. That means torque is opposing the rotation of the machine. Let me draw that curve first of all. Okay. This is the motor torque and this is the load torque. Okay. So, if you carefully look at the diagram, this is the torque. Is it not a positive side of the x-axis? This is negative side of the y-axis, speed. This is the motor torque given, Tm, and this is the load torque. I can use a different color so that you can easily recognize it. This is the load torque. Okay. According to the given diagram, the motor torque is positive, but the speed is negative. That shows that both are in opposite direction. Therefore, motor torque is opposing the rotation. When I say motor torque is opposing, indirectly load torque will be supporting. Therefore, this is a generating mode indirectly. The machine is operating like induction generator because the load is acting like a supporting torque. That is nothing but a prime mover actually. In regular class, we use it to discuss this. Okay, but here I am quickly going. Okay, and this is operating point. Which operating point? P, and another one is Q. This is operating point P. This is operating point Q. Now, how do you identify who is stable, who is unstable? Just to create the disturbance. At this operating point P, assume the speed is equal to N1. Okay, speed is on y-axis. Please remember. N1, this is a 0 speed indirectly. You create the disturbance. I told you disturbance may be either increase in speed or decrease in speed. You take any disturbance. I am taking increase in speed. If I assume speed is increased from N1 to N1 dash, at this N1 dash, this is which torque? Load torque. This is going to be motor torque. Which torque looks higher? Can I say motor torque is more, load torque is less? When I say motor torque is more, you please see the width is nothing but the torque value. Motor torque is more, that means opposition torque is more. If opposition torque is more, machine will accelerate or decelerate? Decelerate. Because of that deceleration, speed will decrease and will come back to this N1. Therefore, operating point P is going to be stable. You do the same analysis for operating point Q, you will get instability. I request you to check it rather than concluding directly. Similarly, we have one more curve, right? You look at curve 2. Could you tell me in this curve, try to understand torque is positive or negative? We are on the right side of x-axis, torque is positive. We are on the upside of y-axis, so speed is also positive. Torque positive, speed positive. That means both are in the same direction. Both are in the same direction means the motor torque is supporting the rotation or opposing the rotation. Yes, the motor torque is supporting the rotation. Indirectly, the motor torque is supporting. If motor torque is supporting, load torque is opposition. Okay, so let us quickly solve it. So this case, this is the motor torque, this is the speed. This time torque is positive and speed is also positive. That means both are supporting each other. Okay, and if you go through the diagram, motor torque is like a linear line. This is the motor torque and this is the load torque. So this time the motor torque is a supporting torque. How can I say that? Because torque and speed are in the same direction. Both are positive. Both are supporting each other. That means load torque is opposition. So these are the two operating points. This one is R, that one is S. This is R, this is S. To find out stability, okay, if I do it at S, let us say at this S, assume the speed is NR. Create a disturbance, I told you. Sorry, I made a mistake. X-axis is actually torque, right? Not speed. X-axis is torque, not speed. Speed is on Y-axis, is it correct? Yes, speed is on Y-axis. So at this point, yes, let us say the speed is equal to NR. I told you what is how to find out stability. Create a disturbance, either decrease in speed or increase in speed. Let us say I am decreasing the speed from NR to NR dash. This is zero speed, guys. Moving towards zero means speed decreases. At this NR dash, this is which torque? Yes, this is the load torque. This is which torque? This is the motor torque. Which torque is higher in magnitude? You can see this is load torque magnitude. This is motor torque magnitude. Can I say motor torque magnitude is more? When I say motor torque magnitude is more, supporting torque is more. If supporting torque is more, machine will accelerate. Accelerate means speed will increase and will come back to the previous point. As the speed is coming back to the previous point, therefore operating point S is stable. In a similar manner, you can find out R becomes definitely unstable. Therefore, final answer is P is stable, Q is unstable, R is unstable, S is stable. Therefore, the final answer P and S are stable. P and S are stable. Option B is correct. This is the way to identify the stability of a given induction motor. First of all, from the given graph, you must understand which torque is supporting the machine and which torque was opposing the machine. If a torque and speed both are positive, that means both are supporting each other. If a torque and speed both are negative means what? Again, both are in the same direction only, supporting. If a torque is positive, speed is negative, opposing each other. Or if speed is positive, torque is negative, opposing each other. Okay. This is how we have to identify stability of a given three-phase induction motor. Okay. All right. Now, next observation is effect of rotor resistance on torque speed characteristics. Effect of rotor resistance on torque speed characteristics. Okay. So indirectly what I am talking about, what happens if additional resistance is added into a rotor circuit? Yes, we studied already starting torque formula, right? What is the formula for starting torque? 3 by omega s into E2 square divided by R2 square plus X2 square into R2. But in the denominator, generally winding resistance is always very less compared to leakage reactance. Why? Because to reduce losses, generally we will design winding to have low resistance. So if this resistance is neglected, then approximate starting torque will be 3 by omega s into E2 square divided by X2 square into R2. From this, starting torque is directly proportional to rotor resistance. So if you want higher starting torque, extra resistance must be added into rotor. Next, What about maximum torque? I told you already, maximum torque is independent of rotor resistance, right? It is 3 by omega s into E2 square by 2x2. It is independent of rotor resistance. That means even though resistance is added into rotor, maximum torque doesn't change. Maximum torque doesn't change. But the condition for maximum torque will be changing. Okay, but the condition for maximum torque is going to be changing. All good, right? Going well? No issues in the session, right? Let me know in the chat box if you find any issues related to audio or video. Hope everything was going well. Yeah. So that is the maximum torque value. What about condition? Condition for maximum torque, SMT is equal to R2 by X2. Actually, this is a formula. If stator branch is neglected. But if we add extra resistance into rotor, if I add extra resistance into rotor, this will become R2 plus R external. An extra resistance is added into rotor. The formula got changed. Therefore, SMT will change. Indirectly, what happens if extra resistance is added? SMT increases. If SMT increases, what about NMT? We know the formula for NMT, 1 minus SMT into NS. If SMT increases, NMT will decrease. That means maximum torque will now occur at the same speed or lower speed, lower speed. That is the meaning of it. Okay. So if I draw the curve by taking speed on x-axis, torque on y-axis. For example, if you did not add any extra resistance into rotor, this is NR is equal to 0, NR is equal to NS. If I did not add any resistance into rotor, starting torque is a finite value, and then this is a maximum torque and 0 torque. See, I am drawing a non-linear zone with dotted line because I know it is unstable zone. This is the maximum torque. This is the graph before adding extra resistance, that is like case number 1. Now what happens if extra resistance is added? Starting torque will increase, right? Starting torque will increase. Maximum torque remains the same, but it will occur at lower speed. Okay, this is the graph when extra resistance is added into rotor. And if I keep on increasing the resistance, starting torque will further increase. Maximum torque will now occur at much lower value. So this is the graph with extra resistance R3. If I keep on doing that, after a finite value, definitely starting torque keep on increasing, and at one particular resistance value, starting torque will be equal to maximum torque. That is case number 4. Okay, what is the relation among these resistors? If I ask you, then definitely R4 is greater than R3, greater than R2, greater than R1. R4 is the highest resistance. And especially if you keep your eyes about this fourth curve, okay, at this resistance R4, starting torque value is equal to maximum torque. You can create maximum torque at starting by adding extra resistance into rotor. Okay, maximum torque at starting. Okay, this is possible only when extra resistance is added. First of all, maximum torque means SMT is equal to R2 plus R external by X2. But I need maximum torque at starting. We know at starting S is equal to 1. Combine both equations, therefore in place of SMT substitute 1 R2 plus R external by X2. That implies R2 plus R external must be equal to X2. If this condition is satisfied, what is the meaning of it? Maximum torque can be created at the time of starting. Maximum torque can be created at the time of starting. Okay. Remember, this is the derivation valid only if stator branch is neglected. Okay. If a stator branch is considered, then the equation will further change. Then we have to use maximum power transfer theorem to solve the problem. Okay. Fine. So now let's see some questions related to this concept. Okay. did you remember this question? This is a last year GATE examination question, GATE 2025, related to the characteristics of the induction motor. Okay. Which of the following trajectories will make the shortest time? Okay. Shortest time. Shortest time means quickly the motor has to accelerate. To accelerate quickly, there should be more acceleration, right? Acceleration is possible only when electromagnetic torque is more than load torque. See, already this is the load torque. Therefore, electromagnetic torque should be more than this. More than this, that to highest value. If it is very high, then only more acceleration will come. So the highest value means it is obviously F. Just a moment. This F Q R. Okay, anyway, leave it. Okay, so low electromagnetic torque should be as much high as possible so that you'll get more acceleration. F Q R. Okay, O F Q R. That is the trajectory of electromagnetic torque, so that quickest acceleration will come. Clear? Okay, anyway, let's solve some questions related to this. We don't have much questions related to the characteristics of induction motor. Okay, let's answer this question. This is a 2 marks question, guys. 2 marks question given in GATE 2003 paper. Look at this question. Question number 1. Read that question number 1. Everyone. GATE 2003 paper. Question number 1. Okay. A 3-phase induction motor is driving a constant torque load at rated voltage and frequency. If both voltage and frequency are halved, the following statements related to the new condition if stator resistance and leakage reactance and core losses are neglected. Very important model. It's a theoretical question. These kind of questions you can expect for MSQs, multiple select questions in the actual GATE exam. 4 options will be given. What are the correct options? That is the question. 3-phase induction motor driving a constant torque load. The most important information was constant torque load. Initially, it was at rated voltage and frequency. Later, what happened? Both voltage and frequency are halved. Voltage becomes half, frequency also becomes half. What will happen? What will happen to the difference between synchronous speed and actual speed? Air gap flux, that is another question. Stator current, about current is another question. Per unit slip is another question. Okay, voltage becomes half, frequency becomes half. I hope most of you know this. Okay, in case of induction motor as well as in transformer, flux density is always proportional to V by F ratio, right? If I say flux density proportional to V by F ratio, indirectly flux also proportional to V by F ratio. So when I say voltage becomes half, frequency becomes half, can I say flux density remains constant? Therefore, one of the statement we already got the information. Yes, the air gap flux remains constant. That is a correct statement. Second statement is correct. Okay, second statement is correct. Next, one more important information. I need to understand difference between synchronous speed and actual speed. That is ns minus nr. What will happen? Stator current, what will happen? Per unit slip, what will happen? This is all we have to answer when voltage becomes half, frequency becomes half, but driving a constant torque load. Very, very important. Torque is a constant value. What is the torque equation? Yes, the torque equation. Stator impedance is neglected, so the generalized torque equation you can write 3 by omega s into E2 square by R2 by s whole square plus x2 square into R2 by s. Okay, now I need to write down this equation in terms of voltage and frequency. Then only I can say what will happen to torque, various parameters, etc. First of all, I told you already, according to the graph, characteristics of the induction motor, machine will always operate in the stable zone, which is a linear zone. And in the linear zone, I told you R2 by S is much higher than X2, correct? R2 by S is much higher than X2. If R2 by S is much higher than X2, can I say R2 by S whole square will be much higher than X2 square? Therefore, which value can be neglected? X2 square can be neglected. If X2 square is neglected, just let me remove it directly. If X2 square is neglected, can I say 1 R2 by S value will cancel? Just a moment. Yes, 1 R2 by S value will cancel here and S will go to the numerator. Therefore, torque is equal to 3 by omega S into E2 square by R2. And therefore, what are the constant values here? Already it is given torque is a constant value. Okay, resistance is a constant value, no change in the resistance. But omega S is variable because the frequency is changing, voltage is variable. So from this, I can write down, a separate slip value. Slip will be proportional to omega S will go this way, that is F divided by V square. You take F to the denominator. S is directly proportional to 1 by V by F into V, correct? In the given question, V by F is constant. Why? Voltage becomes half, frequency also becomes half, V by F is constant. So S is inversely proportional to voltage. Therefore, when voltage becomes half, S becomes 2 times. Therefore, slip is doubled. Slip is doubled. So slip is not a constant value. Slip is doubled. Slip is doubled. Okay. So I think one of the option, per unit slip remains the same. That is a wrong statement, right? The actual statement is per unit slip is doubled. Fourth one is a wrong statement. Okay. Then what is the formula for slip? We know slip is equal to ns minus nr by ns cross multiply. S into ns is equal to ns minus nr. Okay, can I say ns is proportional to frequency? Therefore, ns minus nr is directly proportional to slip into frequency. What happens in this question? Slip is doubled, we proved just now. Slip is doubled, S becomes 2S. What happens to frequency? Frequency is half, that is given in the question. So, if frequency is half, but S is doubled, can I say 2 and 2 will cancel? Therefore, ns minus nr will be a constant value. Are you understanding this? Okay. Slip is doubled, frequency becomes half. Therefore, definitely ns minus nr is going to be constant. Okay. I think first statement is correct, right? What is the first statement? The difference between a synchronous speed and actual speed remains the same. First statement is correct. Air gap flux remains the same. Second statement is correct. Per unit slip remains the same. Fourth statement is wrong. 1, 2 correct. Fourth one is wrong. Okay. You can pick the option. Fourth one wrong means already C and D are eliminated. All statements are correct. That is also eliminated. Therefore, the correct answer will be 1, 2 and 3 only. And I will try to prove that. What will happen to stator current? What will happen to current? To answer what happens to current, let us write down a torque equation in terms of current. What is the torque equation? Air gap power by omega S. Air gap power formula 3 into I2 square into R2 by S. Okay, in this torque is constant. Omega S, this is proportional to frequency. And resistance is constant. No change in resistance. Therefore, I2 square will be proportional to omega S will go this way. Slip also goes this way. Frequency into slip. Correct or not? Are you understanding? I'm quickly going. Okay, I don't have time. I hope you understand. Omega S, synchronous speed depends upon frequency. And there is a slip term also. So I2 square, if I cross multiply frequency into slip. What happens to frequency in this question? Half. What happens to slip? Doubled. Frequency becomes half. Slip is doubled. That means the product is constant. Therefore, current is a constant value. If rotor current is constant, stator current will also be constant. Therefore, current is constant. The third statement is also correct. See, that's why it is a 2 marks question. Even though you did not answer this third statement, but you can still pick up the option. Most important data that was given in the question is Torque is a constant value. Torque is a constant value. So write down the equation for a torque. Voltage and frequency becomes half. V becomes V by 2. F becomes F by 2. Clear? Okay. That is how we proved everything. So the observation is slip is doubled. This is very, very important. Slip is not constant. Most of the students will confuse. What is the confusion? They will write like this. Sir, linear zone means torque is directly proportional to slip. In the question, they said torque is constant. That's why slip is also constant. That is wrong analysis. You have to write down the complete torque equation. And in this zone, R2 by S is more than X2. Okay. This is the analysis. As R2 by S is actually here, X2 square will be there. Okay, as R2 by S is much higher than X2, X2 square is neglected. One R2 by S will cancel, slip goes to the numerator. Now torque is constant, resistance is constant. You wrote the equation in terms of frequency and voltage, and we found that a slip is doubled. Okay. Clear? Right. That's all. This is about torque speed characteristics, and we have discussed only motoring mode. I'll quickly go through the other modes also. I told you I don't want to discuss generating mode and braking mode. Okay, but just I will draw the curve. I don't have time. Okay. So I'm taking the speed on x-axis or slip on x-axis, better word. If I take the slip on x-axis and torque on y-axis, this is a starting point where slip equal to 1. This is where NR is equal to NS, that is a slip equal to 0. NR more than NS, slip is negative. This is slip is greater than 1. So this is how the usual torque speed characteristics of induction machine can be. This is what we call it as braking mode, right? Braking mode means slip is greater than 1. What is the formula in braking mode? S is equal to NS plus NR by NS. Okay, NR and NS in opposite direction. This is the motoring mode. In a motoring mode, what is the range of slip? The range of slip will be from 0 to 1. What is the formula for slip? NS minus NR by NS. But NR is less than NS. This is motoring mode. This is the generating mode. In generating mode, slip is negative. Slip is negative. The formula for slip is same. NS minus NR by NS, but NR is greater than NS. Then only slip will be negative. And in this entire 3 modes of operation, what is the only stable zone? Linear zone. Linear zone is this one. This is the stable operating zone. Stable. You don't find stability in the non-linear zone. That means in the braking mode, there is no stability. This is a non-linear zone. Torque is inversely proportional to slip. Torque is inversely proportional to slip. Torque is directly proportional to slip. This is again non-linearity. Inversely proportional to slip. Okay. You have to cover braking mode and generating mode also. I will not be discussing right now. I will be focusing only on motoring. Okay. Clear? Right. Now let's move to starting methods. Starting methods. First of all, why starters are required in induction motor? As the name itself is indicating, starting. We know at the time of starting, slip is equal to 1, right? If slip is equal to 1, if you remember the rotor equivalent circuit, rotor has only one resistance, R2 by S. But that R2 by S can be divided into series combination of two resistances, R2 and R2 into 1 by S minus 1. But now at the time of starting, what is happening? At starting, S is equal to 1. If you replace that S is equal to 1 here, this resistance will become 0. And how do we represent zero resistance? A zero resistance is simply represented like a short circuit. Because it was a short circuit, a large amount of current will be drawn by the motor. And in order to control that large current, we have to use different types of starters. If you don't use any starter and if we directly switch on the motor, that type of starting is known as DOL starting method. Okay, DOL starting. What is meant by DOL starting? Starting an induction motor directly from the rated voltage. Directly from the rated voltage. Then the load is acting like a short circuit. That's why this current is also known as a short circuit current. Then the current is known as short circuit current. And this short circuit current will be much higher than rated current. Therefore, more voltage will drop in the transmission line. And in order to control that, we have to start the motor with rated voltage or reduced voltage. All these things you will study normally, right? So ISC is equal to rated voltage E2 divided by rotor impedance Z2. And this current is much higher than rated current. And in order to control this current, what we need to do, let us start the motor rather than from rated voltage, we will start it from reduced voltage. Okay. So what if the motor is started using reduced voltage? Starting with reduced voltage. Starting with reduced voltage. Therefore, rather than applying a voltage E2, we will apply a voltage X times of E2, where X is the fraction of voltage we are applying. For example, if X equal to 0.5, that means we are applying half of the rated voltage. If X equal to 0.7, we are applying 70% of the rated voltage. Okay. And the rotor resistance is R2, reactance is X2, and the load resistance is simply shorted because it is at the time of starting. Now this current is known as a controlled starting current. Now the starting current will be equal to X into E2 by Z2. In this already what is E2 by Z2 is ISC. Therefore, now the starting current is X times of ISC. X times of ISC. So therefore, who will decide the amount of starting current? This fraction X will decide. So where X is per unit voltage we are applying. For example, if X equal to 0.5, that means we are applying 50% of the rated voltage. If X equal to 0.6, we are applying 60% of the rated voltage. So X will decide the amount of starting current. And the question is how to reduce the supply voltage at the time of starting. Okay. Yes. Now the question is how to reduce that starting voltage. Yes, there are different techniques. We have series reactance starting, we have auto transformer starting, we have star delta starting method. Out of that, auto transformer method and star delta method are more popular. Okay. For example, if we are talking about auto transformer method, in auto transformer starting, what we will use? A very simple, a step down auto transformer will be used. Okay. So here we will apply rated voltage V but this side we will get reduced voltage X into V. For this X into V, the induction motor was connected. Okay. Now that means induction motor is excited from how much voltage? X into rated voltage. Therefore, the starting current drawn by induction motor will be X into ISC. Then this current will become X square into ISC. Correct? All right. So therefore, the motor current may be X into ISC, but the current drawn from the line current at the time of starting. When I say line, it is nothing but a transmission line. The transmission line current at the time of starting is X square into ISC, where X is the fraction of voltage that we are applying. The fraction of voltage that we are applying. Okay. Clear? So that X is nothing but percentage tapping here. Percentage tapping. So for example, if X equal to 0.5, 50% tapping. If X equal to 0.3, 30% tapping. If X equal to 0.6, 60% tapping. So that X value will decide the tapping on the auto transformer. Okay. Clear? Fine. Next we have star delta starting. In star delta starting, first point, star delta starting is useful only when the motor is delta connected. Only when the motor is delta connected. If the motor is star connected, we don't use this star delta starting. Only when the motor is delta connected, we will use this star delta starting. First point. Okay. Next point, star delta starter is equivalent to auto transformer starter with tapping 57.7%. Okay. It is equivalent to auto transformer starter, auto transformer starting with 57.7% tapping. With 57.7% tapping. All right. And in this case, the starting line current will be equal to 1/3 times of ISC. Okay. In case of auto transformer, what is the starting line current? X square into ISC. That X value will decide what is the starting line current. But here the starting line current is 1/3 times of ISC, fixed value. Remember, ISC is nothing but the DOL current. Remember that, DOL current. DOL is nothing but the short circuit current indirectly. Yes, even starting torque also with star delta method is equal to 1/3 times of starting torque when compared to DOL method. We are not trying to prove everything, we are just writing the summary points here. Okay. So if it is a star delta starting, the starting line current will be 1/3 times of ISC, and even the starting torque is also 1/3 times of a DOL starting method, right? Clear? Yes. These are the starting methods we have. So you see the summary of star delta starter. In star delta starter, what we will do is, initially we will connect or we will use stator winding with a star connection. We will excite the motor. Once speed reaches near to synchronous value or rated value, then the connection will be changed to delta, because delta is the actual rated connection, okay, or rated winding. Clear? Okay. Now we will try to answer a few questions related to these starting methods. Okay. See. Okay, some 2 marks questions we will try to discuss. Okay, look at this question number 1. This was GATE 2005 paper question. Question number 1. Visible, right? This side. Yes, read that question. Read that problem. A three-phase cage induction motor is started by DOL switching at the rated voltage. If the starting current is 6 times the full load current and full load slip is 4%, then what is the ratio of starting torque to full load torque? Yes, here an important formula we have to study. I did not derive it actually. In starters we will study that, right? What is the ratio from starting torque to full load torque? It is equal to x square into ISC by IFL whole square into slip at full load. Most important formula in starting methods. No need to go through the derivation, just remember this formula. Starting torque to full load torque is equal to x square into ISC by IFL whole square into SCFL. Now this x value will depend upon the type of starting method you are using. If we are using DOL method, x is equal to 1. If I use auto transformer method, x will be based on the tapping position. If I use a star delta method, I told you star delta method is equivalent to auto transformer method with tapping 57.7%. That means x becomes 0.577. Therefore, the value of x will depend upon the type of method that we are using. In the given question, what method is used? Clearly given DOL method. DOL method means x equal to 1. Then the starting current is equal to 6 times the full load current. We know in DOL method, what is the starting current? ISC. ISC is equal to 6 times the full load current. Full load slip is 4%. Okay. So therefore, if you substitute everything, x equal to 1 because they are using DOL method. Starting current in DOL method, is it not ISC? So ISC is 6 times of rated current, also known as full load current, whole square. And slip at full load was 4%, that is 0.04, correct? The slip is 4%, 0.04. Then what is the ratio? Is it not 36 into 0.04? You can find out the ratio. That is the ratio between starting torque to full load torque. Okay. So 1.44. So the value, the ratio from starting torque to full load torque is equal to 1.44. Simple question. Now go through question number 2. Don't mind about these question marks. Okay. You just go through the question. Yeah. This is also important. This was in GATE 2006 paper. Go through it. At this speed, I think we can cover only 2 machines today. We may not be able to cover all 4 machines. I'll try to take one more, marathon session with remaining 2 machines. Okay, anyway, still I am very fast. I'm going quickly, but still it is taking time. It's a lengthy subject, right? Okay, anyway, go through this question. Question number 2. A 3-phase 4-pole 400 volt 50 Hz star connected induction motor has the following circuit parameters: R1 given, R2 given, X1 given, X2 given, even magnetizing reactance Xm is also given. What is the starting torque when the motor is started using direct online method, that is DOL method? Simple question. This is a 2 marks question, guys. DOL method means you apply rated voltage at the time of starting. I need what is the starting torque. But the difficulty in the question is magnetizing branch parameter is also given. Okay, so that means a shunt branch also we have to consider. Therefore, we have to apply Thevenin theorem to simplify the circuit. Okay, this was in GATE 2006. Okay, but nowadays, due to the introduction of virtual calculator, complex calculations becomes difficult. So mostly this shunt branch will not be given, but at least one problem we have to solve it in this manner. So first let's draw the circuit. Yes, all parameter, but one word is given at the end of the question. What is that? Use approximate equivalent circuit model. That word is given. What is mean by approximate circuit model? That shunt branch you can neglect. If you neglect shunt branch, we will get exact answer or nearest answer. Nearest answer we will get. As the question is multiple choice type, it is easy to select that nearest answer. But if you wanted to have exact answer, you have to consider that shunt branch parameter also. Okay, let me draw the circuit. R1 given, R2 given, X1, X2 are given. 1.5, 1.2. Okay, so if I draw the exact circuit diagram, this is R1, this is the stator reactance X1, this is the magnetizing reactance Xm, this is the rotor branch R2 dash. At starting there, we need to calculate starting torque. Starting means slip equal to 1, reactance X2. Okay, this is the voltage V1. Now remember, this is actually slip, guys, but slip equal to 1 at the time of starting. What is the torque formula? Air gap power by omega s. This is the formula I have to use because complete circuit diagram was considered. Air gap power means it is a power drawn by resistance R2 by S. I need this power. To find out power drawn by this particular element, I need current in this circuit, I2 dash. To find out current, what I need to do, I have to first make it like a single loop circuit. To make it like a single loop circuit, I have to apply Thevenin theorem, right? Yes, by using Thevenin theorem, any equivalent circuit can be represented like a single voltage source in series with impedance. Therefore, between node A and B, apply Thevenin theorem. Therefore, find out Thevenin impedance, Thevenin voltage. Then you will get exact answer. But if you want approximate answer, simply remove this shunt branch. You'll get current. Current is equal to voltage by impedance. The moment you know current, 3I2 square into R2 will give you the air gap power. Air gap power by omega s is the torque. Okay. So, as it was a 2 marks question, I'll try to find out Thevenin impedance. How to find out Thevenin impedance? To find out Thevenin impedance, first I have to make this voltage source 0. Then calculate the Thevenin impedance between these two elements. Then is it not the parallel combination of these two? So Thevenin impedance is equal to parallel combination of R1 plus JX1 in parallel with JXM. Okay, what is R1 value in the question? R1 is 1, X1 is 1.2, XM is 35. Okay, this is 1, this is 1.2, this is 35. So you know how to calculate Thevenin impedance. It is a parallel combination of the two. Directly I will do it. But I told you, please solve it when shunt branch is neglected. That is the quickest way. Okay. So 1 plus, first I have to keep it in complex mode. 1 plus 1.2i into so I'm getting Thevenin impedance 0.934, okay, plus J 1.18 ohm. This is the Thevenin impedance. What about Thevenin voltage? Thevenin voltage means you have to apply V1 here. Then Thevenin voltage is the voltage across this impedance. What is the voltage? Total voltage V1 into JXM divided by total impedance. What is V1? That is the rated voltage. How much is the rated voltage? 400 is line. Therefore, phase voltage will be 400 by root 3. This is 400 by root 3 into the impedance J35 divided by 1 plus J36.2. Okay. You will get Thevenin impedance also, Thevenin voltage. 35i divided by 1 plus 36.2. Yes, I am getting 223.19 at some angle 15.8 degrees. This is going to be the Thevenin voltage. Now I have Thevenin voltage with me, Thevenin impedance with me. I can draw a Thevenin circuit diagram. So this is the Thevenin voltage, Thevenin resistance, Thevenin reactance, then rotor resistance, rotor reactance, Okay, as it is a starting condition, slip equal to 1. So find out the current directly. It is the Thevenin voltage by overall impedance root over R Thevenin plus R2 dash whole square plus X Thevenin plus X2 dash whole square. What is the Thevenin voltage? 223 we got, right? So directly this is 223.19 by what is R Thevenin plus R2 dash whole square. What is R Thevenin? We got 0.934. R2 is given already, right? What is R2 value? 0.5. Okay, 0.934. 0.934 plus 0.5 plus 0.5 whole square plus X Thevenin 1.18 plus X2. Is it not 1.2? Yes or not? X2 is also 1.2 whole square under root 2.277. Yes, I got current is equal to 80.32 ampere. Directly I'm writing 80.32 ampere. Okay. Please remember, guys, I am solving completely, but I requested you to solve it by neglecting the shunt branch. You got my point? Okay. I am solving it completely, but you can solve it by neglecting the shunt branch. Okay. So the moment I know current, I can find out air gap power now. Air gap power is equal to 3I2 square into R2. So 3 into current is 80.32 square into a rotor resistance 0.5. Correct? Rotor resistance is 0.5. This is the air gap power at starting. This is all at starting, guys. Okay, how much is this? Square into 3 into 0.5. So I'm getting 9678 watt. And divide this air gap power with synchronous speed, I will get the torque. 9678 by what is the synchronous speed? 4 pole 50 hertz. Is it not 1500 rpm? Converting into radian per second, that will be 157. Divided by 157. I'm getting 61.64 Newton meter. Therefore, the correct answer for this question is nearest value. 63 is the correct answer. They said take approximate calculation. If you take approximate calculation, you will definitely get that 63.6 Newton meter. Okay. At the end of the question, they asked us to use approximate circuit model. If I use approximate circuit model, that shunt branch can be neglected. I will also solve that way. Simply you can get the answer. What if a shunt branch is neglected? You will have R1, X1, R2 dash and X2 dash only. Shunt branch is neglected. This is V1. Okay, what is the current now? Directly. So current is equal to simply voltage by impedance. I will directly do it. Okay, I don't want to write down again. Voltage is 400 by root 3. R1 1 ohm, R2 0.5, X1 X2 1.2. Okay, so this is 400 by root 3. Okay, so let's directly solve it. 400 by root 3, 230.94 divided by R1 is 1 ohm plus R2 is 0.5, X1 plus X2 both are 1.2. So I'll get the current now. Yes, let's see. 1.5 square plus 2.4 square under root 230.94 by I'm getting 81.59 ampere. This is the current. If you know the current value, find air gap power. 3I2 square into R2 dash. You may wonder why, sir, what happens to slip? Slip equal to 1 because the answer I need is starting torque. Okay. So therefore, square of this current into 3 into 0.5. So this is 9987.50 watt. Now divide this air gap power with synchronous speed, I will get the torque. 9987.50 by 157. By 157. I'm getting 63.61 Newton meter. Is it what the option? 63.6 Newton meter. And that is the exactly same answer I got here. Okay, this is if I take approximate circuit or exact circuit. Approximate circuit. What is if I take an exact circuit? I'm getting 61.64. Do we have a huge difference or very minor difference? Very minor difference. Okay, very minor difference. If I take exact circuit, but what is the difficulty? If you take the exact circuit, solution becomes lengthy because you have to solve it using Thevenin theorem. The solution becomes lengthy. That's why take approximate circuit, we will get the answer. Approximate circuit means the shunt branch is neglected. I hope all of you get this point. Okay, these kind of questions are boring to you, I know, but these are important. Okay, at the end of the question it was clearly given use approximate circuit, that's why I'm using it. And why I am not considering a slip in the problem? Because I wanted to find out starting torque, and we know at the time of starting slip equal to 1. Okay, right. The answer is 63.61 Newton meter. See how important calculator usage here. If you are very quick using a calculator, these kind of problems you can solve very, very easily. If you are slow substituting values in calculator, this single problem will take 5 minutes for you. Okay, calculator usage is extremely important. Okay, I am right now using a normal calculator, but that is not possible for you in examination hall. You must use a gate calculator only. Okay, right. Okay, some simple questions are there. Let's answer this one question out. This is a common data question. One question we will answer. Go through this data and answer question number 3. All of you. Last question in starters. Then we will go to speed control. Come on. Read that problem. A 3-phase squirrel cage induction motor has a starting current of 7 times the full load current and a full load slip of 5%. See, starting current means ISC. ISC is 7 times of full load current and a full load slip is 5%. Now, if an auto transformer is used for reduced voltage starting to provide 1.5 per unit starting torque, the auto transformer ratio X is equal to how much? Indirectly, the question is all about to find out X value. Let's understand the data given. Starting current is 7 times the full load current. That means ISC is equal to 7 times IFL. Full load slip is 5%. Now we need starting torque to full load torque of 1.5 per unit ratio. Then what is the X value? I told you the direct formula. Yes, what is that? Starting torque divided by full load torque is equal to X square into ISC by IFL whole square into SCFL. What is our requirement? Starting torque to full load torque ratio must be 1.5 and the starting current is 7 times of full load current. And what is a full load slip given? The full load slip is 5%. Okay, the full load slip is 5%. So IFL will cancel. So 1.5 is equal to X square into 49 into 0.05. Find out X value. Very simple question. Find out X value. You can find the answer, right? Yes. What is answer? By 49 into 0.05. I'm getting 0.7824. 0.7824. Therefore, we need percentage tapping 78.25%. That is what? 78.25%. All right. Simple. There is one more question also with the same data. If a star delta starter is used to start this induction motor, what is the per unit starting torque will be? If a star delta starting torque is used, what is I have to do? I told you star delta starting method means it is equivalent to auto transformer starting method, with percentage tapping 57.7%. That means in place of x, you just substitute 0.577. Okay. Therefore, what happens for the same question? What is the ratio of starting torque to full load torque if a star delta starting method is used? Okay. Just substitute everything. So now x equal to 0.577, and this is 7 times of full load current, and the full load slip was 5%, 0.05. So therefore it is 0.577 square into 49 into 0.05. That would be the ratio. Substitute. Yes, I am getting 0.8156. So that is the ratio from starting torque to full load torque. This question, right? Second option, 0.816. That is what we got. Okay. Clear? Yes. We have many questions like that related to starters. You please practice the remaining PYQs also. Simple. Just a moment, guys. Okay, so this is about starters, different types of starters that we have in induction motor. Yes, guys, see, you can also use the logic, that is what I told you. As the starting current is very high, the shunt branch current can be neglected. That is why in the end of the question itself, it is given use approximate calculation only. Okay. But what if that question is a NAT type, numerical answer type question? If the same question is a numerical answer type question rather than objective type, for example, the doubt is about this question, right? Yeah, this question, second question. For example, the same question is given in the next gate exam, only the numbers are modified. But that question was given for numerical answer type, NAT type. Also, I am not using this last word. I am not using this word. Use approximate equivalent circuit model. I am not using. I gave the question for 2 marks. XM was also given. Numerical answer type question. If it is objective type, what you can do? You can take that approximation and you can choose the nearest answer. Fine. But if it is a numerical answer type question, that too XM is given, then exactly you have to solve it, right? To get the exact answer, nearest answer. That is where Thevenin theorem can help you. That is why I solved it. Okay, at least some of you might find it useful. Okay, but for this particular question, it is clearly given approximate circuit. So you can neglect shunt branch, solve it quickly. Even if it was not given, as it is objective type model, you can still neglect it, choose the nearest answer. But nowadays, this is GATE 2006 question. But nowadays questions are numerical answer type, right? These kind of questions. So to get exact answer, you must use Thevenin theorem. Okay. All right. Okay, there are many questions related to starting methods. Starting methods is an important topic. I request you to practice the remaining questions also. Okay, so let's move to the next topic, speed control topic. Speed control of induction motor. Speed control of three-phase induction motor. There are many methods available to control the speed of induction motor. Okay, the theory part is not required for us. For us, how to solve numerical questions is important. There is nothing theory left, available in speed control methods. Most of the methods are related to the numerical questions. Okay, so first of all, there are different types of methods. The most important method is V by F control method. Okay, by controlling both voltage and frequency, how to control the speed of the motor. See, the advantage of this method is speed can be controlled above rated value as well as below rated value. Both are possible. Speed can be controlled above the rated value as well as below the rated value. But one important observation in speed control method is, we know flux density is always proportional to V by F ratio, especially when you are controlling frequency. For example, what happens if frequency is reduced by keeping voltage constant? If I do that, if frequency is reduced keeping voltage constant, flux density will increase, right? If flux density increases, core may reach magnetic saturation. If magnetic saturation is reached, what is the problem? Even for a small rise in flux density, a large amount of magnetizing current will be drawn. Therefore, machine may overheat and that may damage the machine permanently. That is why what we need to do, whenever we wanted to reduce frequency, reduce the voltage also, keep this V by F ratio constant. So when I say V by F ratio is constant, indirectly flux density will be constant, and that is how we can avoid magnetic saturation. But the same thing is not required when you are increasing the frequency. When we are increasing the frequency, no need to increase the voltage. For example, if I increase voltage, what will happen? Insulation will damage. Never increase voltage beyond rated value. If we apply voltage beyond rated value, insulation may damage. That's why when it comes to increasing frequency, increase the frequency only, don't increase the voltage. Keep the voltage constant. You better keep the voltage constant. Then flux density will decrease, right? Decrease in flux density is not a problem at all. It won't create any saturation. But increase in flux density is dangerous. This is one important rule we have to follow in V by F control method. Okay. Next, we have rotor resistance control method also. Rotor resistance control method. As the name itself is indicating, in this method, we will add additional resistance into the rotor. By adding additional resistance into the rotor, we will try to control the speed of the motor. Okay, but this method is possible only to control the speed below the rated value. Below rated speed only. We can't control the speed above the rated value. We can only control the speed below the rated value. Yes? Clear? Below the rated value. Next, we have variable voltage control method also. We have variable voltage control method. In this, as the name itself is indicating, only voltage will be modified. Frequency does not modify. Only voltage we will modify. That is, just by using an auto transformer, we can control the voltage, right? And this method is also used to control the speed below rated value only. You can't control the speed above the rated value. So to control the speed above rated value, we need V by F control method. These are the important speed control methods. There are many methods also. We need not to discuss all those things, but these are the important speed control methods. And we will try to answer a few questions so that how speed control is exactly possible in induction motor. Okay. Right. Yeah. We will start with this question. Question number 1 here. One more question. Just go through it. That is in GATE 2014 exam, set 2. You should not use voltage division. Okay, I don't know your name, Winter Child. Okay, It is not voltage division. You have to use Thevenin theorem, not voltage division. Voltage division you can use only if you have series branches. But when you have both series and shunt branches, then we have to use Thevenin theorem to simplify that circuit diagram, right? Yeah. Anyway, go through that first question, 1 mark question. In a constant V by F control of induction motor, the ratio V by F is maintained constant from 0 to base frequency. Remember, base frequency means it is rated frequency. Okay, from 0 to base frequency, where V is the applied voltage of the motor at fundamental frequency. Which of the following statement relating to low frequency operation of the motor is true? The question is about low frequency. Low frequency. At low frequency, stator flux increases from its rated value. At low frequency, stator flux decreases from its rated value. At low frequency, the motor saturates. At low frequency, stator flux remains unchanged at its rated value. Okay, the question is about low frequency, a very low frequency. Okay, yes, try to answer this question. Anybody? Yes, any answer? Come on. So in a constant V by F control of induction motor, the ratio V by F is maintained constant from 0 to base frequency. When V is the voltage applied to the induction motor at fundamental frequency F, which of the following statement relating to low frequency operation of the motor is true? Yes. At low frequency, stator flux increases from its rated value. Remember, V by F is maintained constant. Please don't forget that. V by F is maintained constant. V by F ratio is maintained constant. Okay. V by F is maintained constant. Therefore, there is no saturation concept here. There is no saturation concept. Okay, let's see how to answer. This is a typical question. You see that in a constant V by F control of induction motor, V by F is maintained constant from 0 to base frequency. V is the voltage applied to the motor at fundamental frequency. Which of the following statement relating to low frequency operation of the motor is true? For example, this motor is connected to a constant torque load application. Just imagine. Okay. What is the torque equation? 3 by omega s into I2 square into R2 by S, or voltage in terms of voltage if I write. In terms of voltage, E2 square divided by R2 by S whole square plus X2 square into R2 by S. They are talking about very low frequency. At very low frequency, can I say reactance is also going to be very less, because reactance is a term dependent on frequency. At very low frequency, reactance is going to be very, very less. If reactance is very, very less, X2 square can be neglected, right? If X2 square is neglected, 1 R2 by S will cancel. So torque will be 3 by omega S into E2 square by R2. Okay. Now just imagine the machine is driving a constant torque load. I'm saying torque load is not disturbed. R2 is a fixed value because we are not disturbing resistance also. Omega s is dependent on frequency. So slip is proportional to F by V square. Okay. Therefore, S is proportional to, take frequency to the denominator, then it is V by F into V. V by F is constant. So slip is inversely proportional to voltage. This is one equation I got. Next one, I would like to write down the same torque equation in terms of current also. I2 square into R2 by S. Okay. Here R2 is constant, torque is constant, omega S is proportional to frequency. So I2 square is proportional to frequency into slip. Already I told you that slip is inversely proportional to voltage. We proved it, right? Slip is inversely proportional to voltage. Okay, so I2 square is proportional to 1 by V by F. V by F ratio was constant. That means I2 is constant. Current is constant. Motor is drawing same amount of current. But the question is not about current, not about voltage, not about torque. The question is about what? The question is about, does the machine flux will change or does not change? Okay. Yes. The question is about flux. Okay. Current is constant, right? Now, if you draw the equivalent circuit, right? This is the equivalent circuit of the induction motor, right? So this is R1, this is X1, this is XM, this is R2 by S, this is X2. Okay, this is the equivalent circuit. Now this is the supply voltage, this is the current. Okay, current drawn by the motor. Now the point is very simple. At low frequencies, reactance is neglected because frequency is very low and voltage is very small. Why very small? Because I said V by F ratio was constant, right? When I say V by F ratio was constant, frequency is very low, indirectly voltage is also very low. But current is a low value or current is constant? Current is constant. Because the current is constant, what happens? More voltage will drop across this resistance itself. More voltage will drop across this resistance. Most of the students does not get this concept, I know. Okay. Most of you select flux remains constant, but that is a wrong answer. That is absolutely wrong answer. You see the explanation. Voltage, supply voltage is very small, but current is kept constant. Therefore, more voltage will take place, more voltage drop will take place at the resistance itself. Where most of the voltage drops at the resistance itself, the applied voltage is almost neglected. The voltage across this impedance will be negligible. That is indirectly the induced EMF. The induced EMF is neglected. When I say induced EMF is neglected, indirectly what is the meaning of it? The flux is negligible. Flux is negligible means very low. The flux is very low. The flux is very low. This is a strange concept and very important and valid for this question only. The question is about low frequency. When frequency is, but current is not changing, please remember that. If voltage is rated value, then sufficient amount of voltage will induce inside the machine. But already I am applying a very small voltage. Okay, out of that small voltage, most of the voltage will drop in the resistance only, machine winding resistance, because current is the same, voltage drop doesn't change. If most of the voltage drops here, how much voltage will induce inside the machine? A very small voltage will induce. And we know induced EMF will depend upon the amount of flux inside the machine. And the voltage is very small, that indicates the amount of flux is also going to be very, very small. So the correct answer is the amount of flux will be very small. At low frequencies, the stator flux decreases. Second option will be correct. Second option will be correct. At a low frequency, stator flux decreases from its rated value. Okay. If it is slightly reduced frequency, no problem. But at very low frequencies, this is going to happen. The flux will be decreased. The stator flux will be decreased. Okay. Clear. I saw many videos related to this question. Most of the faculties explained that flux is constant because V by F ratio was constant. But the exact answer is flux will decrease. This will happen at very low frequencies. I hope you get the answer, right? Induced EMF will be very, very low because the flux is very low. You cannot maintain flux constant at very low frequencies. Most of the voltage will drop in the series resistance itself. That's why very low frequency will appear. Very low frequency will appear. Okay? Yes. Yes, the answer is B. It is not D. You have to correct it. The option is not matching. Okay? Okay. Next, we will try to answer one more question. Yes. Go through question number 2. That's a simple question. Slip at maximum torque. You remember SMT. SMT formula. What is the formula for SMT? SMT is equal to R2 by X2. Therefore, SMT is inversely proportional to frequency. Correct? Yes. Direct question. SMT is inversely proportional to frequency. So it has inverse relation with frequency. Inverse relation with frequency means indirectly inverse relation with synchronous speed also. Okay. Then we will answer some 2 marks questions. Okay. You go through question number 2. First question is easy. Go through question number 2. 2 marks question. Question number 2. Yeah, make it fast. The speed of a 4-pole induction motor is controlled by varying the supply frequency while maintaining the ratio of supply voltage to supply frequency constant. See, V by F ratio constant. At rated frequency of 50 Hz and rated voltage of 400 volt, its speed is 1440 rpm. Find the speed at 30 Hz if the load torque is constant. Direct question, guys. 2 marks question. Simple question also. Initially, frequency was 50 Hz, voltage was 400, speed is 1440 rpm. Now, what is the new speed if the load torque is held constant? Remember, to find out new speed, first we have to find out what is the new slip. Okay, for that the condition given is load torque is kept constant. Okay, so first let us find out a slip in the first case 1440 rpm. So in the first case, voltage was how much? Voltage was 400, frequency 50, right? So voltage was 400, frequency is equal to 50 Hz. So what is the synchronous speed? It is 1500 rpm. A rotor speed is equal to 1440 rpm. What is the slip corresponding to this? The slip is equal to, where is the calculator? 1500 minus 1440, I think 0.04, right? 1500 minus 1440 divided by 1500, 0.04. This is a slip in the first case. Given the torque is constant. In the next case, what happened? In the next case, frequency was changed from 50 Hz to 30 Hz. V by F ratio was constant. This is given in the problem. What is the new slip? If you find a new slip, automatically we can find out new speed. Correct? For that, the condition given in the problem is torque is constant. This is the condition. Okay. What is the formula for a torque? Torque is equal to 3 by omega s into E2 square divided by R2 by s whole square plus x2 square into R2 by S. We know R2 by S whole square is very high compared to x2 square. So x2 square can be neglected. Then 1 R2 by S will cancel. The approximate torque equation becomes 3 by omega S, S into E2 square by R2. Correct? Now the given point is torque is constant, resistance is constant, no change. So slip is directly proportional to F by V square because synchronous speed directly proportional to frequency. You take F to the denominator, then S is directly proportional to V by F into V. V by F is constant. So S is inversely proportional to V. That means inversely proportional to frequency. When I say V by F ratio is constant, V and F are proportional. So if S is inversely proportional to frequency, first case slip divided by second case slip is equal to second case frequency by first case frequency. What is the slip in the first case? 0.04. You have to find out what is the slip in the second case. The answer will be 50 by 30 times. I am getting new slip 0.066. If I know this is a new slip, can I find out what is a new speed? What is the formula for NR? NR is always equal to 1 minus S into NS. 1 minus 0.066 into NS 120 F by T. F is 30 Hz, remember. So if I substitute, yes, I'm getting 840 RP. Just check this. Please correct if I made any mathematical mistakes. Yes, the correct answer will be 840 RPM. The new speed will be equal to 840 RPM. Okay. I'm expecting you are solving. Quick mathematics is very important. If you are getting answers slowly, means your calculator usage is not so perfect. Calculator usage is extremely important in gate level exam. It is not only about concepts, it is about using calculations quickly. Okay. Yes. When you are calculating new synchronous speed, don't forget that frequency was 30 Hz only this time. So the new speed was 840 RPM. Okay. Right. 840 or 846? Whatever. Nearest answer. So 840, option C is the correct answer. Option C. Okay. That's all, guys. Speed control problems. I am not discussing single phase machine. I don't have time to go for that. All right. I request you to study single phase machines. Okay. Also. So we don't have time. We will go to the next machine. Please let me know which machine would you like me to discuss next. Which machine do you want me to discuss next? Another 4 hours we will try to spend. Already it is 5 hours. Maximum 3 to 4 hours we can spend. I'll take one more session for the remaining 2 machines. Please let me know if you vote. Then I'll try to discuss that more. Oh God. Guys, there was a power break also. Power was lost. My system was working on UPS right now. Let's see whether power will restore or not. సాయి, అరే పవర్ పవర్ పోయింది బయట కూడా. ఆ? ఎప్పుడు వస్తుంది మళ్ళీ? సెషన్ మధ్యలో ఆగిపోయిందిరా. ఒకసారి ఫోన్ చేసి సార్కి తెలుస్తుంది. నైట్ ఏమన్నా ఈరోజు ఏమైనా పవర్ కట్ ఉంది అక్కడ? స్టూడియోలో ఇది యూపీఎస్ కూడా అయిపోతుంది ఛార్జింగ్. లైవ్లో ఉందా? గైస్, దెర్ వాజ్ ఏ పవర్ కట్ ఎట్ మై స్టూడియో లొకేషన్ రైట్ నౌ. వచ్చిందిరా. యా ఇట్ వాజ్ రీస్టోర్డ్. Okay, so based on the poll, I think most of the students wanted me to discuss synchronous machines. Okay, we will start synchronous machines. Yeah. So meanwhile, take a short break, then we will continue. Okay. Take a short break, we will continue. Synchronous machines next. Take a break for 20 minutes, then we will come back again. Yes, take a break for 20 minutes, then we will start synchronous machines next. All right. All right, welcome back to the next session. Yes, please correct it. It's not option D, it is option B. I told to other student also. Yes. If it is reduced frequency, then B is, constant flux is the correct answer. But at very low frequency, the flux will be reduced. Okay, because of more voltage drop in the series resistance. Please correct it. No problem. You see the official gate key, then you will find it. Okay, anyway. So let's move to the next topic. Okay, synchronous machines. As it is a quick revision session, I'll go in a different way. Okay, like see, especially in synchronous machine subject, most of the concepts are very similar in synchronous generator as well as in synchronous motor. Okay, so once I cover the basics, then every topic we will try to discuss for generator as well as motor. Phasor diagram of generator, phasor diagram of motor, EMF equation of generator, EMF equation of motor, like that. Okay, fine. So coming to the basics, first of all, if I'm talking about a synchronous generator, we also call it as alternator. So what is the basic operating principle? Faraday's law of electromagnetic induction, right? What Faraday's law states that according to Faraday's law of electromagnetic induction, whenever a conductor is moving in a time invariant magnetic field, it will experience changes in flux linkages so that an EMF will be induced across it, and the magnitude of that induced EMF is equal to BLV sine theta. Okay, so this is according to Faraday's law of electromagnetic induction. This is the operating principle both for DC generator as well as a synchronous generator. Whenever a conductor is moving in a time invariant magnetic field, so we need time invariant field. Time invariant field. What is mean by time invariant field? Time invariant field means the magnitude of flux will be constant with respect to time. That is like a DC flux waveform. Yes or not? And what is the formula for flux? Flux is always equal to MMF divided by reluctance, where MMF is nothing but number of turns multiplied by current. From this formula, flux is directly proportional to current. And if I wanted to create a DC flux, in a machine, if the flux wanted to be DC, then we have to excite that field system with DC current. So when you excite the magnetic field system with DC current, then the flux will also be in DC nature. DC means what? Time invariant in nature. Time invariant means it is constant with respect to time. Therefore, in a synchronous machine, the field system will be always excited with DC supply, so that the magnetic field will be time invariant. And in that time invariant field, if I move a conductor, what will happen? It will experience changes in flux linkages so that an EMF will be induced across that conductor. Okay. So now, so point is very simple. So let us come to the point. So synchronous machine will have two windings. One is stator, another one is a rotor. Okay. This stator winding is known as armature winding. This is armature winding. The rotor winding is known as field winding. And as I mentioned, this field winding is excited with DC current. All right. So when you give DC excitation, what will happen? Time invariant field will be created. Time invariant field will be created. Now, this time invariant field will be linking the armature winding. Okay. So when it is linking armature winding, AC voltage will be induced in this armature winding. Even though magnetic field is a time invariant, but the kind of voltage that will induce inside armature winding will be AC voltage. I'm not trying to prove it. In the regular class we will discuss by using Fleming's right hand rule. We will find out the polarity of EMF. And then you see, for example, if you take a simple example, like imagine we have a north pole and a south pole here. Okay. and I am rotating a conductor in this particular direction. I'm keep on rotating. When the conductor was here, it is under which pole? South pole. Let us say under south pole, negative voltage is induced. Under the same conductor, once it comes to north pole, a positive voltage will induce. Because north and south are two opposite polarities or two same polarities, two opposite polarities. Again, south pole is negative voltage, north pole positive voltage, negative, positive, negative, positive. Therefore, what is the type of voltage that will induce? Negative, positive, negative, positive, negative, positive. Therefore, the kind of voltage that will induce across this armature winding will be AC voltage. Okay, but the magnetic field is DC. The field system, that means this north pole and south pole were excited with DC supply. But when you rotate the conductor, AC voltage will be induced. Okay, in regular class we used to study how that will happen, but here we are just discussing the basics. So in armature winding, AC voltage will be induced. This AC voltage will generate AC current. Okay, that's why this is known as alternator. Okay, that's why it is called as alternator. It was generating alternating voltage by using which type of field? Time invariant field. Okay, and as the name itself is indicating, rotor. So therefore the field is rotating in nature. Armature will be stationary in nature. If you apply the same concept to DC machine, armature will be rotating in nature, a rotor field will be stationary in nature. Okay, so let us understand what is the situation. Okay, further. Okay, how this is simple basic only. Okay, I'm not going through construction. This is not possible. This is not the time to discuss about construction, but few points in the construction that will help us to understand the subject. There are two types of synchronous machines, right? One is salient pole rotor synchronous machine. Another one is cylindrical rotor synchronous machine. For example, imagine this is the stator part of a given synchronous machine. This stator will have three-phase distributed winding. Okay, usually that is three-phase distributed winding will be a star connected winding. Most of the times stator is star connected. What is the advantage of star connection? Yes, star connection will have higher output line voltage compared to delta connection. Okay, also by using a star connection, third harmonic induced EMFs can be neutralized. Okay, I'm not writing that, but you try to understand. Star connection will have higher output line voltages. For example, in a star connection, if each phase voltage was V, then what is the line voltage will become √3 into V. If you use a delta connection, if each phase voltage was V, then line voltage will also be V only. Okay, that is why to generate higher output line voltage, normally we will go for star connection. Also, third harmonic voltage cannot present in the line values. For example, if every phase is having a third harmonic voltage, but the line voltage, the third harmonic voltage will be equal to 0. The lines do not have a third harmonic voltage. Only fundamental voltage, fifth harmonic and seventh harmonic will be available. So harmonic voltage is neutralized. That is an advantage or disadvantage? Definitely an advantage. This is the reason why stator is always star connected. Stator is star connected and there are three output line terminals. This is stator. Let's say this is phase A winding, A and A dash. After 120 degrees, we will be having B and B dash. After one more 120 degrees, we will be having C and C dash. Three-phase distributed winding, that is a stator. We call it as armature indirectly. This is the armature part. Now inside this, we have a rotor. See, I am considering a two-pole rotor right now. This is a rotor. And this rotor will have a field winding. And this field winding will be excited with the help of DC supply. This is a field voltage and this is the field current. Based on the direction of a field current, you can identify the direction of a field flux. Can I say the field flux is in upward direction? Yes. The field flux is in upward direction. Okay, I just used right hand thumb rule, right? Right hand thumb rule you can use to identify the direction of field flux. Can I say field flux is in upward direction? That means this pole is emitting the flux. Therefore, this is a north pole. This pole is taking the flux. This is a south pole. Okay. All right. And this type of structure is what we call it as salient pole rotor structure. And remember, this is a rotating body. Rotor is a rotating body. And we will rotate the rotor at synchronous speed exactly. Why we are rotating the rotor exactly at synchronous speed? Because the frequency of induced EMF in a synchronous machine is always equal to P into N by 120 Hz. That is the frequency of induced EMF. And in power system, we need constant frequency or variable frequency, constant frequency, that too 50 Hz, rated frequency. So the speed at which rated frequency is generated, that is what we call it as synchronous speed. Therefore, the rotor is rotated exactly at synchronous speed. Then only rated frequency can be generated. If we rotate at low speed, what will happen? Frequency will be less frequency will be generated. Got it? And this type of rotor is what we call it as salient pole rotor. And the salient pole rotor will have uniform air gap length or non-uniform air gap length. Non-uniform air gap length. You see, this is the axis which is passing through the poles, right? This is what we call it as the direct axis of the machine or polar axis. Any word you can use. And along this direct axis, minimum air gap is available or maximum air gap is available. Minimum air gap. The air gap length is minimum. And this is the perpendicular to D axis. We also call it as quadrature axis of the machine. And along the quadrature axis, we have a maximum air gap length. So the air gap length is non-uniform. Okay. Minimum air gap length along direct axis, maximum air gap length along quadrature axis. Such design is known as salient pole rotor design. This is known as salient pole rotor design. Salient pole rotor design. Okay. And this salient pole rotor design is used for which applications? Low speed applications only. Low speed applications, typically water turbines we will use. Why speed has to be very low? Because non-uniform air gap length is there. So if you try to rotate rotor at very high speed, more forces will create on the rotor shaft, centripetal forces. The rotor shaft may damage permanently. So it is used only for low speed. Because the speed is low, we need more number of poles are required. More poles required. Why? Because in power system, frequency must be always constant, right? What is the formula for frequency? P into N by 120. When I say frequency is constant, indirectly the speed is inversely proportional to poles. And to operate the rotor at low speed, we need more number of poles for this machine. Okay, so salient pole rotor is designed with more number of poles. And in order to accommodate more number of poles, we need larger cross-sectional area with less axial length. Okay, so larger cross-sectional area with less axial length. Okay, so we need larger cross-sectional area with less axial length. If the cross-sectional area is large, then only more number of poles can be accommodated on that particular, magnetic core. This is about salient pole rotor machine. We will mainly use for low speed applications, indirectly hydro power plants, water turbines. And also remember, this salient pole rotor will also have damper winding bars on the surface of the rotor. Damper bars will be available. All these damper bars are short circuited to each other. Okay, number of damper bars will be available. All these damper bars are directly short circuited to each other. Damper winding we call it as. And damper winding will have two main purposes in a synchronous machine. One is to reduce hunting problem. Another one is to create starting torque for induction synchronous motor. We will see very soon, synchronous motor is inherently not a self-starting motor. In order to make it as a self-starting motor, we will use this damper winding. Okay, so damper winding will be located on the surface of the pole shoe and all the damping bars are short circuited directly. Clear? It will be used to reduce hunting and also to create a starting torque for synchronous motor. Okay. Then there is another type of rotor practically possible. Okay. cylindrical rotor, also known as non-salient pole rotor. Non-salient pole or simply cylindrical rotor type. Okay. So as the name itself is indicating, the rotor will be a circular rotor this time. Okay. So imagine this is the stator part of the machine. Stator will have a three-phase distributed winding. Okay. Typically it is star connected. Okay. Stator winding. And coming to the rotor is also a circular cross section. The rotor will also be a circular cross section. Okay. And this rotor will have a number of slots here. And in those slots, the field winding will be located. These are field conductors. Field conductors. Okay. And we will excite these field conductors using a DC supply. For example, these are carrying the current into the plane and these are carrying the current out of the plane, field current. Then what will be the direction of a field flux? Upward direction. Okay. If the field flux is in upward direction, this surface of the rotor will act like north pole, this surface of the rotor will act like south pole, and this is how the direct axis will be. This is the direct axis, the axis passing through the pole. And perpendicular to that, we will have quadrature axis. Okay. And whether it is a direct axis or quadrature axis, can I say air gap length is going to be uniform? Whether it is direct axis or quadrature axis, the air gap length will be uniform. So as air gap length is uniform, we can operate this rotor for high speed applications. High speed prime mover applications means generally thermal power stations. Okay, steam turbines. If the prime mover is a steam turbine, that is in thermal power station as well as in nuclear power plants, steam turbines are used, which are high speed turbines. Therefore, for high speed, we will use cylindrical rotor machine. Okay. Yes, high speed means less number of poles. Less number of poles. I already told you when frequency is constant, speed and poles are inversely proportional. If speed has to be high, number of poles requirement will be less. Okay, to accommodate less number of poles, we need less cross-sectional area. Less cross-sectional area with more axial length. As cross-sectional area is reduced, axial length requirement will increase. Okay, because for a given size, if area is reduced, axial length will increase. Okay, so with more axial length. With more axial length. Okay, now the next question here, what about damper winding in this machine? In case of salient pole machine, damper winding has a separate space, right? On the surface of the pole should be located. But in a cylindrical rotor machine, where is the damper winding? First of all, you don't need damper winding for cylindrical rotor machine. The distributed field winding will act like damper winding. Okay, we don't need separately a separate third winding, damper winding. The distributed field winding itself will act like damper winding. Then why that is not happening in a salient pole machine? Because in a salient pole machine, field winding is a concentrated winding. It cannot, create hunting problem, synchronizing torque to reduce hunting. But whereas in a cylindrical rotor machine, the field winding is distributed winding. So because it is distributed winding, it can create a synchronizing torque during the hunting problem. So the field winding itself will act like damper winding. Okay? Field winding acts like damper winding. We don't need a third separate winding for damping purpose. Okay, that is about cylindrical rotor machine. Air gap is uniform. In a salient pole rotor machine, air gap is non-uniform. Okay, now coming to the next discussion, EMF equation of synchronous generator. That's about the construction. Important points only I discussed. I'm not going in depth. Okay, so EMF equation of a synchronous generator. Okay, so first of all, if you go through step-by-step operating process, this machine consists of two windings. One is stator winding, another one is rotor winding. The rotor winding will have field winding, right? Imagine this is the field winding available on the rotor, and we are exciting this field winding with DC supply. Field voltage and the current is field current. That field current will create a flux inside the machine known as a field flux. That field flux will cross air gap and link armature winding. Remember, armature winding will be available on stator. Okay, and armature winding is a three-phase balanced distributed winding. I told you it will be always star connected. Now what is happening? Whatever field flux is created by field winding, that field flux will cross air gap and link this armature winding, so that an EMF will be induced in armature winding. We call it as field induced EMF. Field induced EMF. So what is the definition? By definition, field induced EMF means it is the EMF induced inside armature winding due to field flux. That's why we call it as a field induced EMF. Okay, and what is the formula for that field induced EMF? If I go, yes, the formula for field induced EMF will be equal to, I'm directly writing, I'm not deriving, it will be 4.44 into field flux per pole into frequency, number of turns per phase into winding factor, voltage per phase. Remember, even though our armature winding is a three-phase connected, EMF equation is always developed per phase only. That is per phase induced EMF. 4.44 into field flux into frequency into number of turns into winding factor. Here, phi f is field flux per pole. Field flux per pole. The value of field flux per pole. And f is frequency of induced EMF. Frequency of induced EMF. And what is the formula for frequency? Pn by 120 Hz. And T represents number of turns per phase. Number of turns per phase. How many number of turns are available per phase in armature winding? In armature winding. Okay. And then Kw. Kw is known as winding factor. And this winding factor Kw is equal to product of pitch factor multiplied with distribution factor. Important. Winding factor is equal to the product of pitch factor multiplied with distribution factor. What is the formula for pitch factor? Pitch factor is equal to cos alpha by 2, where alpha is known as short pitch angle, right? Short pitch angle in electrical degrees. And what is the purpose of short pitch coils? You know, based on the coil pitch value, coils are subdivided into two categories. Okay. Coils are subdivided into two categories. One is short pitch coil, another one is full pitch coil. But we will always use short pitch coils only. Yes. Rahul, yes, I will discuss the terminology of armature winding, but quickly. In regular class, terminology of armature winding itself will take more than 1 hour, 1.5 hours like that. Here in 5 minutes, 6 minutes, I'll try to conclude it. Okay. You just see the terms. Okay. Complete discussion may not be possible, right? But if you have a basic idea, you can follow. Okay. Right. Yes. So alpha is nothing but short pitch angle. And what is the advantage of short pitch coils? Short pitch coils are used to reduce or to neutralize harmonic EMFs. Remember guys, in rotating electrical machines, the goal is always to make flux purely sinusoidal. But we cannot make it 100% sinusoidal. Always some non-sinusoidal nature will be available. Why? I'm not going into the details. Directly I'm saying flux cannot be purely sinusoidal always. Non-sinusoidal nature will be there. Because of that non-sinusoidal nature, harmonic EMFs will be induced inside armature. And to neutralize higher order harmonics, effective harmonics, we can use short pitch coils. Okay, by using short pitch coils, harmonic voltages can be neutralized. Okay, next, distribution factor. What is the formula for distribution factor? It is sine m gamma divided by 2 by m sine gamma by 2. This is the distribution factor. What is the definition for a distribution factor? See, distribution factor is defined as the voltage of a distributed winding with respect to voltage of a concentrated winding. For example, I have a concentrated winding like this. Best example, transformer. Imagine there are three turns. Assume every turn is having 10 volt magnitude. Then what is the total voltage here? If each turn is having 10 volt per each turn, then what is the total voltage? Because three turns are there, it will be 10 plus 10 plus 10. You add algebraically, you will get 30 volt. This is a situation when the winding is concentrated type. But what if the same three coils are distributed type? For example, I have a circular core like this. Slots will be available, right? Number of slots will be available. Imagine there are three conductors like this. Okay, imagine every conductor is having 10 volt magnitude. Also assume that all the three coils are connected in series. Now what is the total voltage here? Total voltage will be not 30. Guys, I lost the power again. Please wait a moment. Let's see. Power restored or not. సాయి ఉన్నావా? బయట కూడా పోయిందా? సాయి నాకు కొద్దిగా వాటర్ వేడి చేసి గొంతున మంట పుడుతుంది. ఇది అచ్చా. Please be online, so we will see whether power is restored or not. The system was on CPU right now. CPU was working due to battery backup, but digital board cannot work. Camera and all. So let's see whether power is restored or not. Guys, wait for a few minutes. Power is restored. I'll switch on the board. Madhilo button nokku. Yeah. You'll connect in 2 minutes, okay? What table number it is? Okay, thank you. All right, guys. Yeah. So hope my audio was clear, right? Video also clear. All right. Fine. So yes, we are discussing about distribution factor. So the formula for a distribution factor was sine m gamma by 2 divided by m sine gamma by 2. And I'm telling you what is the definition for a distribution factor. So it is the ratio between, yes, distributed winding voltage to concentrated winding voltage. Okay, concentrated winding voltage. And I'm also telling you what is the difference between a distributed winding and a concentrated winding. For example, if you take a magnetic core like this, imagine there are 3 turns. If every turn is having a 10 volt, then the total voltage will be algebraic summation, which was 30 volt. But when the coils are distributed in nature, okay, if every coil is having a 10 volt, you cannot say total voltage will be 30. It will be definitely less than 30. Why? Because I have to add these 3 coil voltages vectorially, because there is a phase angle difference from one slot to another slot. That is what we call it as a slot angle gamma. So what I need to do, I have to add the total voltage like this: 10 at an angle 0 plus 10 at an angle gamma plus 10 at an angle 2 gamma, like that, so on. Vectorially, I have to add them. So, and we all know that vectorial addition will be always less than algebraic addition. So every time we can't do this vector calculation, right? That's why we are deriving this formula. What if I cross multiply this? Therefore, distributed winding voltage will be always equal to Kd times of concentrated winding voltage. Therefore, if you initially assume the winding is a concentrated type, what is the advantage if I assume the winding is concentrated? Algebraic calculations will work, just like a transformer. And then multiply that voltage with Kd so that we will get distributed winding voltage. That is the advantage of using distributed winding. Okay, that is what we call it as distribution factor. Okay, right? And here in this sine m gamma by 2, what is m is known as? Where is the pointer? Yes, here m is known as slots per pole per phase. So m is known as slots per pole per phase. M is equal to slots per pole per phase. Okay. For example, if m is an integer, then we call that winding as integral slot pitch winding. If m is a fraction, then we call it as fractional slot pitch winding. For example, if m is equal to 3, 4, 5 exact integers, then we call it as integral slot pitch winding. If m is a fractional number, 3.2, 3.4, 4.6, something like that, we call it as a fractional slot pitch winding. And always fractional slot pitch winding is used, because by using a fractional slot pitch winding, slot harmonics can be minimized. In regular class, we use it to study that. Okay. Yes. Next, gamma is known as slot angle. Slot angle, and it has a direct formula, 180 degrees divided by slots per pole, electrical degrees. Okay, that is a slot angle. That is indirectly the angle between one slot to the next slot. Angle between two adjacent slots. Okay, right. So if you know Kp and Kd, we can easily find out winding factor. Once we know winding factor, we can find out EMF of a synchronous generator. Okay, right. Now we will discuss about armature reaction in synchronous generator. Armature reaction. Okay, see, armature reaction is effect of armature MMF, effect of armature MMF on main field MMF. On main field MMF. This is what we call it as armature reaction. First of all, there are two windings, right? Armature winding we have, field winding we have. So this field winding is excited with DC supply. It creates an MMF known as field MMF. That field MMF will create a flux known as field flux. This armature winding will experience AC voltage inside it. And when you connect a load, what will happen? That will generate, see, if you connect a load, that will generate an armature current. Okay, that creates armature MMF. That armature MMF will create armature flux. Now the effect of this main field flux on armature flux is what we call it as armature reaction. And what is the nature of armature reaction in synchronous generator? I'm not going to draw complete phasor diagrams. We don't have that much time. We will quickly revise in generator and motor both. For example, if it is a synchronous generator and also synchronous motor, both machines, we will try to understand the nature of armature reaction at different load power factors. Okay, armature reaction will depend upon the load power factor mainly. Okay, for example, if the load is ZPF lagging power factor, remember lagging power factor will create demagnetization effect in synchronous generator, exactly opposite magnetization effect in synchronous motor. Demagnetization effect in generator, magnetization effect in motor. For example, if it is ZPF leading power factor, it will be magnetizing effect in generator, demagnetizing effect in motor. If it is exactly opposite, why? Because generator to motor, the only difference is current flow, right? Generator will generate the current, motor will absorb the current. So in a normal regular class, we use it to prove everything by drawing a phasor diagram, understanding the analysis of the machine, etc. But this is just a revision I am directly writing. For example, if the power factor is unity power factor type, then it is going to be cross magnetization in both machines. Pure cross magnetization. For example, power factor is not completely lagging, not completely unity power factor. For example, if it is a finite lagging, like 0.8 lagging or 0.6 lagging, something like that, then armature reaction would have been partial demagnetization and partial cross magnetization. Partial demagnetization and partial cross magnetization. In motor, exactly opposite. Partial magnetization and partial cross magnetization. Partial cross magnetization. For example, what if a power factor is a finite leading? Okay, like 0.8 leading or 0.6 leading, then in generator it will be partial magnetization and partial cross magnetization. Okay, in motor it will be partial demagnetization and partial cross magnetization. Okay, just to look at this screen, if required you can take a screenshot also. Take a screenshot. That is the effect of armature reaction at various power factors in both generator and motor. You can take a screenshot. Yes, this will help us to answer some of the questions, okay, very soon. Clear? Okay, that is about armature reaction in both generator as well as motor. Clear? Fine. Now, let's try to understand some simple questions related to these basic concepts before moving to the next topic. Just a moment. Okay. All right. See some of the simple questions. I hope it is visible to everybody. Right. Look at the first question. Just read and answer type. See, most of the previous gate questions from synchronous machine, especially 1 mark questions. See, these are all 1 mark questions. Are you finding numerical questions or more theoretical questions? Yes. Most of the 1 mark questions are theoretical type. You can see up to here, these are theoretical questions. 1 mark questions up to question number 24. Combining all topics. All questions are theoretical. See that. Only one question was a numerical type, that is in GATE 2014 from 1 mark. Okay, remaining all are theoretical. So 1 mark questions are mostly theoretical type, especially from synchronous machine subject, because this particular subject is 70% theory, only 30% numerical answer type questions will be there. But to answer those numerical questions, this 70% theory is extremely important. So it's a theoretical subject more or less. Okay. Now let us try to answer few questions based on the topics that we covered so far. Okay, look at the first question. Okay, let me do it. Yes, damper winding is provided in a polyphase synchronous motor. What is the purpose of damper winding? To dampen out the noise of the machine or to prevent hunting, to provide starting torque, provide cylindrical structure to reduce wind friction. Actually, both B and C are correct answers here. You can see B is correct and C is correct. But what is the primary advantage? The primary advantage is obviously to provide starting torque. This is the correct answer. Primary advantage is always the starting torque, because it's a motoring machine, clearly. As it was a motor, rather than reducing hunting problem, it is to create the starting torque. That's why this C is going to be the correct answer. Okay. Yes. If it is a generator, then definitely hunting is the first priority. Next, what is the torque angle? Torque angle of a synchronous machine operating from a constant voltage bus is usually defined as the space angle between what and what. In the morning session, while explaining about induction machines subject also, I wrote basic torque equation. You remember? Basic electromagnetic torque is directly proportional to minus F1 F2 sine lambda. This lambda is what we call it as torque angle. Okay, and that is the angle between stator mmf F1 and rotor mmf F2. These two are separated by a phase angle lambda, and in between the two we have air gap field, and that lambda is known as torque angle, and that is the angle between stator field and rotor field. So the correct answer is, it is the angle between stator mmf and rotor mmf. That is option A. Okay, next. This topic is not completed. One more question. Question number 5. It is gate 96 question related to hunting problem. Read that question. During hunting of synchronous motor, negative phase sequence currents are generated. Harmonics are developed in the armature circuit. Damper bar develops the torque. Field excitation increases. Yes. Who is helping us to reduce the hunting problem? Damper bars. Therefore, the correct answer is C, option C, the third option. Damper bars will develop the torque so that the hunting problem can be minimized. Okay. Okay. That's all. These are simple basic concepts questions. Remaining questions we can answer after discussing few more topics. Okay, one question here you have, question number 13. You please read this. A synchronous, question number 13. It get 2006 problem again. A synchronous generator is feeding a ZPF lagging power factor load at rated current. What is the nature of armature reaction? Are you finding the answers? Question number 13. First of all, it's a generator or motor. It is a generator. And what is the power factor? ZPF lagging. So what is the nature of armature reaction? Just a moment, guys. Clear? Yes, what is answer? Please respond so that, yes, B, demagnetizing. Simple question. It's a generator, ZPF lagging. We have seen the tabular column already. Okay. Armature reaction will be demagnetization. Okay, any more questions related to the concept? Because I don't have questions concept wise. I just have year wise questions. That's why I need to check all the years. Okay, another question number 16 is also the concept we discussed just now. Question number 16. It is GATE 2014 problem. One more question. In a synchronous machine, hunting is predominantly damped by. Who will damp out the hunting? Just a moment. Yeah. So this is an extremely important question. See, I told you hunting is predominantly reduced by damper bars. Actually, what is happening in damper bars? Whenever you change the load, rotor speed will become either less than synchronous speed or more than synchronous speed. That means a relative speed will be created between ns and nr. Once the relative speed is created, an EMF will be induced in damper winding. That EMF will create circulating currents known as damping current, and that damping current will create extra torque that will damp on the harmonics. So what is happening inside a damper winding? The current that is produced inside the damper winding will obviously create some copper loss in the damper winding only. So according to the options, the most suitable option will be this third one. I think not correct. That is not correct. Just a moment. That is wrong actually. The correct answer is copper losses in the rotor. Because a damper winding will be available on the stator part or rotor part? Rotor part, right? Yes or not? Damper winding will be available on the rotor. Just a moment. Okay. Yes. So damper bars will have some external circulating currents. Therefore, copper losses will be created in the damper bars. That will damp out the harmonics, right? Okay. Oh, I don't know how to use this. What we call. What happened? Okay. Leave it. Right. Let me verify a few more questions. Yeah, that's all. These are the 1 mark questions related to these basic concepts. You don't find 2 marks questions related to basic concepts most of the times. Okay. 2 marks questions are little more concepts we need. Okay. Let's move to the next one. Next one is equivalent circuit of synchronous generator. At the same time, we will discuss about equivalent circuit of synchronous motor also. Quickly we will go through. Yes. Equivalent circuit of cylindrical rotor synchronous generator first. Remember, cylindrical rotor machine circuit and salient pole rotor machine circuit both are different. Okay, slight difference will be there. First, we will discuss about cylindrical rotor machine. And remember, even though our machine is a 3-phase machine, equivalent circuit will be drawn per phase only. Equivalent circuit will be drawn per phase only. Understand? All the parameters that I am going to mark in the equivalent circuit, they are per phase parameters. Okay. So coming to the field, first of all, that is a rotor. Field winding will be excited with DC supply. This is the field voltage and this is the field current. And that will induce an EMF inside the armature. We call it as field induced EMF. And then we have synchronous reactance and then armature resistance. Finally, we will be having the load circuit over here. This is a synchronous generator equivalent circuit. And whatever voltage is available across the load, we call it as terminal voltage. And terminal voltage will always be the reference. Reference means at an angle 0. Then induced EMF will lead that terminal voltage by an angle delta. I hope you know that. From the phasor diagram also we can prove. And this XS is known as synchronous reactance. Synchronous reactance. And that is a combination of armature reactance and leakage reactance, guys. Synchronous reactance is a combination of armature reactance and leakage reactance. Both will be available. Okay. And then combination of this RA and XS, we call it as synchronous impedance. RA plus JXS. Together, we call it as synchronous impedance. I need not to write that. And the machine was generating the current. So current was flowing from EF to VT, and the induced EMF will lead the terminal voltage by an angle known as delta. Delta is known as load angle or power angle. Why it is called as load angle, power angle, all the details you will study in normal class. Now what if I apply the KVL equation here? Can I say current was flowing from EF to VT? So start writing the KVL equation from EF. So EF is equal to VT plus IA RA drop plus IA excess drop. The common mistakes most of the students will do is when they are using this KVL equation, they use it to add the parameters algebraically. But actually we have to add them vectorially, not algebraically. Okay, because it is a AC circuit, phase angles are very important. So vector calculations are very, very important. Clear? So EF and VT are not in phase. There is a phase angle difference, delta. Resistance is there, real part. Reactance is there, imaginary part. So therefore, this KVL equation, we have to add the parameters vectorially. How we have to add vectorially, that you can decide based on the phasor diagram. So I'll draw one phasor diagram related to one power factor, and then directly we will write down equations for other power factors. Okay. So let us try to develop this phasor diagram with respect to lagging power factor load. For example, if I take lagging power factor load, always in power system, terminal voltage will be the reference because it is the bus bar voltage. Normally, our alternator will be connected to bus bar. Okay. Therefore, the terminal voltage is indirectly a bus bar voltage. So let us take terminal voltage as reference. VT at an angle 0. And I am considering a lagging power factor load. When the load is a lagging power factor type like REL type, armature current will lag the terminal voltage. See, armature current was lagging the terminal voltage by a power factor angle phi. Now, for this VT, what is the first drop we have to add? IARA. We know IARA is the resistance drop. As it is a resistance drop, it will be in phase with current. So if this is IA, IARA is also in the same phase. Draw that here. Okay. This is IARA. Okay. What is the next drop? IAXS. Remember, XS is a inductive reactance. As it was an inductive reactance, this is inductor voltage only. Inductor voltage drop. And we know in inductor, voltage will lead the current by 90 degrees. Don't confuse. In inductor, current will lag the voltage by 90. Voltage will lead the current by 90. So this is the current. Leading means anti-clockwise direction by exactly 90 degrees. Draw that here. This is IAXS. Now what is the sum of VT plus IARA plus IAXS? Yes, this summation is nothing but EF. Got it? And the angle between that EF and VT is known as load angle delta. And you can clearly understand from the phasor diagram, induced EMF is leading the terminal voltage or lagging the terminal voltage. Yes, it was leading the terminal voltage by an angle delta. And finally, there is one more angle very important, internal power factor angle. If you see the circuit diagram carefully, which EMF is internal EMF to the machine? The voltage induced inside the machine or internal to the machine, that is EF. Current generated by the machine, IA. Internal voltage EF, internal current IA. So the angle between internal voltage EF and internal current IA is known as internal power factor angle psi. So three angles I defined here. Load power factor angle phi, internal power factor angle psi, load angle delta. So phi is the load power factor angle. This is the angle between terminal voltage VT and armature current IA. Indirectly, angle between load voltage and load current. Next, internal power factor angle psi. Internal power factor angle. It is the angle between internal voltage to internal current. Internal voltage is EF, internal current is IA. Next one, load angle or power angle. load angle or power angle. It is the angle between induced EMF EF and terminal voltage VT. Got it? Clear? So this is a phasor diagram valid for lagging power factor load. Similarly, you can draw this diagram for leading power factor load, unity power factor load also. Okay. Now what I am trying to do here is that, okay, I would like to simplify this phasor diagram so that I will find some important equations from the phasor diagram. See, what I am trying to do is, let us simply extend this IA phasor. Just a moment. Yeah. Let us extend this IA phasor. Also, let us extend this IA axis phasor. Can I say both will meet each other exactly at 90 degrees? Because IA axis is leading IA by 90 degrees. Any issues? Session was running smoothly, right? Yes. Yes, I'll try to discuss those concepts also, if the time permits, right? We can't just jump like that. Yeah. Okay, so this is 90 degrees. Now just extend this from VT phasor, just to draw a parallel line to this dotted line. This is also 90 degrees. Now, are you finding a right angular triangle here? In this right angular triangle, this angle is phi. So what is the opposite side of phi? This is nothing but VT sine phi. What is adjacent side? This length will be, this is going to be VT cos phi. Just a Pythagoras theorem we have to apply. If this is VT sine phi, can I say this length is also VT sine phi? I better use a different color. This is also going to be VT sine phi, because both are parallel, right? This is VT sine phi. One more thing, this length is IARA, right? If this is IARA, what about this small length also? IARA. IARA. Okay, IARA. Now, are you observing a big right angular triangle here? In this big right angular triangle, this side complete length is VT cos phi plus IARA. This side the complete length is VT sin phi plus IA axis. Then is it like EF is nothing but hypotenuse? Therefore, what is the hypotenuse length? EF is equal to square root of one side VT cos phi plus IARA whole square, other side VT sin phi plus IA axis whole square. So therefore, EF is equal to square root of one side, it is VT cos phi plus IARA whole square. The other side, VT sin phi plus IA axis whole square. This is the voltage per phase. And remember, this is the formula when I consider which power factor load? Lagging power factor load. And if you do the same analysis for a leading power factor load, what happens? Everything will be same. You will get minus excess here. Only this is the difference. Remaining formula will remain same for leading power factor. So therefore, I can derive a common equation. So the only difference is here. Plus sign, you will use it for lagging power factor load. Minus sign, you will use it for leading power factor load. That is the only difference. Remaining formula will be same. Next, one more formula from the phasor diagram, that is finding this internal power factor angle psi. Finding this psi. Okay. That means what I will do is that in this big right angular triangle, apply tan psi value, tan of the angle. Can I say in a right angular triangle, tan of the angle is nothing but opposite side by adjacent side? What is the opposite side of psi? This whole length. What is the adjacent side of psi? This whole length. So therefore, if you apply tan psi, so tan psi will be equal to, what is the opposite side? Whole length, VT sin phi plus IA axis. VT sin phi plus IA axis. And what is the adjacent side? This whole length, VT cos phi plus IARA. VT cos phi plus IARA. Most importantly, this is a formula we derived using which power factor? Lagging power factor. And if you apply leading power factor, everything will be same. You will get simply a minus sign here. Okay, just a moment. Yeah. Okay, so the only difference is plus minus here. So once again, when should I use plus sign here? Plus sign, we will use it for lagging power factor. Not only lagging, even for unity power factor also. Unity power factor also, you'll get plus only. And a minus sign, we will use it for leading power factor load. That's all. So the importance of tan psi. Tan psi is an extremely important formula to solve numerical questions. If you use tan psi, you will get first psi value. If you know psi value, then only you can find out load angle delta or power factor angle phi. Remember, one angle will be given in the problem, either delta or phi. For example, if phi is given, they'll ask you how to calculate delta. If you know phi, how can you find out delta? For that, you need to find out psi first. If I find out psi, can I say delta is nothing but psi minus phi only? Yes. Okay, that is how we can solve the problem. Okay, yes. So this is the phasor diagram of synchronous generator, that too lagging power factor. And what if I do the same analysis for synchronous motor? Remember, this is synchronous generator formulas. And if you do the same analysis for synchronous motor, what will happen? You will get exactly similar formulas, but plus will change to minus, minus will change to plus. Why? Because what is the difference between a generator and a motor, guys? If I ask you a simple question, from generator to motor, what is the difference? Yes, direction of current, right? Generator will generate the current, motor will absorb the current. So you will get absolutely same formulas, but in place of plus armature current, you will get minus armature current. In place of minus armature current, we will get plus armature current. So without wasting time, let me discuss motor equivalent circuit also. This is the equivalent circuit of generator. Let us do the same analysis for motor. Just a moment, guys. Okay, sorry guys, just got an important call. Okay, now let us do it for synchronous motor also, so that we can quickly complete both generator circuit diagram and motor circuit diagram. Okay, so equivalent circuit of a cylindrical rotor synchronous motor. Okay, now the point is, synchronous motor means it is a machine where the motor will absorb the current rather than generating, right? So this is the field circuit diagram. For example, we are exciting field circuit with DC supply, field voltage and field current. The induced EMF is field induced EMF. This time in motor, induced EMF will lag the terminal voltage. Remember, in the actual class, we will prove this first and then we will draw the circuit diagram, but I am directly drawing it. Okay, right? Induced EMF will lag the terminal voltage. That's why EMF is at an angle minus delta. Okay, then we have synchronous reactance and armature resistance, and we have a supply voltage here. This time it is not load voltage, it is the source voltage. This is a source voltage, and from this source, machine will draw armature current. This is the flow of armature current. This is the equivalent circuit of a synchronous motor. In generator, machine will deliver the current to load. So Vt is output load voltage, but here Vt is input source voltage. Okay. Input source voltage. Okay. Now, what about the KVL equation in this particular circuit? Current was flowing from Vt to EF, right? So therefore, the KVL equation will be Vt is equal to EF plus IAXS plus IARA, or IARA plus IAXS, whatever. In case of generator, the KVL equation is EF is equal to Vt plus drops, but here Vt is equal to EF plus drops. Okay. Now what we will do is that to satisfy this KVL equation, let us draw the phasor diagram considering leading power factor condition. In a generator, most of the times we will draw for lagging first, then leading, but here leading and then lagging. You can take any power factor, but to make things easy, I'll be considering leading power factor. Okay. So let us draw the phasor diagram for a leading power factor. Terminal voltage is the reference, I told you, right? So you take terminal voltage is reference, that is at an angle 0. Then armature current was leading the terminal voltage. Leading means anti-clockwise direction by a power factor angle phi. Now, what is the first drop? Let me consider IAXS drop first. Remember, XS is an inductive reactance. Most of the students will say, sir, leading power factor means it is a capacitive reactance. Wrong. Machine will have inductive reactance. Please don't forget that. Okay. Yes. Therefore, IAXS is an inductor voltage drop. If it is inductor voltage drop, can I say it will lead the current by 90 degrees? Right? And that IAXS drop, let us draw on the bottom side of Vt. Don't draw it on the top side of Vt because the drop must be added to EF phasor, not to Vt phasor. If you draw this IAXS on the top side of Vt, that means you are adding the drop to Vt, not to EF. Okay. Next, IARA, resistance drop, that will be in phase with current. Draw that here. This is IARA. It is in phase with current. Now this gap is nothing but induced EMF, EF. Okay. And the angle between induced EMF and Vt is known as load angle delta. And this is internal power factor angle psi. Is it clear that induced EMF is lagging the terminal voltage? Yes. In a generator, induced EMF is leading the terminal voltage. In a motor, induced EMF was lagging the terminal voltage. And also, I'm not doing the complete proof. I'll directly write down the EF formula. What is the induced EMF formula? Same formula like generator. It will be square root of, you see the generator formula, Vt cos phi plus IARA. So in motor, it will become minus IARA. Here you will get plus or minus once again, but there in generator, plus is for lagging, minus is for leading. But in motor, plus is for leading, minus is for lagging. Simple way to remember, okay? Right. So this will be first term, Vt cos phi minus IARA whole square plus Vt sin phi. Once again, we will get plus or minus. When should I use plus sign this time? Yes, this time plus sign is used for leading as well as unity power factor. Minus sign is used for lagging power factor. In a generator, plus is lagging, minus is leading, but here plus is leading, minus is lagging. Similarly, what is tan psi formula? Same formula again. What is tan psi here? Vt sin phi plus or minus IAXS by Vt cos phi plus IARA. In a motor, plus will change to minus, minus will change to plus. So in place of plus IARA, you will get minus IARA. So what is tan psi formula? Tan psi will be equal to Vt sin phi plus or minus IAXS divided by Vt cos phi minus IARA. And here plus is for leading and unity power factor, minus is for lagging power factor. These are the formulas for synchronous motor. So the point is, if you learn generator formulas, developing motor formulas is not a difficult task. You can easily do it. Okay, clear? So once again, these are the formulas for generator: EF formula and tan psi formula. All right. Yes. So if you practice one machine formulas, the other machine formula will be very simple. Okay, it depends upon practice. Practice is very, very important. Okay, then only you can remember these formulas in the examination hall. All right. Now let us try to understand, do we have any questions related to these concepts? Okay, probably okay. Yes, we have a question in GATE 2000. This is a concept related to voltage regulation, but we can still answer because we already have the formula with us. At least tell me, before answering this question, can somebody tell me what is the formula for voltage regulation of an alternator? Voltage regulation. Yes, it is the change in the terminal voltage of the alternator from no load to full load, right? It is the difference between no load terminal voltage to full load terminal voltage, correct? What is mean by no load terminal voltage? EF, full load terminal voltage, is nothing but VT. The difference between these two voltage magnitudes is what we call it as voltage regulation. And if I know voltage regulation, how can I find out per unit voltage regulation? Then it is the ratio between actual voltage regulation divided by base voltage. Yes, base voltage is always terminal voltage because it is a bus bar voltage. And if I know per unit voltage regulation, I can easily find out percentage voltage regulation also. EF minus VT by VT into 100. Now, in the given question, VT was already given in the problem. We are simply asked to find out EF value. If I find EF, I can easily find out what is the voltage regulation. That question was given for 2 marks, you just imagine. Okay, if you go through the problem, first point in the question is, yes, it is a single phase induction motor. It is a single phase single phase synchronous generator. That's why there is no difference between line voltage, phase voltage, etc. Yes, and the terminal voltage was 2000, that was given. Armature resistance was 0.8. Synchronous reactance was 4.94. Current is equal to 100 ampere. Power factor is equal to 0.8 leading. What is the voltage regulation? If you note down, VT was 2000, RA was given, XS was given, current was given, power factor was given, just to find out EF, right? So, what is the formula? EF is equal to square root of, direct formula, it's a generator, VT cos phi plus IA RA whole square plus VT sin phi plus or minus IA XS whole square, right? Already VT was given in the problem. How much is VT? 2000 volt. Power factor was given 0.8 leading. When I say power factor, that is cos phi or sin phi, cos phi, 0.8 plus current was 100 ampere. Resistance was given, right? What is the resistance value? Resistance value was 0.8, reactance was 4.94. Resistance was 0.8, VT was 2000. Yes, if cos phi is 0.8, what is sin phi? 0.6. Now the question, plus minus, what sign we have to use? Minus, right? Why? Because the given power factor is 0.8 leading power factor. Leading power factor means we have to use minus. Minus, armature current was 100, excess was 4.94 whole square. So if you solve it, you will get induced EMF value. And the moment you know induced EMF, you can easily find out what is the voltage regulation. Yes. We have to use minus sign because it is a leading power factor. Okay. In generator, leading means minus. Okay. Just use calculator. 2000 into 0.8, 1600 plus 80 whole square plus 1200 minus 494 whole square under root. So I am getting 1822.31 volt. 1822.31 volt. This is the induced EMF. So find out percentage voltage regulation. So EF minus VT by VT into 100. So if you substitute 1822.31 minus VT was 2000 by 2000 into 100. That's all. You will get a regulation, you'll get a negative regulation, right? Minus 2000 divided by 2000 into 100. Okay, I'm getting minus 8.88 percentage. That is the voltage regulation of the given alternator, correct? Yes. That is the voltage regulation of the given alternator. Okay, simple problem. This problem was given for 2 marks. So see, solving questions is very easy, but you should have good practice. Okay. Clear? All right. So 8.8%, approximately 8.9. Let's find, do we have any more questions related to this concept? Parallel operation. Okay, these are all easy questions. I'm thinking about question based on the concept that we discussed so far. Okay, this question we can answer. GATE 2005. It's a simple question. A 100 kV, 1000 kVA, 6.6 kV, 3-phase star connected cylindrical rotor synchronous generator. Take a snapshot. Okay, I will not be solving. I'll give you a clue. After the class, you solve it. Take a screenshot for this question. Take a screenshot, right? Okay, 1000 kVA, 6.6 kV, 3-phase star connected cylindrical rotor synchronous generator has a synchronous reactance 20 ohm. Armature resistance is neglected. Machine is at full load, unity power factor. What is the induced EMF line to line? First of all, you need to be careful that given machine is a 3-phase machine. Okay, given machine is a 3-phase machine. That means this 6.6 kV is the line voltage. Then what will be the phase voltage? 6.6 kV by root 3. Next, this 1000 kVA is the volt ampere rating, full load. What is the formula for volt ampere rating? Root 3 VL IL or 3 V phase I phase. From that, find out current value. Now you have a terminal voltage with you, current with you. You just ask to find out induced EMF. First, you will get induced EMF per phase, then convert to line value. Okay, I will give you the clue, hint. You try to solve it after the class. So terminal voltage was 6600 by root 3 volt per phase. VA rating was given 1000 kVA, but what is the formula for VA rating? Root 3 VL IL. This is equal to 1000 K. From this you will get line current 1000 K divided by root 3 into line voltage 6.6 K. This will give you the line current. But the machine is a star connected machine, right? The machine is a star connected machine. We know in star connection, line current and phase current both are going to be same, right? Therefore, if the line current is this much value, then the phase current is also same value. This is indirectly nothing but armature current. Now you have current with you, terminal voltage with you, find out induced EMF. First you will get induced EMF per phase, then convert to line voltage. Power factor is unity in the given question. Unity means cos phi is equal to 1, sin phi is equal to 0. So solve it after the class. Okay, simple question. Right. Okay. Okay. Right. Sufficient practice. Let's move to the next concept. Okay, it's almost 6 p.m. Okay, so we'll try to spend another 1.5 hours. Okay, all right. So let's move to the next topic. I'm not going through characteristics of synchronous generator, OCC characteristics, SCC characteristics, finding synchronous impedance using those characteristics. I'm not discussing them. Okay, I hope you can study, right? I'll directly go to the important topics. Okay, please study characteristics of alternators. Characteristics of alternators. Mainly, you need to focus on two characteristics: open circuit characteristics and short circuit characteristics. Using both of them, finding synchronous impedance. ZS formula: open circuit voltage to short circuit current at a constant field current, right? You please go through it. Right. I'll try to go to some important topics. The first one is going to be power flow equations. Power flow equations. First we will discuss in generator. Then we will discuss the same equations in motor. Okay. The idea is to understand active power equation and reactive power equation of a synchronous generator. Okay. So to develop the power flow equations, I will draw the equivalent circuit first. Induced EMF is at an angle delta. And then we have armature resistance and synchronous reactance. And finally, we have terminal voltage. Terminal voltage is at an angle 0. Current will flow from EF to VT. This is where the load is connected actually, because it's a generator. Now, two equations we wanted to develop here. One is output power equations, another one is input power equation. If you calculate power on the output terminals, here we will get output power. If you calculate the power at these terminals, you will get input power. Tell me, I'm talking about generator or motor? Generator, right? Generator means, can I say input power will be mechanical and output power is electrical? Okay. So remember, when it is mechanical, it will have active power only. Mechanical terms do not have reactive term, guys. Please remember that. Mechanical power means real power only, active power only. You don't find reactive power. But when it is electrical, we will be having active power output and reactive power output also. Both will be available. Okay. Now we will try to find out what is the formula for active and reactive power output. First output power we will try to calculate, then we will calculate the input power. So to calculate the output active power and reactive power, first we need to find out what is the complex power output. Complex power first, then from that complex power, real part will be active power, imaginary part will be reactive power. So what is the complex power output? So complex power output will be equal to Vt into Ia conjugate. You know, to get complex power, you need to consider Vi conjugate. In power system, you will study what is the importance of that conjugate. So here, Vt is at an angle 0, and you tell me armature current was flowing from EF to Vt or Vt to EF? EF to Vt, right? So therefore, it is EF at an angle delta minus Vt at an angle 0 by Zs at an angle theta. Whole conjugate. Zs at an angle theta. Theta is known as impedance angle. I'm not going thoroughly, I'm just going summary way. Okay. Then if you divide this entire concept into real part and imaginary part, you will get real part, first term, EF into Vt by Zs into cos theta minus delta, right? Minus Vt square by Zs into cos theta per unit. If you want actual power, so we have to multiply this entire equation with 3. This is the active power output. Similarly, what will be the reactive power output? The reactive power output will be EF into Vt by Zs sine theta minus delta minus Vt square by Zs sine theta per unit. These are lengthy formulas. If you continue this equation 2 more steps, you will get these formulas. But these formulas are difficult to remember, so derivation is very, very important. But we can simplify these equations by making a small modification. Yes, we can simplify these equations by taking an approximation. What is the approximation? We know in the equivalent circuit, Ra is very, very small, usually. We will design the winding to have a very low resistance always. As resistance is very small, just neglect it. Then we will be having only reactance. Then what will be the modification you will get? If resistance is neglected, Zs will become Xs. This impedance angle theta becomes 90 degrees, right? Then the power equations will change. So what will happen if Ra is neglected? So if Ra is neglected, impedance will become reactance and impedance angle theta becomes 90 degrees. Then active power formula, active power output will become EF into Vt by Xs into sine delta. Reactive power output will become Vt by Xs into EF cos delta minus Vt. Directly I am writing the equation. You can derive them. You just replace impedance with Xs. My eyes were burning because of these focus lights. Okay. So impedance is equal to Xs and impedance angle theta will be equal to 90 degrees. So this is how you can develop both active power equation and our reactive power equation separately. These are easy equations you can remember. But these are lengthy equations. Even if you try to remember, you can't remember most of the times. Okay, that's why understand the derivation. But remember, these are the output powers only. But what if I calculate input power? Input power means only mechanical term will be there. That means only the real part. And input term is, can I say power at these terminals? Yes. That is EF into this current Ia. So therefore, if I try to calculate input power, that is nothing but a mechanical power, that will be the real part of power calculated internally, that is EF into IA conjugate. Only the real part of this complex power I have to consider. Then only I'll get input mechanical power. Therefore, it is the real part of EF is at an angle delta, right? And VT is again flowing from EF to VT through the impedance ZS, whole conjugate. Then if you resolve into real part, okay, then you will get input power. Then what will be the formula for input power? The first term will become EF square by ZS into cos theta, minus second term will become EF into VT by ZS into cos delta minus theta, or theta minus delta. Okay, just a moment. If I multiply, minus theta becomes plus theta, theta plus delta. This will become theta plus delta. This is the input power, which is nothing but the mechanical power of the machine. This is again a lengthy equation. If you wanted to simplify this equation again, you can neglect RA value. Okay. So if RA is neglected, you can simplify that equation. Then input power equation will also become EF into VT by XS into sine delta. You please understand, the input power equation and output power equation both looks the same, right? Why input power and output power both are same? Because I am neglecting RA, right? Remember, neglecting RA is indirectly neglecting losses in the machine. Neglecting RA is nothing but neglecting losses. If you neglect losses, input power and output power will be same, right? Input power and output power will be same when you neglect RA. Clear? But when RA was considered, then both are going to be different. Okay. Yes. This is about active power and reactive power equations in an alternator. And the moment we know the power equations, now we can understand different types of excitations in alternator. Okay. The three types of excitations: over excitation, under excitation, and normal excitation. Right? Would you like me to discuss the power flow equations of synchronous motor also? You can develop in a similar manner power flow equations of synchronous motor also. But in motor, remember, input power was electrical, output power was mechanical. Okay. Right now, these are the generator equations. Next, you will get motor equations. Okay. Right. Now, let's try to understand the different types of excitations in alternator. Okay. Types of excitations. Types of field excitations. Remember, by controlling field excitation, indirectly field current, we can divide alternator into three operating zones: over excitation condition, under excitation condition, normal excitation condition. While discussing about these three types of excitations, we will be neglecting armature resistance so that we can easily understand the excitations. Okay, I will not be deriving all the conclusions. Okay, I'm not deriving all the equations. I will directly write down what is over excitation, under excitation, and normal excitation. Please remember one thing. First, we will discuss about over excitation. In case of a synchronous generator, over excitation will come into picture when a lagging power factor load is connected. Okay, lagging power factor load, that is RL type load. Then the generator will be under over excitation. I'm not proving it. I'm directly writing the summary points. Okay, proving it will take another 1 hour again. Okay, So if the machine is under lagging power factor case, over excitation will come into picture. And always remember, over excitation means EF cos delta magnitude is greater than Vt. Remember, over excitation means EF cos delta is greater than Vt. Never compare EF and Vt to conclude what excitation it is. Don't say EF is greater than Vt, that's why it is over excitation. We should not say EF greater than Vt, we should say EF cos delta greater than Vt. Then only the machine is said to be under over excitation. Okay? And this will come with which power factor? Lagging power factor case. And during this case, active power will be generated by alternator to the load. Reactive power is also generated by alternator to the load. And most importantly, reactive power is a positive quantity. This is over excitation of an alternator. And during over excitation, focus must be on reactive power. Reactive power was generated by alternator. And if you look at under excitation, first of all, what is mean by under excitation? That means less excitation. Less excitation means EF cos delta will be less than terminal voltage. This is what we call it as under excitation condition. And this under excitation condition comes into picture for leading power factor load. That means when the load is RC type. In this case, active power will be generated by alternator, but reactive power will be absorbed. The machine was absorbing reactive power. And if you calculate, reactive power will become a negative quantity. So a negative quantity of reactive power means alternator was absorbing reactive power. This is a situation of under excitation. Now another kind of excitation we have normal excitation. Okay. Normal excitation means it is neither over excitation nor under excitation, where EF cos delta is exactly equal to Vt. This situation is what we call it as normal excitation of the machine. And this normal excitation will come into picture when the load is unity power factor type load, means purely resistive. If the load is purely resistive, then it is unity power factor. In this case, active power will be generated by alternator. Okay. But the reactive power is neither generated nor absorbed, it is equal to 0. Therefore, clearly you must understand whether it is over excitation. Look at this over excitation, active power generated. Under excitation, active power generated. Normal excitation, active power generated. Therefore, whatever may be the excitation, active power is always generated by the machine. No change in active power. But which power was changing? Reactive power is changing. If it is over excitation, reactive power is generated. If it is under excitation, reactive power is absorbed. If it is normal excitation, reactive power is 0. So how can you say whether a system is lagging power factor or leading power factor or unity power factor? We can answer that based on the status of active power or status of reactive power. Yes, based on the status of reactive power. Active power status will never tell you what is the power factor. Only reactive power status will represent the power factor of the alternator. Got it? This is one thing we have to understand. Okay. Right. Actually, using a phasor diagrams, we have to prove everything. But I'm not going to derive all those things. Directly, I'm writing the summary points. Okay. Clear? Now, over excitation, under excitation, normal excitation. And most importantly, to decide excitation, we have to compare EF and Vt or EF cos delta and Vt. Yes, we have to compare EF cos delta and Vt, not EF and Vt. We have to compare EF cos delta and Vt. EF cos delta and Vt. Remember that. Okay. EF cos delta and Vt. Fine. Okay. Now we will try to answer a simple question related to these power flow equations and the type of excitations. Just let me select a question. Some 2 marks questions we will select. Okay. Okay, look at this question number 43. It's a 2 marks question in GATE 2014 paper. Question number 43. A synchronous generator is connected to an infinite bus bar with excitation voltage of 1.3 per unit. The generator has a synchronous reactance of 1.1 per unit and it is delivering a real power P of 0.6 per unit to the bus bar. Assume the infinite bus voltage is 1 per unit. Neglect stator resistance. What is the reactive power in per unit supplied by the generator to the bus bar? Is this question. A very simple question given for 2 marks. Induced EMF is already given to us. Please look at this. Induced EMF is given 1.3. Synchronous reactance is given 1.1. Real power is given, that means active power is 0.6. Bus voltage, indirectly terminal voltage is 1. What is the reactive power is the question. Do we have a direct formula? Yes. What is the formula? We derived reactive power Q is equal to Vt by Xs into EF cos delta minus Vt. Why I am using this formula? Because Ra is neglected in the question. You please read this. Neglect stator resistance. That is Ra is neglected. That's why that formula is valid. Okay. So to answer this question, I need Vt that was given in the problem 1. Xs was given 1.1. EF was given 1.3. I don't know what is delta. Vt is 1. So to answer what is the reactive power, the only unknown was load angle delta. Yes, to find out that load angle delta, active power information was given. What is the active power given? If you read carefully, active power, that is the real power 0.6. So using that, we know formula for active power, right? EF into Vt by Xs into sine delta. Active power P was 0.6, EF was 1.3, Vt was 1, Xs was 1.1, sine delta. Now you can find out delta value from this equation, right? Okay. So find out what is the value of delta. So 0.6 into 1.1 by 1.3. Okay. Sine inverse of this value. I'm getting delta equal to 30.51. Delta is equal to 30.51 degrees. And substitute that delta here. So therefore, 1 by 1.1 into 1.3 into cos 30.51 degrees minus 1. Okay, this is the reactive power. So cos of this answer into 1.3 minus 1 divided by 1.1. I'm getting 0.109 per unit. That is the value of reactive power. Correct? That is the value of reactive power. Clear? Simple question that was given for 2 marks. You see how easy it is. Okay, let's see. Another question related to the same formulas. Okay, let's answer question number 46. This is actually motor's question. Okay, we have not developed motor formulas, but I hope from the generator formulas we can write down motor formulas also without wasting much time. But actually, if you know motor formulas, this will be easy. Okay, go through this question 46. It is gate 15 question, 2 marks problem. Just go through it. Just have a look at this question. I'll be just back. All right. Any idea? Question number 46. A three-phase 11 kV 50 Hz two-pole star-connected cylindrical rotor synchronous motor. Okay. First of all, the machine is a three-phase machine, star-connected. Therefore, this 11 kV is line voltage. So phase voltage becomes 11 by root 3 kV. Synchronous reactance is given. Synchronous reactance is 50 ohm per phase. Resistance is neglected. The motor has constant field excitation. Please understand this. Constant field excitation means induced EMF remains constant because field excitation will control the induced EMF value. And when I say field excitation is constant, indirectly induced EMF is constant. At a particular load torque, okay, its stator current is 100 ampere at unity power. This is the initial case. Initially, current is 100 ampere at unity power factor. But later, the load torque is increased. The load torque is increased so that stator current becomes 120 ampere now. What is the new load angle is the question. There are two cases in the problem. In the first case, current was 100 ampere at unity power factor. Next case, the load torque is increased. Okay, so see what is going to happen. Let us take case number 1. In case number 1, the terminal voltage was 11,000 by root 3 volt per phase. Current was armature current is equal to 100 ampere. Power factor was unity. This is the first case. At this case, calculate what is the induced EMF. Can I use the formula? Induced EMF is equal to square root of Vt cos phi minus Ia Ra whole square plus Vt sin phi plus or minus Ia xs whole square. It's a motor. Now, important thing is power factor is unity. Unity means what? Cos phi is equal to 1, sin phi is equal to 0. Correct? Also, armature resistance is neglected in the problem. Ra is equal to 0. Then in the first term, only Vt will remain. In the next term, Ia xs will remain. Whether it is plus or minus, you will get a square means positive only. So if I continue, square root of what is Vt? 11,000 by root 3 whole square. Ia 100 into xs was given 50 whole square, correct? Xs value was 50. The reactance was 50 ohm. Okay. All right. So if I solve it, I will get the induced EMF value, right? So 11,000 by root 3 whole square plus 5000 whole square. I am getting 8082.90 volt per phase. This is the field induced EMF. And remember, in the next case also this EMF remains the same. Why? Because they said field excitation is constant. Okay. So now in case number 2, the EMF remains same value, 8082.90 volt. Terminal voltage will be same, 11,000 by root 3, because it is a bus bar voltage. But the new armature current, this time it was 120 ampere. Please understand, the current was increased to 120 ampere this time because the load torque is increased. What is the new load angle is the question. What is the new load angle is the question. The delta value we have to find out. But please understand, in the previous case, what is the power factor? Unity, right? But now the load is increased, the torque is increased, so that machine was drawing more current. What is the new power factor will be? Yes, those who have idea about this, you will study in synchronous motors, right? This is a concept where excitation was constant, load torque is changing. Remember, if load torque is changing, the current will move like this. Okay, when the torque is variable, excitation was constant, armature current will change like this. From leading power factor, slowly armature current will come to unity power factor. Next it will go to lagging power factor. This is how armature current will change when the mechanical load is increasing. If a mechanical load increases, this is how armature current will move. For example, if you start with leading, slowly you will come to unity, next we will come to lagging, further lagging like that. This is how armature current will change its positions when mechanical load is increasing, keeping excitation constant. What is the initial power factor? Unity, right? Already the motor is at unity power factor. That means you are already at case number 3. What if the load torque increases further? Next case will be lagging. So therefore, definitely the new power factor will be lagging in nature. This is in synchronous motor, guys. If the same thing was happened in synchronous generator, exactly opposite thing will happen. Lagging, slowly unity power factor, next leading like that. So lagging, unity, leading, that is in generator, leading, unity, lagging, that is in motor. So the new power factor will be definitely lagging here. Okay, the new power factor is lagging. Now how to find out load angle delta? Already EF is constant, so you have EF with you, VT with you, armature current with you. Power factor is definitely lagging, we know. So what is the first thing I will do to find out delta? Any idea? Yes, I can find out delta if I calculate active power. What is active power formula? EF into VT by XS into sine delta. If I am able to calculate active power, already EF is available, VT is available, XS is available, I can easily find out delta. But right now, I don't have active power value with me. But I can find active power using one more formula. What is that? Root 3 VL IL cos phi. If I'm able to use this formula, I can easily find out active power P. For that, I need voltage, current and power factor. Already voltage is available, current is available. The only unknown is power factor. If I am able to find out power factor, definitely I can find out active power. Using that active power, I can find out the load angle delta. This is the strategy here. How do you find out power factor now? Yes. To find out power factor, I will write down the equation which is known for me in terms of power factor. Yes. What is the formula we know? EF is equal to, actually square root will be there, but if I square on both sides, it is VT cos phi minus IARA whole square plus VT sin phi. Come on, plus or minus? Because I know the new power factor is definitely lagging. In case of generator, you remember, plus is lagging, minus is leading. But in motor, Plus is leading, minus is lagging. Therefore, this is minus. Because the question is from a motor. Already resistance is neglected. So if I continue, EF square is equal to Vt cos phi whole square. This is the first term. In the second term, is it looking like A minus B whole square only? In that, what is A square? Vt sin phi square, B square, Ia xs square minus 2Vt Ia xs into sin phi. What is the sum of first two? Cos square plus sin square is equal to 1. Then Vt square will remain here. Take it to the left side. So EF square minus Vt square is equal to Ia xs whole square minus 2Vt Ia xs sin phi. Substitute everything. You know everything, right? What is EF? 8082.90. 8082.90 square. Vt 11,000 by root 3 whole square is equal to Ia xs. Ia was 120. The new current was 120, remember. Into xs was 50 whole square minus 2. Vt was 11,000 by root 3 into Ia 120 xs 50. What is the only unknown here? Sin phi. Sin phi is the only unknown. So from this, if you solve this lengthy equation, it's not so difficult. It's just a Am I audible now? Am I audible? Yeah, the battery is over for that audio system because of lengthy live session, right? The battery is over, so I just changed it. Please remember, if somebody asks you find out voltage or current simply without mentioning anything, by default you have to answer line values only. Don't confuse, okay? By default it will be line values. Okay. I can't repeat this calculation again. I hope you can understand. Okay, right. Already my legs were paining. I can't repeat again. Okay. Hope you're understanding that calculation. So you'll get cos phi, right? Fine. So once you know cos phi value, using that cos phi, find out active power. So active power is equal to root 3 VL IL cos phi. Okay, so root 3 into what is the line voltage 11,000, what is the line current 120, and what is the power factor we got 0.989. Okay, so this is the active power value. Okay, so how much will come? So root 3 into 11,000 into 120 into 0.989. So as Hughes value is coming 2261157.68. If you convert into megawatts or kilowatts, it will be easy. Now I know active power value with me, but I have one more formula in terms of active power. 3 into EF into VT into XS into sine delta. So using this, you can find out delta value, right? Just a moment. Okay, guys, you got the answer for delta? Yes, any answer? Yes, 47.23 degrees. All of you got the same answer? Remember, guys, in this equation, I am already writing 3. Therefore, this EF is per phase value. VT is also per phase value only. Got it? Now you will get delta. Yes, 47.23 degrees. Okay? Yeah, that is the answer. So the most important thing in this question is understanding what is the new power factor. Okay? Yes. Remember, in a motor, when you are keep on increasing the mechanical load, the armature current movement phasor will be like that. It will be from leading, unity, lagging. If it is generator, it will be from lagging, unity, leading. Okay. So first we will get sine phi, from that we will get cos phi, and then we can find out delta. Okay. Now, some latest questions also we will see. Yes, GATE 2019, it's a similar question. Okay. The terminal voltage was given. You convert to phase value. Synchronous impedance is given. This time RA was given, XS was given. Motor is drawing 10 amperes, 0.8 power factor leading. we are asked to find out internal voltage. What is mean by internal voltage? EF. But we need to find out line to line value. First you will get answer for phase voltage, then convert to line voltage. Easy question, right? Same formula. EF is equal to square root of Vt cos phi minus Ia Ra whole square plus Vt sin phi plus or minus Ia xs whole square. Okay. Okay, let's try to answer question number 55. This is GATE 2022 paper question. Question number 55. Go through that question. This is a recent GATE question, GATE 22 paper. A star connected 3-phase 400 volt 50 kVA 50 Hz synchronous motor has a synchronous reactance of 1 ohm per phase with negligible armature resistance, right? The shaft load on the motor is 10 kilowatt while the power factor is 0.8 leading. The loss in the motor was 2 kilowatt. What is the magnitude of per phase excitation EMF of the motor? Simple question. Shaft load is already given, right? What is mean by shaft load? Indirectly output power of the motor. Output power was given because for a motor, input power is electrical, output power is mechanical. The shaft load means output power was given. Loss power is already given. So can I say output power plus loss power together is equal to input power? And if you know input power, you can easily find out current from that and then find out induced EMF. Okay. So look at this question number 55. Same model. Okay. Output power 10. Loss is 2. So what is the input power? So the input power of the motor will be equal to output power plus loss power. That is 10 plus 2 is equal to 12 kilowatt, right? And what is the formula for input power? Is it not root 3 VL IL cos phi? Because it is electrical power, right? In a motor, input power is electrical. In a generator, output power is electrical. So in this, input power is 12 kilowatt, that is 12 into 10 power 3 is equal to root 3 into what is the line voltage? The line voltage was 400 volt, correct? Power factor 0.8 leading. So the line voltage was 400 volt. I don't know the line current. Power factor was 0.8 leading. So find out current first. You'll get the line current. Similar concept, see how many questions were given. 12,000 by root 3 by 400 by 0.8. I'm getting line current 21.65 ampere. This is line current. Then can I say the same current is valid for phase also, because in star connection, line current or phase current both are same. The moment you know current, you can find out induced EMF. Direct formula. It's a motor. In motor, the formula for induced EMF will be Vt cos phi minus Ia Ra whole square plus Vt sin phi plus or minus Ia xs whole square. Okay, first you'll get phase voltage, then find out line voltage. What is Vt? Ra is already neglected in the problem, correct? Neglected or Ra is given? Ra you can't neglect probably. Why? Because loss is considered, right? Synchronous reactance was given 1 ohm, but don't neglect resistance. Why? Because I think, yeah, it is given. Neglect armature resistance. That means loss is only iron loss and mechanical loss. Copper loss is neglected. Okay. Only iron loss and mechanical loss is 2 kilowatt. Okay. Anyway. So substitute. Vt was 400 is line voltage. So per phase 400 by root 3. Power factor was 0.8 whole square. Vt 400 by root 3. Sin phi is 0.6. It is leading power factor. In a motor, leading power factor is plus sign. and current we just found 21.65 into reactance is 1 ohm whole square. This will give you the induced EMF per phase. If you know induced EMF per phase, you can find out the line voltage also, which is root 3 times of phase voltage. Calculate and let me know the answer. These are 2 marks questions, very simple, right? All right. So find out the phase voltage first and then calculate the line voltage also. Yes, first you will get phase voltage, then you find out line voltage. Directly tell me the line voltage magnitude. It was the 423. One answer came in the chat box. Yeah, find out line value also. Line voltage will be root 3 times of phase voltage. Correct? Yes, 423 is the correct answer. Fine. Okay, right. Let's see any more concepts based on the discussions we had so far. Again, similar question. Synchronous impedance was given. Steady state stability limit. You know what is meant by steady state stability limit? It is nothing but maximum power when delta is equal to yes, maximum power. Steady state stability limit means maximum power 2.5 per unit. The corresponding excitation voltage in per unit will be how much? Okay, first of all, it's a synchronous motor. This is a 2 marks question in GATE 2023 paper. Okay, let's see. Steady state stability limit. Steady state stability limit is nothing but maximum power. First of all, for synchronous motor, what is the maximum power? By default, it is output power, maximum output power. Okay. Yes. In a synchronous motor, what is the formula for output power? This is Vt, this is Ia, this is Ef at an angle minus delta. See here, these are the terminals where you will get output power, right? Output power. Because it is a motor. In a motor, input power is electrical. Output power is mechanical. Here is the one where you will get output power which is mechanical. And I need output power equation. So therefore, the output power, which is nothing but mechanical power, I told you mechanical power will have real terms only. It is a real term of power calculated here. What is the power here? Ef into Ia conjugate. Okay. So if I continue, it is a real part of what is Ef? Ef is at an angle minus delta, and Ia was flowing from Vt to Ef, right? It's a motor, Vt to Ef. So Vt at an angle 0 minus Ef at an angle minus delta by Zs at an angle theta. You have to write this complete formula. Why? Because in the given question, Ra was neglected or Ra was considered? Ra was considered. If Ra was neglected, then input power and output power would have been equal Ef into Vt by Xs into sine delta. Direct formula you can write. But here Ra was considered. Okay, so that's why complete formula we have to write down. Okay, then what is the real term? First term will become Ef into Vt by Zs into theta minus delta. Second term, Ef square by Zs into theta, right, at an angle theta. So therefore, output power will be first term Ef into Vt by Zs into cos, because real term is cos terms, right? Theta goes to the numerator, minus theta conjugate becomes plus theta minus delta. Second term, EF square by ZS into cos theta, right? This is actually the output power equation. But I don't need output power, I need maximum output power. So at what load angle we will get maximum output power? Yes. Maximum output power can be developed when delta is equal to theta, right? For example, if RA is neglected, then maximum power can be developed when delta is equal to 90 degrees. But when RA was considered, maximum power can be developed when delta is equal to theta. For example, if I write delta is equal to theta, theta minus theta 0, what is cos 0 becomes 1. Therefore, maximum power will be equal to EF into VT by ZS. Okay, cos 0 will become 1 minus EF square by ZS into cos theta. Don't forget to multiply this formula with 3 because the given power is actual value, not per unit value. Now, this maximum power was given in the problem. How much is that? 2.5 per unit. This maximum power was, I think, per unit value only. So I need not to write 3 here. Okay. That maximum power was 2.5 per unit. So this is 2.5. I don't know what is EF, but terminal voltage will become 1 because it is bus bar voltage. Then ZS is equal to square root of RA square plus XS square, correct? RA was 0.1, XS was 0.3. 0.1 square plus 0.3 square minus EF square, I don't know, divided by ZS 0.1 square plus 0.3 square into cos theta. Theta is the impedance angle, right? What is the impedance angle formula? Tan inverse imaginary part by real part. That is tan inverse 0.3 by 0.1. You will get impedance angle separately, right? Yes, it was 71.56 degrees. Substitute that here. 71.56 degrees. Are you understanding? The only unknown here was induced EMF EF only. But we are getting a second order equation. If you strictly look at this equation, you will get a second order equation. So you will get two solutions here. Can you solve this equation and let me know what are the two solutions so that we will decide what is the correct solution? Because our ultimate answer is what is the excitation voltage? That is EF. Okay, you'll get two solutions. Let me know both of them. Solve it. Here EF square is there, so you first figure out what is the solution here. What is EF square coefficient, EF coefficient, and simplify and tell me what is the two solutions. Okay, come on. Don't use EV by XS. If you are using EV by XS, that means you are getting a wrong answer. EV by XS is the maximum power when RA is neglected. But in the given question, RA was considered. Therefore, we have to write down exact equation and then maximum power formula. Okay, Pramod, please correct your equation. Yes, come on, solve this equation and let me know what are the two solutions. Then we will decide what is the correct answer. Yes, any solution? Anybody? What is the solution? You cannot take this much time solving a second order equation. What is the induced EMF? Yes, 1.58, correct answer. Both, I think both solutions will be same, right? Both solutions will be 1.58 only. Yes, 1.58. So therefore, the induced EMF will be equal to 1.58. 1.58 is the induced EMF. Okay. So this is an important problem. Steady state stability limit. Actually, this is a power system terminology, right? In power system equal area criterion, you will study steady state stability limit means it is the maximum output power. In a motor, output power means it's a mechanical power. That too, maximum power will come when load angle delta is equal to theta. For example, if RA is neglected, this problem would have been more easy. Then active power equation will become EF into VT by XS into sine delta. Maximum power will come when delta is equal to 90. Correct? That would have been more easy question. That will become 1 mark. But this is 2 marks problem. All right. Fine. All right, guys. Let's move to the next topic. We will quickly try to revise V and inverted V curves of alternator, also synchronous motor, and then we will see circle diagram information. I won't discuss about synchronization methods, that is a 3 dark lamp method, 2 bright and 1 dark lamp method. We don't have that much time. You please study that topic, okay? I'll quickly discuss about V and inverted V curves. Okay, V and inverted V. First of all, V and inverted V curves is a concept we will study when we keep active power constant in synchronous machine and excitation variable. When I write EF is variable, indirectly excitation was variable. If excitation is variable, okay, active power is constant. What is mean by active power is constant? In a generator, who will control the active power? Steam input. So when I say steam input is constant, indirectly active power is constant. In a motor, who will control the active power? In a motor, there is nothing called steam input, right? We don't connect a prime mover to the rotor, we will connect a mechanical load. So when I say in a motor, active power constant means mechanical load is constant. Both cases are same. Steam input constant in alternator, mechanical load constant in motor, both situations are same. So when you keep this active power constant and you only change excitation, definitely V and inverted V curves can be drawn. So V and inverted V curves concept has to be studied only when excitation is variable, active power is kept constant. Okay, and let me draw the curve directly. I'm not proving anything, I'm not trying to prove. Okay, I'm not doing any derivations. Directly we will draw the curve. So what is V curve? First of all, V curve is drawn between armature current and field current. We will take armature current on y-axis and field current on x-axis, and the shape of the curve will be V, and this is a unity power factor point. Unity power factor point. And the right side of the curve, that is a more field excitation, indirectly over excitation, This is lagging power factor if it is generator, leading power factor if it is motor. Left side of the curve, that is less field current, indirectly less excitation. Less excitation means under excitation. In generator, leading power factor is under excitation. In motor, lagging power factor is under excitation. This is V curve of synchronous machine. Both generator and motor directly I am discussing. Single type. Simple point. Right side of the curve, which indicates more field current. More field current means over excitation. In generator, over excitation will come into picture for lagging power factor. In motor, over excitation is for leading power factor. That means for one machine, if you remember the curve, the other machine is exactly opposite. Next, inverted V curve is a concept we will study between power factor and field current. This is inverted V curve. This is the unity power factor. Highest power factor is unity. Once again, right side over excitation, lagging power factor if it is generator, leading power factor if it is motor. Left side under excitation, leading power factor if it is generator, lagging power factor if it is motor. This is inverted V curve. And first question, when do we need to study V curve and inverted V curve? V curve and inverted V curves we have to study when active power is kept constant and excitation is variables. If excitation is variable, active power is kept constant, then we have to study about V and inverted V curves. Okay? Clear? For example, if excitation is constant, active power is variable, then we have to study about performance curve or circle diagram of synchronous machine. Okay, then the phasor diagram we have to draw. For example, if second case, if excitation is constant, active power is variable. What is mean by active power is variable? In a synchronous generator, active power variable means steam input is variable. Steam input is variable. That means maybe increase in steam input or decrease in steam input, anything. In case of a synchronous motor, steam input, mechanical load is variable. Mechanical load is variable. That is active power. Okay. So mechanical load increases or mechanical load decreases. One problem also we solve it like that. In this case, what we need to do, the phasor diagram we have to draw. If you draw that phasor diagram for a generator, I told you how armature current will move. You take terminal voltage as a reference. First, we will start with lagging power factor. Let's say initially alternator is at lagging power factor. If steam input increases, slowly we will go towards unity power factor with increase in current. Remember, current is increasing. See the length of the current. What if I increase the steam input further? Next, unity power factor will come with more current. Next, leading power factor will come with more current. Much more leading power factor with much more current. This is how armature current was changing if a mechanical load was, so not mechanical load, steam input is increasing. If steam input increases. This is a simple way to remember. The exact concept I am not discussing because it will take a long time. So this is how armature current phasor will move when steam input is increasing. What if steam input decreases? Exactly opposite thing will happen. For example, if I say an alternator is already at unity power factor, what happens if steam input increases? Next leading power factor will come. What happens if steam input decreases? Lagging power factor will come. Previous case. Also, whenever steam input increases, armature current will increase. Whenever steam input decreases, armature current will decrease. This is what is happening in a synchronous generator. What about in a synchronous motor? I told you already one problem we solved. In a synchronous motor, the movement will be exactly opposite. You take terminal voltage as reference. We will start with leading power factor. What if I increase the mechanical load? Next, towards unity. I am moving towards unity with more current. Next unity will come, IA3. Next lagging will come with more current, much more lagging, much more current. This is what is happening if mechanical load was increasing. This is happening if mechanical load is increasing. Okay, mechanical load is increasing, excitation is constant. Don't forget, excitation was constant. Excitation was constant, active power is variable. Then the phasor diagram we have to understand. Okay, this is a 3 hours concept in actual class. We are discussing that in 5 minutes. So understand the observations. Okay. All right. So in generators, lagging, unity, leading. In a motor, leading, lagging, unity. This is all when mechanical value is increasing, when mechanical power is increasing. If mechanical power decreases, exactly opposite thing will happen. Okay. Clear? Okay. Now we will try to answer a question related to this concept. So I repeat again, when V and inverted V curves we have to use. When excitation is variable, active power is constant, use V and inverted V curves. When active power is variable, excitation was constant, use these phasor diagrams, phasor diagram concept. Okay. Okay. Right. So now let's try to find out some questions. This is the last discussion, guys, for today. Okay, questions related to this concept. Okay. Mm, let's look at this question number 36. This is a 2 marks question in GATE 2006 paper. Question number 36. Just go through that question. Okay. Look at question number 36. A 3-phase 400 volt 5 kilowatt star connected synchronous motor having an internal reactance of 10 ohm is operating at 50% load. Look at the rated load 5 kilowatt, but machine is only operating at 50% load. That means indirectly 2.5 kilowatt. Unity power factor. Now see what happened. Excitation is increased by 1%. What will be the new load in percentage if the power factor is to be kept at the same value? The aim is to keep the power factor at the same value. Then what must be the new load is the question. So there are two cases. In the first case, 50% load is there, which is 2.5 kilowatt. Using that 2.5 kilowatt load, you find out armature current value, then calculate induced EMF value. Now excitation increases by 1%, that means EMF will also increase by 1%. Find out the new induced EMF. But the aim is to keep the power factor at the same value, unity power factor. What is the new load power is the question. Remember, power factor is unity. Right. Let's answer this question. Simple question only. Okay. So remember, the rated power was 5 kilowatt, but machine is only operating at 50% load. That is 2.5 kilowatt. Okay. Yes. So case number 1. The active power was 2.5 kilowatt, that is 2500 watt. Terminal voltage is equal to 400 volt, that is line voltage. Then the phase voltage will be 400 by root 3. Okay. Power factor is unity, that was given in the problem. Now find out armature current. What is the active power formula? Root 3 VL IL cos phi. Remember one point, this is the load power. Load means output. Okay, but right now output and input both are same. Why? Why? Because armature resistance is neglected in the problem. Therefore losses are neglected, so output power and input power both are same. So therefore, if output power is 2500, input power is also 2500. Okay, so this is 2500 into root 3. చెప్పుదోరు బాబు. All right. So just to substitute the data, the line voltage was 400 volt. Line current we don't know, but the power factor we know, unity, right? So you will get current from here. This will be the line current, then phase current will also be same. Okay, because the circuit is a star connection, right? It is star connected. Therefore, line current and phase current will be same. Using this current, find out induced EMF. Okay, induced EMF you can find out. What is the formula for induced EMF? Square root of Vt cos phi minus IaRa whole square plus Vt sin phi plus or minus IaXs whole square. You have enough practice and you must tell me the answers now. Power factor is unity. Therefore, cos phi is equal to 1. Sin phi is equal to 0. Resistance is already neglected in the problem. Simple calculations, okay? Proceed and tell me what is the induced EMF, guys. Come on, let me know what is the induced EMF. Come on. What is the current you are getting at least? 2500 by root 3 by 400. It was 3.60. Okay. Yes, what is the value of induced EMF, guys? Yes, current you got to find out induced EMF also. Quickly you need to answer. 3.60 ampere is the current. Now substitute that current in the above equation, you'll get induced EMF, right? Vt was 400 by root 3. Don't forget to substitute only phase values. 400 by root 3 whole square plus IAXS, that is 3.60 into what is the excess value? Excess value will be available in the problem, right? Excess value was equal to 10 ohm. Excess value was 10 ohm whole square under root 233.72. 233.72. This is the induced EMF. Now the point is excitation increases by 1%. It is given in next case, case number 2. Excitation increases by 1%. Therefore, the induced EMF will increase. It was increased by just 1%. Therefore, the new induced EMF will be equal to 1.01 times of the old induced EMF. 1.01 times of what is the old induced EMF? 233.72. This is the new induced EMF. But we wanted to maintain a power factor constant. That means once again, the new power factor must be unity power factor. For that purpose, what is the new load I have to connect? That means indirectly active power is changing. What is the new active power we have to connect so that power factor will be remaining constant? Okay. So what is the new induced EMF? This will be simply 1% more. It will be 236.06, right? That is the new induced EMF. But we wanted to maintain power factor at the same value. What is the new load is the question. Now what to do? I wanted to calculate new active power. I have two formulas for active power. One is root 3 VL IL cos phi. In this, terminal voltage is constant. Power factor is also constant. We wanted to make sure power factor is unity only. Okay. All right. I don't know what is the current. You have to find out current. Yes. So to find out new power, I have to find out new armature current. Or else we have one more formula available, right? Active power, we have another formula. What is the other formula? The other formula was 3 into EF into VT by XS into sine delta. This is one more formula. In this formula, VT is already available. The new induced EMF is also available. XS is available. Therefore, if I find load angle delta, I can find out active power. Now, how do you find out load angle delta? That is where you can use this information. What is a power factor? Unity power factor. Unity power factor means which excitation? Normal excitation, right? What is mean by normal excitation? Normal excitation means EF cos delta is equal to VT, correct? In this, EF is known, 236.06. Delta is unknown. VT was known, VT was the 400 by root 3. Now, if you solve it, you will get a delta value first. Substitute that delta here, you will get new active power. So directly tell me what is a new active power, guys. Okay. Directly tell me what is a new active power. First, to find out a new delta. From that delta, you will get a new active power. Yes. What is a new load angle delta? It's 236.06 into root 3 divided by 400 and cos inverse of that value. Yes, normal excitation means EF cos delta is equal to VT, right? Is the terminal voltage 400 only? Yes, 400 by root 3 by 236.06. Yes, delta is equal to 11.95 degrees, correct? Delta is equal to 11.95 degrees. Substitute this 11.95 degrees in this equation. You will get directly active power P. Okay. I'm using 3. These are per phase values. Just to substitute. So the new active power will be equal to 3 times of EF is 236.06. VT was 400 by root 3 by XS is already in the formula it is given XS is 10 ohm. 10 into sine delta. What is the delta value? 11.95 degrees. 11.95 degrees. This is what is going to give you the new active power. Okay. So the new active power will be 87 watt. But the question is to find out new active power or percentage of the power. You see, the rated power was 5 kilowatt. Then the new power is how much percentage of it? The new power is how much percentage of it? So therefore, percentage load will be equal to this 3387 divided by the actual load 5 kilowatt. So indirectly 3387 is how much percentage of 5000? It was 67.75 percentage load. 67.75% load. Therefore, the new load is 67.75. That is option A. This is the correct answer. That is the correct answer. Okay. Remember, you have to compare with rated load 5 kilowatt. Don't compare with 2.5 kilowatt. Earlier the load was 50%. Now the load was 67.75%. Okay. That is the new load, the new percentage load. Clear? 67.7% load, so that I can maintain the same power factor unity. Okay, that's all. So that's all, guys. So I will conclude the session here today. So within the available time, whatever the topics are possible, I discussed. The missing topics you have to study still. Okay. Any questions, you can let me know in the chat box. Any questions, please let me know in the chat box. Please let me know if you have any question. This is your next marathon session. Will start tomorrow. A session on operational amplifiers by Gautam sir from analog electronics subject. Okay. Yes. Yes, I'll take one more session as I said for the other two machines. It's been more than 8 hours, so I'm concluding the session here today. Whatever the missing topics are there, you please study, or else we will discuss in the next session. Okay. Right. So the next marathon you will get tomorrow from analog electronics. Yes. Floating condition means the condition where the machine just synchronized with infinite bus bar. That is the condition where induced EMF will be same as a terminal voltage. And the load angle delta will be 0. No active power, no reactive power. That is what we call it as floating condition. Okay. All right, guys. So I will conclude the session here today, and all the very best. We will meet in the next session. Whenever possible, I'll take the session, one more session, to discuss the remaining two missions. Okay. Yes. Thank you.